depending on what you actually mean by the word statistics. We looked at the difference between the population and the sample, between a statistic and a parameter. We focused on variables. We realized that there were 4 different levels of variables: nominal, ordinal, interval, and ratio. And we ordered it in that way because as you move up, as you go from nominal to ratio, the variables themselves hold more and more information. We talked about the difference between a sample and a census. A census, you talk to every single thing in the population. Which population? Just the population. Usually we talk about the target population. Although sampled population also works for the census, it's just the population. Make sure you do know the difference between the sampled population and the target population. And then we went forward. We looked at classifying data or variables. You could do it in terms of qualitative or quantitative. Another word for qualitative data is categorical. Another name for quantitative is numeric. There's 2 types of qualitative data. There's nominal and ordinal. There's 2 types of quantitative data. There's interval and ratio. Nominal data only has a name attached to it. There's no ordering, there's no intensity, it's just a name, which is where the word nominal comes from. Ordinal data takes its name, has that name, but it also has an implicit ordering to it. So going from nominal to ordinal, you gain ordering, which is why it's called ordinal, which is a portmanteau of ordered nominal. Moving on to interval, you get not only that ordering, but the distance between any 2 values is the same throughout the scale. So we can now meaningfully speak about subtraction. And finally, the ratio, moving on, not only do we get that meaningful subtraction, but we get meaningful division. Ratio data has a 0 point, and that 0 point means lack of whatever is being measured. Interval, you can have a 0 value, but that doesn't mean a lack of anything. And the numeric data can be broken up into continuous or discrete. Discrete data, you can enumerate all the values. And since it is numeric, you can order all the values so that between 2 adjacent values there is nothing else. Whereas continuous, you cannot order it because between any 2 adjacent values there's another value. So think of discrete as being natural numbers based or integers based. Think of continuous as being reals based. Still in the first chapter, we looked at several sampling methods. We looked at random sampling, which is in many ways the gold standard. The problem with random sampling is that the variation in the estimates is larger than we would like it to be. Of these 5, only random sampling is guaranteed to be an unbiased method. The others are biased to one point or another. Stratified sampling, you break your population up, you group your population according to some variable that's related to what you're trying to estimate. So if we're trying to estimate heights of a population, we would break it up according to perhaps gender, because females tend to be smaller than males. If we're trying to estimate IQ, we would not want to do it based on gender because female IQs and male IQs are about the same. In fact, the only difference between the 2 is going to be down in the 100th place. So stratified, you break it up according to a grouping variable that's related to what you're trying to estimate. Cluster sampling, on the other hand, you break it up according to a grouping variable that's not related to what you're trying to estimate. So if we look at, if we're trying to estimate height, maybe we would like to cluster on city, which we did in the first laboratory activity. And of course, we are assuming that Galesburg Heights and Monmouth Heights are about the same. Fourth one is systematic, where you pick a random starting point and then you go every nth entity. So every 5th person, every 25th jar, etc. All 3 of those are biased. Cluster sampling, of those 3, cluster and systematic are the closest to being unbiased. Stratified will be a better estimator. It'll be closer to being unbiased if your estimates of the population proportions are correct. However, all three of those have one advantage over random sampling. The variation in the estimates, remember lab D, the variance in the estimates is much smaller for those three than it is for simple random sampling. And then, of course, convenience sampling, which should not even have on there. Lab B, we looked at stopping rules. We looked whether or not we should replace the person back into the population to draw, or if we should remove that person. That was the main difference between the binomial and the hypergeometric schemes. And then we focused again on representative. The sample you get needs to be representative of the population as a whole. Note that on any single sample, it may or may not be representative. You could do perfect simple random sampling and still get a sample that is not representative of the population. Just random chance. Conversely, you can do convenience sampling and get a sample that is representative of the population. You might luck out. So this representativeness allows us to take the sample and apply what we know about the sample to the population. The key for those sampling methods is how to get that representative sample. From there, we moved on to graphical descriptions in Chapter 2. We looked at several different graphical displays. Basically, what we were able to use was based on the type of data we had. Pie charts, bar charts are good for nominal and ordinal data. Side-by-side bar charts and stacked bar charts are good for bivariate categorical, that is, two variables that are both categorical. Histogram, box and whiskers plots are both very good for numeric data. Stem and leaf plots it's okay for numeric data. Of these, you've done histograms a lot, you've done box and whiskers plots a lot, you've done bar charts a lot. So you should know how to do those. And in fact, if you look through the literature in your own field, you'll see bar charts, histograms. Sometimes you'll see box and whiskers plots, but not too frequently. Going from graphical, where we get to see a picture of the data, to numeric, where we see little snapshots of aspects of the data. We looked at several measures of center, mode, median, mode, mean, and median. The mode is the value that occurs most often. The mean is the arithmetic average of all the values, and the median is the middle number if you rank all the values from smallest to largest. An outlier is a value that is far from the middle clump of the data. There are numeric rules for outliers, but it's more important to be able to look at a histogram or look at a box and whiskers plot and say, hey, that point right there, that's an outlier. We also looked at measures of dispersion. We quickly looked at range, then dismissed it. We looked at variance and standard deviation. If you're able to use the mean, that is, if the data are sufficiently symmetric, then you would also use the variance and or the standard deviation. If you cannot use the mean as your measure of center, that is, if the data are sufficiently skewed, according to the Hildebrand rule, then you'd use the interquartile range. And then in the book, it covered the coefficient of variation. I didn't say too much about it. Coefficient of variation is just a scaled standard deviation. And we also looked at the empirical rule and Chebyshev's inequality. Empirical rule popped up again in chapter 7, 6, 7, 8, 9, 10, well, whenever you were dealing with the normal distribution. Because the normal distribution fits the requirements of the empirical rule, and those cutoffs come from the Z table in the back of the book, the standard normal quantiles. We looked at some others, the percentiles, which we also can call the quantile. We looked at quartiles. A quartile divides the data up into 4 parts, whereas the median divides it up into 2 parts, and the percentile or the quantile divides it up into 100 parts. We also saw the 5-number summary, which is the minimum and the maximum values, the first and third quartile, and the median. So it's really just the 5 quartiles. And then we looked at the standard score, which reared its ugly head again later in chapter 6, 7, 8, 9, 10, 11, etc. Standard score is just x bar minus the median divided by the standard deviation. And we saw later in the book when we apply the standardization, that is, subtract off the expected value and divide by the standard deviation, you go from a normal distribution to a standard normal distribution. That is, it's a normal distribution with mean 0 and standard deviation 1. And this brought us to chapters 5 and 6. Chapter 5, we looked at discrete distributions. In doing that, we had to figure out what a random variable was, and we saw that a random variable was just the outcome of a probability experiment. We looked at some properties of discrete random variables, learned what a sample space was. It's the set of all possible outcomes of that random variable. Talked about probability, expected value, variance, standard deviation. We have a formula for the expected value, but ultimately the expected value is the long-run average of the outcome of that random variable. So if I do the experiment a gazillion times, the average of all those outcomes will be the expected value. And the variance and the standard deviation that we calculate will be the variance and the standard deviation of all of those values. We looked at the binomial random variable. We had the 5 requirements. What are they? Number 1 is the number of trials n is known. 2, each trial is a success or a failure. 3, the probability of a success is constant throughout the binomial experiment. 4, each outcome is independent of the others. And 5, the random variable is the number of successes in those n trials. And we use the binomial as a basis for all other discretes, comparing them all to the binomial. Sample space is all numbers 0, 1, 2, 3, all the way up to n, the number of trials. There's a formula for the probability mass function if we need to calculate probabilities. But we know we can use d binom in R to calculate those probabilities. The binomial has 2 parameters, n and p. N represents the number of trials, p represents the probability of success for each trial. We know the formula for the expected value of a binomial is n times p, and the variance is n times p times 1 minus p. The next one was the Poisson. We looked at the requirements, compared those requirements to those of the binomial. For the Poisson, there is no n. There are binomial trials, but those trials are done over time or space. So the sample space for a Poisson is 0, 1, 2, 3, 4, 5, all the way up to infinity and beyond. We could calculate probabilities using the Poisson's probability mass function and doing it by hand, or we could use just d POIS and R. Poisson has just one parameter. It's lambda. It is the expected value. It is also the variance. Proving that lambda is the expected value or is the variance requires mathematics, specifically probably applied calc. Definitely it's done in Math 175, which is discrete mathematics. We also briefly looked at the hypergeometric simply because of Lab B. The main difference, or the only difference between the binomial and the hypergeometric is with the binomial, either the population that you're drawing from is infinite, or you put the person back after each drawing. For the hypergeometric, finite population, and it's without replacement. Notice I'm not asking you to know the formulas for the expected value or variance for the hypergeometric. And I'm also not asking you to remember the sample space for the hypergeometric. Just want you to know the difference between the hypergeometric and the binomial. And at that point, we moved on to continuous distributions. It's kind of a counterpoint to the discretes. Notice we're in blue here. That means that this is stuff that's not in Hawks. We covered three main distributions, three main continuous distributions, the uniform, the exponential, and the normal distribution. Uniform distribution is characterized by a constant likelihood. There are two parameters for the uniform, minimum and maximum. Sample space is all real values between the minimum and maximum. The expected value is the average of the minimum and maximum. The variance is the square of the difference between the minimum and maximum divided by 12. Those two, well, expected value, you can do that with simple high school geometry. The variance you do need calculus to figure out. The shape of the uniform, it's a flat top. You can think of it as a rectangle. But the key for this is where we introduce the importance of the cumulative distribution function, the CDF. For continuous distributions, probability is just area under the PDF curve. We are able to calculate the CDF, the cumulative distribution function, from that definition of cumulative distribution. It's the probability of x being less than or equal to a value. We're able to use high school geometry to do that. Quantiles are those x values that give us the requested percents. So if I want to find the 50th quantile, or the 50th percentile, I would find the x value such that 50% of the data, or 50% of the distribution, is to the left of it, is less than or equal to it. If I want to know the 5th quantile, or the 5th percentile, then I would find the x value that gives you that has 5% of the distribution to the left. Uniform distribution was very easy to work with because it was just rectangles. And we moved from there to the exponential, which was no longer rectangles, but had a nice CDF function that I showed you how to do it if you knew calculus, and if you don't know calculus, I didn't show you. But it does give you a formula for the CDF, which is something that's missing from the next distribution. Exponential distribution has one parameter, it's lambda. It's 1 over the expected value. Sample space is all real values from 0 onward. The variance is the square of the expected value. The shape is of an exponential decay. We got the CDF for the exponential, and the quantiles again, easily to calculate from the CDF. Quantiles, you're given a probability and you want to find the x value. For the CDF, you're given an x value and you want to find the probabilities. Quantiles and CDFs are inverse functions of each other. The third continuous distribution that we looked at is the normal distribution. Now with the uniform distribution, we could do all the calculations because it was just looking at rectangles. The exponential, we could do the calculations as long as I gave you the CDF. The normal distribution, you don't even get the CDF. There is no CDF for the normal distribution. Mathematically, it can be proven that one cannot write the CDF for a normal distribution in terms of elementary functions. Which is why there's a table in the back of the book. Or, more importantly, which is why for the uniform, exponential, normal, and a gazillion other distributions, you can use R to do the calculations with little trouble. There are two parameters for the normal distribution, the mean and the standard deviation. Sample space is all real values. Expected value is the mean. The variance is sigma squared. The shape, remember back to the empirical rule. What was the shape we had to have before the empirical rule applied? Yep, it's the normal distribution shape. Bell-shaped, unimodal. And the probabilities and the quantiles, the CDF and the quantile requires a back of the book table or your computer. The CDF for the normal is P norm. The quantiles for the normal would be Q norm. And this led to the central limit theorem, the most important theorem in all of statistics. The statement of the central limit theorem is essentially as the sample size increases, the distribution of the sample sums or the sample means becomes more normal. Notice it's a statement about the distribution of the sample sums or sample means. Notice it's also about the sample sums or the sample means. And finally, note that the central limit theorem tells us about the distribution of the sample sums or the sample means. You got that yet? And in fact, labs E and F, in fact, lab C, I believe, all dealt with the central limit theorem in some way. So you may want to revisit those labs to see how the central limit theorem was exemplified or illustrated by those labs. But it was the central limit theorem that led us to the second half of the book, the statistical inference half, and also allowed us to just focus on the normal distribution most of the time. So now confidence intervals. We talked about what a confidence interval was. It's a set of reasonable values for that population parameter. And then we used R to do the calculations for us because our brains are good for interpreting output and computers are good at doing the calculations themselves. So we know how to estimate a population mean when sigma is unknown. We use the T procedure if we can. T procedure requires that the data are generated from a normal distribution. So we test to see if the data come from a normal distribution. We use the Shapiro-Wilk test. If it passes the Shapiro-Wilk test, we get to use the T procedure. If it doesn't, we move down to the next level, the Wilcoxon procedure. Wilcoxon procedure requires the data come from a symmetric distribution. We test symmetry of data from using the Hildebrand rule. If it passes, yay, we get to use Wilcoxon test. If it doesn't pass, well, now we got to use the nonparametric bootstrap. Throughout all of that, we learned what the margin of error was. We thought about the effects of population variance on that margin of error. As the population variance increases, the margin of error also increases. Look at the formula for the confidence interval to see that. Effects of the sample size and the margin of error. As the sample size increases, your estimates become more precise. That is, margin of error decreases. And we also saw the effects of alpha on that margin of error. As alpha increases, the margin of error decreases. But the consequence of increasing alpha is you also increase your type 1 error rate, which we may want to do, we may not. I tend to stick to 95%, I tend to stick to alpha equals 0.05 pretty much. We looked at estimating a population proportion, a single one. We'd use the binomial test. All of those things kept coming back. The meaning of the confidence interval. How do we calculate the confidence interval? The margin of error, the effects. These are true for all confidence intervals. The difference is what test we run. For a single population mean, we use a t-test, or a Wilcoxon test, or a bootstrap. For a single population proportion, we use a binomial test. For a single population variance, we use the chi-squared test, the one variance test. Then we moved on. Confidence intervals on the difference of means. Notice those 6 bullet points are the same because they carry through all of this confidence interval stuff. That's why Chapter 8's lecture was so important, because it laid the meaning of these confidence intervals. Difference of population means, we'd like it to be a 2-sample t-test. Requires normality in both groups. We test normality with Shapiro-Wilk test. If it passes, woohoo, we get to use the 2-sample t-test. If it doesn't pass, then we have to use the Mann-Whitney test. There are assumptions to the Mann-Whitney test, but they are beyond the scope of this course. Difference of population proportions For two population proportions, we're now using the proportions test. Ratio population variances, we're using Fisher's F-test. But at the end of the day, the meanings of those confidence intervals are all the same. It's a set of reasonable values for the population parameter. Just on this slide, that population parameter is the ratio of the two population variances. On the previous slide, it was the difference of two population proportions. And on slide 30, it was the difference of two population means. That was the parameter that was being estimated. Hypothesis testing, the meaning of p-values and hypothesis tests. We covered the fundamentals of hypothesis testing. The scientist gives the research hypothesis, and you as the statistician create the null and the alternative hypothesis from that. Either the null or the alternative is going to be the research hypothesis. Depends on if the research hypothesis has an equals part or doesn't. If the research hypothesis has an equals part, that is if the sign is greater than or equal to, less than or equal to, then it's also the null hypothesis. If it does not have the equals part, that is if it uses less than, greater than, or not equal to, then it is the alternative. The null and the alternative are opposites of each other. The idea is to create a test statistic that relates some statistic on your data to your population parameter. And then it is mathematically scaled in some way to give you a distribution that is known or is knowable. The distribution of the test statistic is known or is knowable. We talked about statistically significant and practically significant. All that statistical significance tells us is that it's not zero, that there is a difference, that there is a relationship. Practical significance is what the scientist does. You come back to the scientist with that confidence interval as a set of values that are reasonable, and the scientist is going to say, yeah, those are practically significant. That's an important finding. Or, okay, so it's not zero, but it's close enough to zero that I don't care. Let's move on to the next analysis. So for instance, there is a statistically significant difference in IQs between males and females. It's not a practically significant difference. The difference is 0.0, if I remember correctly, it's 0.018. Remember, average IQ is 100. Standard deviation is 15. So a difference between the means of males and females of 0.018 is not practically significant. It's a cool, it's not zero, but who cares? It doesn't mean anything. That level of significance is what we choose, or what our discipline chooses for us, and it's what we always compare the p-value to. If the p-value is less than or equal to alpha, we reject the null hypothesis. Note how it always comes back to that null and alternative hypothesis that we created, which reflects the research hypothesis of the statistician, of the scientist. So compare the p-value to alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis. But I think more importantly, we report the p-value and the confidence interval. Because if the p-value is 0.049, we may officially reject the null hypothesis, but come on, it's not that far from 0.05. That p-value is can actually be thought of as a measure of how well the data support the null hypothesis. So from that standpoint, there's really not much difference between a p-value of 0.049 and 0.051. However, if we are wedded to an alpha of 0.05 and a reject or fail to reject mindset, there is a big difference between 0.049 and 0.051. One of them you reject the null, the other one you can't. As statistics moves forward, we're going to be dealing with, as statistics, the field moves forward, we're going to be trying to tease out what that actually means for our scientists, our clients. If we do get 0.051 for our p-value, what are we going to tell our clients? If we get 0.049, what are we going to tell them? And what is the right thing to actually tell them? Open question at the moment. We looked at hypothesis testing. Once we got beyond that theory, we looked at how to actually do the hypothesis testing in R. For one mean, we would like to use the t-test. However, the t-test requires the data come from a normal distribution. How do we test if the data come from a normal distribution? We use the Shapiro-Wilk test. If it passes the Shapiro-Wilk test, we can use the one-sample t-test. If it doesn't, then we move on down the list. Wilcoxon test is next. Wilcoxon test requires that the data come from a symmetric distribution. We test using the Hildebrand rule. If it passes that test, yay, we get to use Wilcoxon. If it fails, we have to use the nonparametric bootstrap. Now then, some of you have asked, why does the Wilcoxon test require symmetry? And the answer is it kind of doesn't require symmetry. Originally, the Wilcoxon test was created to test for the median, to get estimates on the median or to test for median equal, less than, etc., some value. That's why when you see the Wilcoxon output, you see pseudo-median given to you. So the Wilcoxon test is actually a median test. However, if the data are symmetric, what do we know about the mean and the median? Therefore, if the data are symmetric, we get to use Wilcoxon test to tell us about the mean of the data. If the data are not symmetric, then we can still use the Wilcoxon test, but all it's telling us is the median of the distribution. Hypothesis testing for 1p. This is the binomial test. Hawks wants you to use the z-test, the Wald test for this. But why would you use an approximate test if you can do an exact test? The binomial test is that exact test. Notice how these tests that we're looking at here for the hypothesis testing are the same procedures we used back with the confidence intervals. All we're doing differently is now we're looking at the p-value and interpreting the p-value, whereas before we were looking at the confidence interval in that output and interpreting the confidence interval. And the reality is you should, in all of your analyses, provide both. Hypothesis testing for a single sigma squared or single population variance, that'll be the chi-squared test. By the way, why is it called a chi-squared test? It's because the test statistic follows a chi-squared distribution. Same reason they're called a t-test, because the test statistic follows a t-distribution. Or an f-test, test statistic follows an f distribution. Or a z-test, test statistic follows a z distribution. We get we run out of names to give it, so we just name it after the distribution that the test statistic follows. That's also why there's so many chi-squared tests. This is a chi-squared test for a single variance. You've also seen chi-squared tests for goodness of fit and for independence of categorical variables. And again, for the same reason, the test statistic follows a chi-squared distribution, at least approximately. And then we moved beyond that. We moved into some additional hypotheses that we can test. Difference in μ's. We would like to use a two-sample t-test. Two-sample t-test requires that the data are normal in both samples. Test it with the Shapiro-Wilk test. If it passes, use the two-sample t-test. If it doesn't pass, use the Mann-Whitney test. Again, same process as you did for estimating the difference in two population means. Here, all we're doing is testing the difference in two population means. Same thing for the difference in two population proportions, or the ratio of two population variances. Same tests are being run, the same code, just we're paying attention to a different aspect of it. Instead of looking at the confidence interval part of the output, we're looking at the p-value part of the output. Then we move beyond that to some particular hypotheses that can be tested, but for which there is no confidence interval, such as testing for multiple means, the analysis of variance, ANOVA. The null hypothesis for ANOVA is that all of the means are the same. All of the population means are the same. At least that's one of them. Which means the alternative is at least one is different. ANOVA has two assumptions to it. Assumption number one is normality in each of the groups. Assumption two is the variance is constant for all of the groups. How do we test the assumptions in ANOVA? How do we test normality? Shapiro-Wilk test. How do we test equal variances? Fligner-Killeen test. And if the assumptions are not met, we'll use the Kruskal-Wallis test. We also looked at testing goodness of fit of a discrete distribution. The assumptions of the chi-squared goodness of fit test are the same as they were for the two sample proportions test. It's going to be the same as for the chi-squared test of independence. It's that your sample size is large enough so that the normal approximation to the binomial is a good approximation. Testing for independence of two categorical variables. It's another chi-squared test. And then finally looking at testing for independence of two numeric variables. If all we want to know is if they're correlated or related, we can use a correlation test. If we want to know how, if we want to model the dependent variable, which is really what we want to do, we want to get more and more information from the data. We don't want to throw away information from the data because it's expensive to collect that data. We want to get as much information from it as possible. Then we're going to do a regression test. We're going to try to fit your data with a line. Lines have slopes and intercepts. We're going to get p-values off that, confidence intervals for slopes. We're also going to be able to get prediction intervals and confidence intervals for observations. Prediction intervals for another observation, and I guess confidence interval for an expected observation. Hello and welcome to this video, section 1.1, Getting Started. In this section, we're going to learn the vocabulary of statistics, the basic vocabulary at least. We're going to distinguish between a population and a sample, and we're going to distinguish between the two types of populations, the target population and the sampled population. So let's begin. The goal of the branch of mathematics, and these are the words from Hawks, the goal of the branch of mathematics called statistics is to provide information so that informed decisions can be made. I disagree 100% with this statement. Statistics is not a branch of mathematics. Sure, we use numbers, we use formulas, but then so does chemistry and physics, and they're not mathematics. Statistics is a science. It proceeds forward based on inductive reasoning. Tries to learn about the larger whole based on your smaller sample. Mathematics, on the other hand, draws from the larger to bring down to the narrower. Deductive reasoning. So statistics is actually a branch of science. The goal of this text is to enable you to filter through the statistics you encounter so that you may be better prepared for the decisions that you make in daily life. As befitting most things in statistics, the word itself has a couple definitions. The first definition is that statistics is the science of gathering, describing, and analyzing data. So it's the science of gathering, describing, and analyzing data. Hawks admits that it's a science. We can also use the term statistics as the actual numerical descriptions of sample data. In other words, statistics are a function of your data, a mathematical function of your data. Target population is a particular group of interest. A sampled population is a group from which the sample is taken. Hopefully those two populations are the same. They don't have to be. If I would like to draw a conclusion about the population of Galesburg, that's my target population. If I contact people based on the numbers in the phone book, the people in the phone book are the sampled population. Target population and sampled population in that case are not the same. Hopefully, however, the sampled population is representative of the target population. A sampling frame is a physical list of all members of the sampled population. This may or may not actually exist. In the example I just gave, the phone book will be the sampling frame. A sample is a subset of the population from which data are collected. A subset of the target population. No, not from the target population. From the sampled population from which the data are collected. It's this sample that we're actually going to apply our statistics to so that we can learn about the target population. Now, hopefully, our sample is representative of the target population. If the sample is not representative of the target population, all the work that we're going to do is worth nothing. The sample must be representative. And we're going to see some ways of obtaining what are called, quote, representative samples in the future. A census is a study from which the data are obtained from every member of the population. Every member of the population. The United States is required to hold a census every 10 years. That is not the type of census that we're talking about because the U.S. Census Bureau is not able to contact every single resident of the United States. It tries, it does a good job of it, but it never actually achieves their goal of a genuine census. So now, let's turn to an intra-lecture question. These questions you'll have to answer these questions in Moodle for section 1.1. It's just to check that you are moving forward through these at a good pace. So the first intra-lecture question for this section, what is the difference between a population and a sample? What is the difference between a population and a sample? Remember, you can pause this. You've got that little double bar thing that you can push on, pause it, so you can do the answers in Moodle right now. I recommend that you actually write the question and the answer in your notes on the left-hand side. But regardless, you can pause, and I can go back to the lecture. A variable is a value, like 4, or a characteristic, like blue, that changes among members of the target population. It's got to change among members of that population, because if it is constant among all members, that is, if all members of the population have the same value, such as blue, there's really nothing to study. It's just blue. Data are the counts, measurements, or observations gathered about a specific variable in a population in order to study it. So data is what you actually mark down from your sample. Do not confuse a parameter with a sample statistic. A parameter is a numerical description of a population characteristic, whereas a sample statistic is a description of a sample characteristic. So parameters are about the population, statistics are about the sample. P for population, P for parameter, S for sample, S for statistic. We want our sample statistics to be good estimates of the population parameters. And that goal will actually dictate some of the formulas that we'll see in the future. Here's our second question. What is the difference between a parameter and a statistic? Remember, these go into your Moodle quiz, but again, I recommend on the left-hand side of your notes, write out the question and the answer, and then later put it into Moodle. And again, remember, you can pause if I go too fast. It is essential that you are mindful of the relationship between a population and a sample. The next figure is a picture to help you visualize this relationship. So that big blue oval is the target population. That is the group we want to draw conclusions about. The yellow oval is the sampled population. Notice the sampled population does not have to be a subset of the target population. It hopefully is. In fact, it hopefully is the target population itself, but it doesn't have to be. But note that the sample does have to be a subset of the sampled population. Sample doesn't have to be a subset of the target population. Again, we hope it does. In fact, we hope that the sample is representative of the target population. But from the way that the data are collected, it's not required. Strongly suggested, hoped for, that's the goal, but it doesn't have to be. So let's summarize the differences between a population and a sample. Population is about the whole group. It's a group we want to know about. Characteristics of a population are called parameters. These parameters in reality are unknown. We're trying to estimate those parameters. Those parameters are fixed. They are about the entire population. Contrast that with the sample, where the sample is part of the group. It's a group we know everything about because we've got it right in front of us. We can measure anything we want in that group. There's no mysteries whatsoever. Characteristics of the sample are called statistics. Those statistics are always known because we can just measure it on this sample that we have in front of us. And the statistics change with the sample. A little bit ahead of the place on that. Example 1.1. Identifying population and sample. So please identify the population and the sample. I will read through it, both A and B. I will expect you to hit pause, and then I'll give you the answers. We've got to identify the population and the sample. So in this survey, 359 college students at the University of Jackson were asked if they had tried the October flavor of the month at the campus coffee shop. 83 of the students surveyed said yes. I'm going to now give the answer to that. Go ahead and hit pause. The population is going to be the University of Jackson students, or the college students at the University of Jackson, because that's the group we're trying to draw a conclusion about. The sample is going to be those 359 college students we actually contacted. A survey of 1125 households in the United States found that 24% subscribed to satellite radio. Identify the population and the sample. Hit pause. The population is going to be all households in the United States. All. And the sample is going to be that 1125 that we actually contacted. Those are the solutions. Move on to example 1.2. Identifying the population, the sample, the parameters, the statistics, etc. For each of the following reports, identify the population, the target population in each of these cases, the sample, and whether or not the highlighted value is a parameter or a statistic. So population, sample, and whether it's a parameter or statistic. So here we go. Numero 1. After an airline security scare on Christmas Day 2009, the Gallup organization interviewed 542 American air travelers about the increased security measures at airports. The report stated that 78%, that must be the highlighted part, of American air travelers are in favor of the United States airports using full body scan imaging on airline passengers. Population, the target population, the sample, and what does that pink, purple, whatever color it is, highlighted number actually indicate. Go ahead and hit pause. The population here is all Americans, because we are all American air travelers, if you wish, because we're trying to draw conclusions about American air travelers in the United States. 2, what is the sample? It's those 542 people, American air travelers, that the Gallup organization contacted. And this 78% is going to be the statistic because it was measured off of that sample. 2. Rasmussen Reports also conducted a survey in response to the airport security scare on Christmas Day 2009. The National Telephone Survey of 1,000 adult Americans found that 59% of Americans surveyed favor racial profiling as a means of determining which passengers to search at airport security checkpoints. Remember, target population, sample, and what does that 59% represent? Go ahead and hit pause. The population is going to be all Americans. because we're trying to draw conclusions about the Americans. 2, the sample is going to be those 1,000 adult Americans contacted. And that 59% again is going to be a sample statistic. It's 59% of those 1,000 people. Two branches of statistics. The branch of statistics called descriptive statistics is a science that gathers, sorts, summarizes, displays the data. It doesn't try to draw conclusions about the data, it just tries to better understand the data itself. And the first 4, 5, 6, 7 chapters of this book are going to cover descriptive statistics. Inferential statistics, as a science, involves using these descriptive statistics to estimate population parameters. And that'll be the last half of the course. So inferential statistics takes our sample and tries to draw conclusions about the population. Descriptive statistics, on the other hand, just takes our sample and learns about our sample. Which brings us to our next question. What is the difference between descriptive and inferential statistics? Remember, you can hit pause. There are two types of analyses. One is called exploratory and one is called confirmatory. Exploratory analysis uses data to estimate parameters. This will be akin to the confidence intervals in the second half of the course. Confirmatory analysis uses statistics to test stated claims about reality. And these stated claims about reality we're going to call hypotheses. And this will relate to the hypothesis testing or the p-values of the second half of the course. So example 1.3, identifying descriptive and inferential statistics in a news report on the state of the media by Tom Rosenthal and Amy Mitchell. They write the following. AOL had 900 journalists, 500 of them at its local patch news operation. By the end of 2011, Bloomberg expects to have 150 journalists and analysts for its new Washington operation, Bloomberg Government. So let's identify the descriptive and the inferential statistics used in this excerpt. Again, remember, hit the pause to answer that, and then just go ahead and listen to me talk. And talk and talk and talk. Descriptive. So the first descriptive is AOL had 900 journalists, so we're describing how many journalists AOL had, and we're describing 500 of them at its local news operation. So those are descriptive. The future, by the end of 2011, Bloomberg expects to have, so expects to have tells us this is a future event. It's going to expect to have 150 journalists, so that will be the inferential statistic. So descriptive is about data that we have, inferential is about the population, which also translates into things that are happening in the future. Oops, we got that solution, and that's the end of the slideshow, and that's the end of section 1.1. So expect these videos to look very similar to this. It's slideshow, me talking over it, giving you questions, me adding to the slideshows, maybe telling a joke or two. Didn't tell any jokes today, I'm sorry, but expect them in the future. So I hope this was helpful. If not, as always, please make sure you email me with any questions, or leave the questions in Moodle's discussion forum for questions for for Learning Module 1. That's it. Thank you very much. I appreciate it. Hello and welcome to section 1.2, data classifications. In this section, we're going to be looking at how to classify data. That is, how to determine what types of variable it is. It can be either classified as qualitative or quantitative. Qualitative is also called categorical. Quantitative is called numeric. It can be classified as discrete, continuous, or neither, I guess. The book loves to talk about the neither. We're going to look at discrete or continuous. And it also has nominal, ordinal, interval, or ratio. So by the end of this slideshow, you should be able to know what all of those terms mean, and you should be able to classify a variable or data as in each of those three ways. So let's begin. Qualitative data, also known as categorical data, consists of labels or descriptions of traits. So qualitative variable example would be eye color, hair color, favorite music, things like that, where you can, if you want, put a number to it, but it's not a meaningful number. Say my eye color is 1 doesn't tell you what my eye color is. Say my eye color is blue does tell you. Those are qualitative. Those are categorical data. Quantitative, on the other hand, also known as numeric, actually does have a number that does make fundamental sense to it. It's usually counts, measurements. I object to the book using the term measurement because counts are also measurements in their own way. Examples of quantitative data would be height, weight, age, gas mileage. We're talking about cars now. Those would be quantitative because there are numbers associated with them, and those numbers are inherently meaningful. So here's a graphic. We got the qualitative side. We've got the quantitative side. Again, qualitative is categorical. Quantitative is numeric. Qualitative data are descriptions and labels, whereas quantitative tends to be counts and measurements, or measurements in general. Yeah. So here's an example. Classifying data as qualitative or quantitative. Classify the following data as either qualitative or quantitative. What are you assuming about the described variables? So A, shades of red paint in a home improvement store. Is that qualitative or quantitative? Hit pause. That is qualitative, probably. It depends on how you're actually measuring the shades of red paint. If you're doing it in terms of the names, such as fire engine red, apple red, baby red, I don't know what colors red paint are, I just see red, then those would be qualitative. But if you're doing it in terms of the percent of the paint that is red, that is, or how many squirts of red dye you have to put in the paint to get that, then it would be quantitative, because it's the number of squirts of red in the paint. Interesting. So the answer depends on what you're trying to actually measure. B, rankings of the most popular paint colors for the season. Again, think about whether this is qualitative or quantitative and what you're assuming, and go ahead and hit pause. The rankings are counts. There's numbers 1 through however many paint colors there are, so this is going to be quantitative. I don't think that there's much you're assuming about it unless you're thinking, hey, what if we're talking about rankings in terms of loved versus hated? Well, in that case, that's qualitative. But if you're looking at maybe number of stars, that would be quantitative. If you're looking at number of people who purchased it, that would be quantitative. Again, it's how are you actually measuring this ranking? So these questions actually are kind of difficult. C, amount of red primary dye necessary to make 1 gallon of each shade of red paint. Qualitative or quantitative, hit pause. This is quantitative because it's an amount of. I don't think I can think of any way of interpreting this to make it a qualitative because it's very clearly an amount of red primary dye. Okay, so that's going to be quantitative. D, number of paint choices available at several stores. Again, qualitative or quantitative, hit pause. You're right, I hope. That's quantitative because you're looking at the words number of paint choices. I suppose you could make this qualitative by saying a lot of paint choices, not so many paint choices, almost no paint choices. That would be a qualitative way of measuring this, but it's pretty explicit with the numbers of, so that would be quantitative. Okay. That's not what I wanted to switch over to. That's what I wanted to switch over to. Intra-lecture question number 1. Again, this goes in your Moodle quiz. Is the variable number of toes a qualitative or a quantitative variable? And again, I recommend you write the question in your notes on the left-hand side, your answer below it, so that you can go to Moodle after this lecture and put the answers in. Is the variable number of toes a qualitative or a quantitative numeric variable? And back to the lecture. Now we're looking at continuous versus discrete data. Discrete data are quantitative data that can take on only particular values, and those values are usually counts, but they don't have to be counts. They could be ratios of two counts. I mean, hey, that would also give you discrete data. Continuous data are quantitative data that can take on any value in a given interval and are usually called measurements. Again, I personally don't like the term measurement because any measurement for a statistician is something that you measure. So eye color would be a measurement for me because I have to measure eye color. But the way that the book wants to frame this, measurements would be things that you have on a scale, like a ruler scale. Continuous versus discrete. So discrete are counts or ratios of counts. Continuous data takes on any value in a given interval. So again, we've got the qualitative and the quantitative ovals. Quantitative can be broken down to discrete, which is usually counts or ratios of counts, and then continuous, which are usually measurements. Notice discrete and continuous don't speak at all towards qualitative because qualitative data is neither discrete nor continuous. Here's another example. Determine whether the following data are continuous or discrete. Temperatures in Fahrenheit of cities in South Carolina. Is this continuous or discrete? Hit the pause button now. Welcome back. Assuming you hit the pause button now, temperatures in Fahrenheit are going to be continuous. What's reported on TV will be discrete, but the actual temperatures will be continuous. B, number of houses in various neighborhoods in a city, continuous or discrete. Hit pause now. Welcome back. Numbers of houses tells me it's going to be discrete. The key word there is numbers. You're counting how many houses are in a various neighborhood. C, numbers of elliptical machines in every YMCA in your state. Numbers of elliptical machines in every YMCA in your state. Is that continuous or discrete? Hit the pause button. You're absolutely correct. That also is discrete. It's got the word numbers of. D, heights of doors, continuous or discrete. Oh, hit the pause button. Welcome back. Whatever I'm supposed to say. That's continuous. Heights are continuous. In the words of the book, it's a measurement. Realize that the actual height of the door is going to be continuous. The variable called heights of doors is continuous. What you actually write down as the height of the door is going to be discrete, because eventually you're going to have to stop writing down digits. And that gets back to something interesting, the difference between the variable and the data. The variable is what you're measuring. The data is essentially what you're writing down for those measurements. The variables are what you're measuring, such as temperature, such as height, such as age. And the data is what you're actually writing down, such as 97.8 degrees, such as 6'5", such as, I forget what the other example was. But those are things that are written down. Variables can be discrete or continuous. What you write down has to be discrete, because you have to stop writing at some point. Which brings us to the next intra-election question. Is the variable grade point average discrete or continuous? Again, I recommend you write the question over on the left side of your notes. Write down your answer right after it. Think about it. Go back over the last 5-10 minutes of this lecture so that you're absolutely certain what the difference between continuous and discrete is. Hit pause, fast forward, rewind as you need. You've got total control over this lecture except for what I say. I mean, you could even slow this down so I sound like this. Or speed it up. Sorry, that's not like this. Levels of measurement. 4 levels of measurement: nominal, ordinal, interval, ratio. If you learned French, you can think of this in terms of NOIR, black. NOIR, nominal, ordinal, interval, ratio. That may help you remember the 4 levels. The level of measurement of a variable describes the amount of information that that variable contains. The 4 levels are nominal, ordinal, interval, and ratio. Nominal, the values are just descriptions. Ordinal, which is short for ordered nominal, you've got the description plus you've got an inherent ordering to it. Interval level, the differences between levels are identical, so you can subtract. And ratio level, not only do you have differences between 2 levels being the same, but you've also got the value of 0, meaning an absence of. So data at the nominal level of measurement are qualitative, consisting of labels or names. So the variable eye color will be nominal level, because what are the eye colors? Blue, brown, green, hazel, and I'm sure I'm missing some colors. Blue, brown, green, hazel. Yeah, I could also order them as brown, blue, green, hazel. It would mean the same thing. They're just names attached. So it's nominal. The word nominal comes from the Latin nominus, meaning name. Suppose all students in a stats class were asked what pizza topping is their favorite. Explain why these data are at the nominal level of measurement. Piece of cake. Favorite pizza topping is, I don't know, pineapple, pepperoni, sausage, olives. I can't think of it anymore because I only use pepperoni and pineapple. Those are just names. I mean, it doesn't matter that they're the individual person's favorite. I'm asking everybody for one pizza topping. I can call it pineapple. I can call it pineapple apple pine. It means the same thing. B, suppose instead that you wish to know that the number of students whose favorite pizza topping is sausage, the number of students, explain why this data value is not nominal. Well, it's the number of, so you're measuring the number of students, counting the number of students. Nominal has to be categorical. If you're counting things, that's numeric, so it can't be nominal. Data at the ordinal level of measurement are qualitative data that can be arranged in a meaningful order, but calculations such as addition or division do not make sense. So we've got some examples of nominal data, eye color, hair color, but we can also look at some examples of ordinal data, such as, I'm having trouble coming up with one off the top of my head. Well, let's think through this. It's got to be categorical, and they've got to be in some sort of inherent meaningful order. Categorical, but some inherent meaningful order to it. How about socioeconomic status? It's categorical, low, medium, high, but there is an inherent meaningful order to it. Low, medium, high. The fact that you could also do it high, medium, low is irrelevant. You've got an ordering to it. So socioeconomic status would be an ordinal level variable. Notice ordinal level variables have additional information to them that nominal level variables don't have. That is, position. I can say high SES is larger or greater than low SES. I can't say blue eyes are larger or greater than brown eyes. Doesn't make sense. Example. Determine whether the data are nominal or ordinal. Seat numbers on your concert tickets such as A23 and A24. Go ahead and hit pause while you think about it. I believe the answer to this will be it's ordinal, although I haven't been to a concert since the 80s. I believe the A would be the row and 23 would be the seat numbers. So seat number 23 is one seat closer to the aisle than seat number A24. Since it is closer to the aisle, since we do have some sort of ordering to it, we've got an ordinal variable. Genres of music performed at the 2013 Grammys, that would be nominal, because it'd be, I assume country and rock and jazz and doo-wop are all done at the Grammys, I assume. And there's no inherent ordering to that. I could do it alphabetical order. It would have just as much meaning as doing it in terms of the order that I just gave you. So A is ordinal, B is nominal. Data at the interval level of measurement are quantitative data that can be arranged in a meaningful order and such that differences between data entries are meaningful. Difference between levels are meaningful. Such as shoe sizes. The difference between a 5 and a 6 in shoe size is exactly the same as the difference between an 8 and a 9 in shoe size. They both differ by 1 shoe size, but also by 1.3 inches, I think. Temperature in degrees Fahrenheit is interval, because going from 45 to 46 degrees is exactly the same as going from 95 to 96 degrees. It's an increase of 1 degree Fahrenheit. Probably should say it's measured in degrees Fahrenheit. Birth years of your classmates are collected. What level of measurement are these data? Well, clearly it's going to be interval. Birth years, 2000, I don't know what birth years you guys have, 2001, 2002, that differs by 1 year, just like 1997 and 1998 differ by 1 year. The key for interval level data is that subtraction, and by extension addition, actually makes sense. And then the last level of measurement, the one that has the most information in it, is called the ratio level. It's quantitative data. It can be ordered. It's interval. And the 0 point indicates the lack of something. So compare the year of your birth, which we decided was interval from the last, with your age, which is ratio. Year of the birth, well, a 0 year of birth doesn't indicate a lack of anything, just indicates it was 2,000 some odd years ago. But an age of 0 would indicate you lack age. Now note that you don't have to be able to achieve a 0. All that it means is that a value of 0 would indicate an absence or a lack of something. So the height of a person would also be ratio, because a height of 0 would indicate a lack of height. You can't achieve a height of 0, but if it were achievable, it would indicate you lack height. Weight would be another example of a ratio level variable. You can't achieve 0 weight, but a 0 weight would indicate a lack of weight. Now it's called ratio level because ratios actually do mean something. So comparing a person of age 10 to a person of age 20, that ratio actually does mean something. The second person is twice as old as the first. A 4-foot person versus an 8-foot person, the ratio of 2 actually does mean that the 8-foot person is twice as tall as the 4-foot person. Compare that with your age of birth, no, just your year of birth, sorry. 1995 versus 2000, that doesn't indicate that your year of birth is 0.5% higher. It's just you're 5 years later, which is interval. So the word ratio comes from the fact that ratios, divisions, actually make sense. So, example, consider the ages in whole years of U.S. presidents when they were inaugurated. What level of measurement are these data? Clearly, they're going to be ratio because it's in this section. But why are they? Because it's ages in whole years. An age of 0 would indicate a lack of age. It doesn't mean you can achieve an age of 0. It just means that if 0 is in the age column in your spreadsheet, you lack age. So here are the nice little stair step. You got qualitative, quantitative. Qualitative includes nominal and ordinal. Nominal means names. Ordinal means ordered nominal. Quantitative is interval and ratio. In interval, 0 is just a placeholder, such as 0 degrees Fahrenheit. If 0 degrees Fahrenheit doesn't indicate a lack of temperature, whereas in ratio, 0 does mean the absence of something. So 0 Kelvin would be a ratio level variable. But measuring temperature in Kelvin would be ratio level, but measuring degrees in Fahrenheit would just be interval level. Because a 0 Fahrenheit just means it's cold, not that it lacks temperature. 0 Kelvin means it actually lacks temperature. Here's the third one. Give an example of a ratio level variable not provided in the slides or the text. Again, I would write this off on the left, write the answer beneath it, so you can go into Moodle and answer the questions. And pause, of course, if you need to. So, final example, classifying data. Let's classify these as qualitative or quantitative, discrete or continuous, or neither, and the level of measurement, nominal, ordinal, interval, ratio. Finishing times for runners in the Labor Day 10K. Colors contained in a box of crayons. Boiling points on Celsius scale for various caramel candies. And the top 10 spring break destinations as ranked by MTV. Go ahead and hit pause before I give you the answers. The answer for A, finishing times for runners, will be a ratio level. It will be continuous, and it will be quantitative. Colors contained in a box of crayons will be qualitative. It will be neither, because qualitative is neither discrete nor continuous. And it will be nominal. Note that number of colors would be different, but we're looking at just the colors themselves. Boiling points on Celsius, that's going to be quantitative, continuous, and interval, because 0 Celsius does not indicate a lack of temperature. And finally, D, top 10 spring break destinations as ranked by MTV. Notice these are the destinations themselves, so it's going to be categorical or qualitative, and hence neither discrete nor continuous. Level of measurement is going to be ordinal. And that's it for section 1-2. Again, don't hesitate to send me comments, questions, and post them in Moodle for the discussion section. Thank you much. Hello, welcome to section 1.3, the process of a statistical study. The objectives for this section are to describe the process of a statistical study. That's probably rather clear. Identify the various types of studies, but most importantly, to understand the primary sampling schemes. And it's this understanding the primary sampling schemes that is key for this section. If all you take out of this section is those sampling schemes and an understanding of them, you're doing great. So here's the process of a statistical study. Notice that there are 4 steps. Step 1 is to determine the design of the study. There are classes taught in experimental design, by the way. But you need to state the question to be studied, determine the target population and the variables, and then determine the sampling method you're going to use. It's 1C. It's a subset of 1, but it's probably the most important thing here. Because remember, your sample must be representative of your target population. Otherwise, all the statistical methods in the world are useless. Your sample must be representative. So we need to study how to draw a representative sample. 2, you're going to collect the data according to that sampling method. 3, you're going to organize the data. And 4, you're going to analyze the data. 4 is going to be the second half of the class. 3 is going to be most of the rest of the first half of the class. So, example 111. Neurologists want to study the effect of vitamin C on nerve disorders. The goal of the study is to see if taking an intravenous dose of vitamin C will reduce the amount of nerve pain reported by patients. So identify the population of interest and the variables in the study. Again, pause, and welcome back. The population of interest is all. Notice all populations of interest have the word all in there somewhere. All patients, period. And the variables in the study will be, all patients with nerve disorders. And the variables in the study will be the amount of vitamin C and amount of nerve pain. Those are the obvious ones. Perhaps others will need to be taken eventually to take care of some intervening issues. Observational study versus an experiment. An observational study observes the data that already exist. So the statistician will sit there and just collect data, won't try to influence the outcome of anything, whereas an experiment generates data to help identify the cause and effect relationships. Yeah, the book emphasizes that it's cause and effect. It's easier to do cause and effect analysis when you've got an experiment, but observational studies can hint at that as well. Know that these are the proper definitions as used by scientists. A statistician will refer to any, quote, theoretical data collection as an experiment. This difference in terminology comes from the fact that statisticians experiment to better understand their field of study. Just like biologists experiment to better understand biology, and physicists experiment to better understand physics, statisticians experiment to better understand statistics. So here's an example. Which type of study would you conduct? Observational or experiment? A, you want to determine the average age of college students across the nation. B, researcher wishes to determine if flu shots actually help prevent severe cases of the flu. Go ahead and hit pause. The first one's an observational study, the second is an experiment. Notice in the second one, you're actually trying to determine if the flu shots do something. Whereas in the first one, you're just observing ages of students across the nation. A representative sample has the same relevant characteristics as the population and does not favor one group from the population over another. Note that a sample could be representative for one characteristic of the population, but not for another. So here's an interesting question. How do you know if a sample is representative of the population? That we're going to come back to time and time and time again, because it's such an important question. Remember, all of statistics is based on that sample you draw, and that sample has to be representative of the population. So how do you know if your sample actually is representative of the population? We got a red star at the bottom, so let's move on to the first intra-lecture question. Question 1. My sample is all females in this class. Is it a representative sample? Remember, hit pause, write the question over on the left side. You probably should listen to what I'm saying before you hit pause. Write the question on the left side of your notes, write the answer down below it so you can put it into your middle quiz, and then hit pause. And I really do want to come back to this. How do we know if a sample is representative of the population? Maybe you should write that on the left-hand side as well and start coming up with answers to that question, because we're going to be seeing it several times in this course. Here's 5 sampling techniques. Simple random sampling. Notice the book also has something called random sampling. We're going to conflate that with simple random sampling. Second type is stratified, then clustered, then systematic, and then convenience. Never ever use convenient sampling except when I give you permission to in class, but we're not in class, so. Simple random sample. Every sample from the population has an equal chance of being selected. Keyword there is actually 2 keywords. It's sample and equal chance. So if I want to draw a sample of size 50 from everybody in the United States, and I want to use simple random sampling, that means that every possible combination of 50 people in the United States has an equal chance of being selected. Every possible combination of 50 people has an equal chance of being selected. Or we can bring it down to the class level. Let's say our class is size 30. So our population is size 30, and I want a sample from this population, a sample of size 5. Simple random sampling would require that every possible combination of 5 people in this class would have an equal chance of being selected. Stratified sampling. Population is divided into subgroups called strata. the grouping variable is correlated with the measurement variable, and a sample is drawn from each stratum. So in this example, if I want to estimate the average GPA at Knox, I probably would break it up into freshmen, sophomore, junior, seniors, estimate the GPA in the freshmen, estimate the GPA in the sophomores, estimate the GPA in the juniors, estimate the GPA in the seniors, and combine them together to get the estimated average. And the reason I'd probably break it up into freshmen, sophomore, junior, senior is because GPA does seem to correlate with class. Contrast that with cluster sampling. Population is divided into subgroups called clusters, not strata, clusters. The grouping variable is not correlated with the measurement variable, and a sample is drawn from at least one of the clusters. So if we're going to go back and I want to determine the typical hair color at Knox, breaking it up into freshman, sophomore, junior, senior would not be useful in terms of stratified sampling, but it would be useful in terms of cluster sampling, because I highly doubt that level in school and hair color is correlated. In this example, we've got a humongous rice field. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. There's 21 subplots there. I randomly select 4 of those subplots and estimate the amount of rice in each of them. Each of those subplots seems to be rather representative of the population as a whole. Systematic sampling. Every nth member of the population is selected. So if I want to select 25% of the population, I would select every 4th bottle, in this example here. If I want to select every 10% of the population, I'll select every 10th bottle. If I want to get 1% of the population, I'll select every 100th bottle. But again, it's systematic because it's selecting every nth member of the population as it comes down the conveyor belt or through the door. Convenient sampling. It's just convenient for the researchers to select. People will self-select into the poll, perhaps. It's very unethical to use. All of the web polls that you see on newspaper sites that say, hey, how would you vote in this case? Those are all convenient sampling, and they are highly unethical because it is trying to give information to the reader, and that information is about the population of interest, but you're drawing a sample from a very skewed population or a very biased population itself. So here's some examples. A pollster surveys 50 people in each of the senator's 12 voting precincts. So this sounds like stratified. Senators' 12 voting precincts, so the voting precinct is the stratum. There's 12 of them surveying 50 from each. I would assume that voting precincts are internally more consistent than the population as a whole because like-minded people tend to live near each other. The quality control department at a cereal manufacturer measures the weight of every 10th box, so this will be systematic. A female student walks down the halls in her dorm asking students how much money they'd spend from the food court. This is convenience. An educator chooses 5 of the school districts in the Chicago area and asks each household in those districts how many school-age children are in the district. This would be cluster. Probably. The book says this is cluster. This may actually be stratified because a school district, the distribution of school-age children may not be the same across the school districts. One school district may have a higher proportion of children in each household than another school district. If that's the case, then this would be stratified. To determine who will win a $100,000 shopping spree at a mall, manager draws the name out of a box of entries. This will be simple random sampling. Technically, this will be random sampling, but we're conflating the two, remember, so it's simple random sampling. There's the red box. Let's move on to question 2. This is a key one. Very, very important. What is the primary difference between cluster sampling and stratified sampling? Remember, hit pause if you need to. Again, write the question on the left-hand side of your notebook and your answer underneath of it. Two types of observational studies is the cross-sectional study and the longitudinal study. Cross-sectional study, data collected at a single point in time on a lot of members, whereas in a longitudinal study, it's over time on a few members. A group of 220 patients is followed for 15 years in order to determine okay, right there, I know this is going to be longitudinal because it's over time for a small group of members. B, a gastroenterologist surveys 130 of his patients 6 months after. Okay, this is going to be cross-sectional because it's done at a single point in time, 6 months after having the gastric bypass. If the gastroenterologist surveyed those 130 people 6 months, 1 year, 18 months, 2 years, 3 years, 4 years, 5 years, then that would be a longitudinal study. Some more terminology. Treatment is some condition that is applied to a group of subjects in an experiment. The subjects or the participants are the people or things being studied in an experiment. The response variable is the variable in an experiment that responds to the treatment. We'll also refer to this as the dependent variable. The explanatory variable is the variable in an experiment that causes the change, or it explains why that change took place. We're going to refer to this as an independent variable. There's another set of variables that are called independent. Oops. It's not the next slide, I guess, called control variables. Control variables are variables that we know affect the dependent variable, but we really don't care about them in terms of our research. So independent variables are broken up into explanatory variables or research variables, and then those control variables. So here are 3 principles of experimental design. 1, you got to randomize the control and treatment groups, because the goal is the only difference you want between the control and the treatment group is to be the treatment. So you got to randomly put people into, you don't have to, you should randomly put people into the 2 groups, control and treatment, and then apply the treatment to the treatment group. Control for outside effects on the response variable, those would be the control variables. Replicate the experiment a significant number of times to see meaningful patterns, and I do want to emphasize here the word replicate. Remember back earlier we asked how do we know if our sample is actually representative? The answer is we don't. We have to replicate our studies over and over and over again. And then the hope is that we don't make the same mistakes and get an unrepresentative sample in each of those replications. Okay, control group versus treatment group. Control group is the group of subjects which no treatment's given, whereas the treatment group gets the treatment. And again, the structure of the experiment has to be such that the only meaningful difference between the control group and the treatment group is the treatment. And hence the importance of the randomization. Confounding variables are unmeasured factors other than the treatment variable that cause an effect on the subjects. To get rid of confounding variables, you measure them, add them to the model. And there's a red star. So let's go back and see. Question 3. How do we know if there are confounding variables in a statistical study? Move those over, write that over on the left-hand side of your notes. Put the answer there so that you can answer the quiz in Moodle. How do we know if there are confounding variables in missing an S, in a statistical study? A placebo is a substance that appears identical to the actual treatment but contains no intrinsic beneficial elements. Placebos are used to ensure that the only difference between the control and the treatment group is the treatment itself. Placebos will be given to the control group, so the control group doesn't know that they're in the control group. The placebo effect is a response to the power of suggestion rather than to treatment itself. That's why we have to give a placebo to the control group, because the very act of receiving medicine will affect you. Hence, we don't know if the treatment actually improves the people or just them thinking they received treatment. So we got to give placebos to the control group and the actual treatment to the treatment group. So they all think, hey, I received something. So the placebo effect is going to be constant for the entire group. And again, remember, the emphasis here, the only allowable difference, meaningful difference, between the control group and the treatment group is that the treatment group receives the treatment. In a single blind experiment, the experimenter pokes out one person's eyes. Oh wait, no, that's not what it is. Subjects do not know that they are in the control group or the treatment group. Whereas in a double-blind experiment, both the subject and the measurer doesn't know. The measurer is the person who measures the temperature of the patient, measures whether or not the patient improved, measures if the patient's foot fell off, whatever the treatment is supposed to fix. The researcher, a good researcher, will remove him or herself completely from this once the experiment is set up and is in motion. A researcher will just take the data that is collected and analyze it, because the researcher needs to know everything. But in a double-blind experiment, it's the subject and the person doing the measuring who don't know. So subject, person doing the measuring, and researcher, 3 different people in the experiment. 3 different roles in the experiment. Sometimes the subject and the measurer are the same person. So here's a lengthy example. Consider the study from example 111, in which a neurologist wanted to determine if taking the IV dose of vitamin C will reduce the amount of nerve pain reported by patients. Suppose that the study was narrowed to focus only on patients with the nerve disorder multiple sclerosis. After study approval, the neurologists solicit volunteers who are patients with MS and who are reporting nerve pain. So target population 1, I guess, is all patients. Smaller target population is patients with multiple sclerosis. Sampled population, patients with multiple sclerosis who have nerve pain. Sampled population is the people in our, after study approval, the people in the study that I can pull from. This doesn't specify what the sampled population is. The sample is the actual 40 participants, 20 in the control group and 20 in the treatment group. Group A is the treatment group. They're given the IV doses of vitamin C. So the subjects are getting the doses. Somebody is measuring the nerve pain. Participants in group B are the control group. They're given an IV dose of saline, which is the placebo, and somebody's measuring it. The participants don't know which group they're in, and the people measuring should not know which group they're in. Oh, should not. However, the nurses administering the IVs are aware of the group assignments. That's not necessarily a bad thing as long as the nurses are not measuring the nerve pain. After a predetermined length of time, the amounts of pain reported by the separate groups are compared to determine if the IV dose reduces the amount of nerve pain. Interesting. Explanatory and response variables. Treatment. Which group is the treatment? Which is the control group? What's the purpose of administering saline to group B? Is it single blind or double blind? Hit pause. Welcome back. Explanatory and response. Response variable is going to be the amount of nerve pain. The explanatory is the vitamin C the vitamin C IV drip. The treatment is the IV of vitamin C. Which group is the treatment group and which is the control group? The treatment group is the one that receives the vitamin C. The control group is the one that receives the saline. What is the purpose of administrating saline to group B? It's to control for the placebo effect. Remember, group A and group B have to be exactly the same except that group A receives the treatment. So giving the IV also makes the groups more similar. Is this a single blind or a double blind study? It depends. If the nurses are measuring the pain, it's single blind. If somebody else is measuring the pain that doesn't know who is in which group, then it's double blind. Last page. IRB is a group of people who review the design of a study to make sure that it is appropriate and that no unnecessary harm will come to the subjects involved. Knox College has an institutional review board. It meets infrequently to handle student and faculty research plans or research designs. Informed consent involves completely disclosing to the participants the goals and procedures involved in a study and obtaining their agreement to participate. There is a lot of question out there whether informed consent is ethical, whether it's even possible in some cases. In all cases where it's reasonable, informed consent should be obtained. Now the question comes down to, when is it not reasonable? And it's not reasonable when the purpose of the experiment is given away by telling the participants the goals and procedures. Because remember, the placebo and the placebo effect, if you know the outcome of an experiment, or if you know what the researcher is looking for in the experiment, there's a much higher probability the researchers are going to find it. So unfortunately, informed consent in those cases could actually destroy the experiment, which means, well, is informed consent ethical in those cases? I don't know. It's a big question. Things to think about. But that brings us to the end of this section. That's the end of this chapter, however. I encourage you to go through section 1.4, but I won't be lecturing through it. It's important stuff. We just have more important things to cover. So thank you much. Hello and welcome to section 2.1. We're going to be creating frequency distributions today. It's unclear at this point why you're creating frequency distributions. Tomorrow, or in the next lecture, you're going to see how we use these frequency distributions to help create graphics that tell the story of the data. We're going to look at how to create ungrouped frequency distribution and create a grouped frequency distribution. The ungrouped is going to lead to charts such as a pie chart and a bar chart, whereas the grouped is going to lead to such things as a histogram or a stem and leaf plot. So today is the foundations, and the next lecture will be for what we're actually going to be using this for. Throughout this lecture, I'm going to point out some things such as, wow, this is a lot of work for not that much. And I want you to take that seriously and think, okay, a lot of work, we're not getting too much out of it. Is there a way of making this easier? And of course, the answer is yes. So, frequency distributions. A distribution is a way to describe the structure of a particular data set or population. We're going to look at sample distributions now. When we get to chapter 5 and 6, we'll be looking at population distributions. So keep this in mind. In fact, on the left-hand side of your notes, put a little star, write C chapter 5 and 6, and another star, just to draw your attention to it that this is the start of looking at distributions. Here for the sample, later for the population. A frequency distribution is a display or a table of the values that occur in a data set and how often each value or range of values occurs. So it's how often, that's where the frequency comes in. Frequencies, which is a little f, are the number of data values in that category, if we're talking about categorical data, or range of values if we're talking about numeric data. In a class, We're going to call that as a category of data in a frequency distribution. For categorical variables, that class most often is going to be one of the levels in the variable. For numeric data, it's going to be some range of possible values for the data. An ordered array is an ordered list of the data from largest to smallest or smallest to largest. Probability distribution is a theoretical distribution used to predict the probabilities of particular data values occurring in a population. Probability distribution, if all we're going to talk about is probability distribution, is going to be about the population. If we're talking about the distribution of our sample, we'll call it a sample distribution. An ungrouped frequency distribution is a frequency distribution where each category or class represents a single value or level in the variable. These are used for categorical variables. Whereas a grouped frequency distribution is a frequency distribution where the classes are ranges of possible values. These will most likely be used in numeric data. The ungrouped frequency distribution will lead to bar charts and pie charts in the future, whereas a grouped frequency distribution will lead to histograms in the future. So here's the steps in constructing a frequency distribution for ungrouped, for categorical data. So to create an ungrouped frequency distribution to determine the levels of the categorical variable, and I do want to emphasize that you would use this only for categorical variables, and count the number of observed values in each level. Okay, remember, a level is a possible outcome of a categorical variable. Example, the eye color of my research students in this term are as follows: blue, brown, brown, blue, brown, 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 green. So the blue, brown, brown, blue, brown, 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 green is the raw data. The observations, the measurements I make of my students' eye colors. Blue is the eye color of my first research student, brown is the eye color of my second research student, etc. The frequency distribution just looks at all the possible levels that we observe, blue, brown, and green, and then counts the number of observed values in each of those levels. I got 1 blue, 2 blue, only 2. Brown, I got 1, 2, 3, 4, 5. Green, I got just 1. So the frequency distribution is 2, 5, 1 for blue, brown, green. Ooh, red star. I think that's what I want to do. So question 1. Again, I encourage you to write these questions and your answers in your notes on the left-hand side. What is the difference between a grouped and an ungrouped frequency distribution? Pause. And we're back. So that was all about the ungrouped, or for the categorical variables. Now we're going to look at grouped, which is almost always applied to numeric variables. Remember, the main difference between the ungrouped and the grouped is that the ungrouped, each row in the table corresponds to one level in the variable, whereas for the grouped, each row is going to correspond to a range of values of that variable. So the first step in creating this grouped frequency distribution is decide how many classes should be in the distribution. Now we've got rules of thumb. None of them are good because they're rules of thumb. The reality is you should choose many different numbers of classes. So the first time through you should choose 5 and then maybe 10 and see what the information given by these distributions, how that changes. Maybe 20. But you're going to realize that if we do 5, 10, 20, 12, and 18, we got to do these steps 5 times. And that takes a lot of effort to do just one. So you're going to fall in love with the computer because the computer can do it just like that. I don't know if you could hear me snapping my fingers, but I'm snapping my fingers. So the first step is to decide how many classes should be in the distribution. Once you've decided that, 2, choose an appropriate class width. Class width is usually going to be the highest value minus the lowest value divided by the number of groups. Sometimes you'll round down to something logical for the lowest value, round up to something logical for the upper value. and then divide by the number of classes. Sometimes you'll skip 1, go directly to 2, and physically determine that class width, what the classes should be based on the problem itself, and we'll see that later. In those cases, easily lends itself to natural divisions, such as decades or years or hundreds of dollars. 3, find the class limits. The lower class limit, and this is for each of the classes, by the way, the lower class limit is the smallest number that can belong to that class. And the upper class limit is the largest number that can belong to that class. So all the values in that class are greater than the lower class limit and lower than the upper class limit. And now you just count the frequency of each class. 4 is the easy part, by the way. You just determine the frequency. You count how many are in each of those classes. So here's some terminology. Class width is the difference between the lower limit and the upper limit of 2 consecutive classes. Lower is the smallest number that can belong to that class. Upper class limit's the largest that can belong to that class. Here's the example. Here are 20 television prices, 3D TVs. The first 3D TV price is $1,595. The second one was $1,599 and $1,685, etc., all the way up to $1999. Great song, but that has nothing to do with class limits. First step is determine the number of classes. If we follow these 3 steps, determine the number of classes. There's 20 data points. How many classes should we do? Or we could use the problem itself to hint what the classes themselves should be. These are TV prices. We got the lowest TV price here of $15.95, the highest of $19.99. These are in, looks like class width should probably be $100. That would make sense here. So we'd do maybe $1,400 to $1,500, $1,500 to $1,600, $1,600 to $1,700. That would make sense. Remember, the purpose of the graphics for you is so that you understand the distribution of the data. For your reader or your client, it's so that they understand the story that the data is telling. So to determine the class width, we were told 5, by the way. Use 5 classes, so maybe my idea doesn't quite work, or at least for this problem. I think it would work for reality. 5 classes. So 19. This is the highest value, the lowest value divided by 150. So about 81 would give us a class width. Okay, $81 class width. I guess if we're going to follow this without thinking, that would be a good thing to do. But if we actually want to think, $81 doesn't really seem reasonable in telling the story of the data. $100 would make sense, because there's something magical about round numbers. In fact, doubly round numbers. There's 2 roundnesses here, and there's none here. Oh, I guess the 8, if you turn it on its side, it's got 2 circles, but this, never mind. So $100 would make sense. Then we got to choose $100 width, so we got to set how low to how high. Beginning at 1500 makes sense. If we want to just follow the directions without thinking at all, 1595 would make sense as the first class starting point. 1500, if you actually want to present this to a client, would make much more sense. So 1600 will be the class limit of the second. 1700, 1800, 1900, 2000 will be all the classes, or the class boundaries, otherwise known as the breaks. Should not be overlap in the class boundaries, really, although in all reality it doesn't matter. So here are the 3D, they can abut, but they can't actually overlap. So now we've got our classes, 1500 to 1599, 1600 to 1699. And now we just calculate the frequencies. 25454. Notice that if you add up 2, 5, 4, 5, and 4, you should get 20, which is our sample size. Now we're going to define something called a class boundary. It is the value that lies halfway between the upper limit at one class and the lower limit at the next class. So the class boundary here would be 1599.50, 1699.50, 1799.50, 1899.50. Or 1599.5 if you want. And the purpose of the class boundaries is to make very clear that there is no overlap and that everything, no overlap, and that every possible value fits into one and only one of the classes. The midpoint is the upper limit plus the lower limit divided by 2. These midpoints are used for estimating the average value in each class. We'll see it in the next chapter in dealing with grouped data. Lower, upper divided by 2 gives us a class midpoint of 1549.5. Although I don't know a statistician alive that wouldn't say 1550 would be the midpoint. 1500 plus 1599 divided by 2 gives us this as the midpoint. 1600 plus 1699 divided by 2 gives us this as the midpoint. Those are for frequencies. If we want to do relative frequencies, we just divide the frequency by the sample size. So 2 divided by 20, 5 divided by 20, 4 divided by 20, 5 divided by 20, 4 divided by 20. Notice that adding up all the frequencies gives us the sample size, which we're always going to symbolize as a lowercase n. Lowercase f is the frequency. The subscript of the I is for class I. So f sub I is the frequency in the ith class. So this calculates the relative frequency. We first add up all the frequencies to determine the sample size. Now we just divide each of the class frequencies, the f sub i's, by 20. So the first relative frequency is going to be f sub 1 divided by 20. Second will be f sub 2 divided by 20. Then f sub 3 divided by 20, etc. Cumulative frequency is just the sum of the frequencies of a given class added to all lower classes. So if you are able to order your data, then you can do a cumulative frequency. If your data cannot be ordered, that is, if it's nominal, then you cannot do a cumulative frequency. It doesn't make sense to talk about less than or equal to if there's no ordering. So here we got the frequencies, and this last column is the cumulative frequency. So the cumulative frequency for the first one is always the frequency. Cumulative frequency for the second is going to be 5 plus 2, because it's whatever's here plus what's above. 4 plus 5 plus 2. 5 plus 4 plus 5 plus 2. 4 plus 5 plus 4 plus 5 plus 2. And notice the cumulative frequency always ends with our sample size, little n. Here's an example. Data collected on the numbers of miles that professors drive to work daily are listed below. Clearly not below, it's on the next slide. Use these data to create a frequency distribution that includes the class boundaries, midpoint, relative frequency, and cumulative frequency of each class. We're told we have to use 6 classes. So here's the data. The low is 1. The high is 11.9. We're told 6. So if we just follow the directions without thinking, we're going to come up with 1.8 as our class width. So we'll do class boundaries as being 1, 2.8, 4.6, 6.4, 8.2, 11, 12.9, whatever they are. I lost count already. I'm just adding 1.8. Where are we? I'm just adding 1.8 to each of those. Notice that it may make sense to do it class width of 2 instead of 1.8. 1, it's a lot easier to do in your head. 2, it makes a lot more sense in terms of presenting the data. So instead of 1.8, let's round this up to 2. So the boundaries will be 1, 3, 5, 7, 9, 11, 13. See? Much easier. And now the lower class limit is the limit of our first class. 1 is the lowest, so if we just want to follow this, we can start with a 1. I would say let's start with 0. That would kind of make sense. So it'd be 0, 2, 4, 6, 8, 10, 12. That would include all the data instead of 1, 3, 5, 7, 9, 11, 13, which would also include all the data. But maybe 0, 2, 4, 6, 8, etc. looks better to the client. However, we're going with 1. So 1, 3, 5, 7, 9, 11. 3, 5, 7, 9, 11, 13. So we're backing it off by 0.1. Now we do the frequencies. There's our midpoints. And again, don't know any statistician that would say the midpoint is 1.95. Every statistician I know would say the midpoint is 2, 4, 6, 8, 10, 12. And the class boundaries and the class would be 1 to 3, 3 to 4, 4 to 5, 3 to 5, 5 to 7, 7 to 9. But notice in each case you include the lower but not the upper. Frequency is 334242. We get that just by going back to the data itself and counting. Relative frequency is our frequency, so f sub 1 divided by our sample size of 18, f sub 2 divided by 18, f sub 3 divided by 18. Cumulative frequency is the frequency in this group plus all those lower. So it'll be 3, 6, 10, 12, 16, 18. And of course we could have a cumulative relative frequency, which would be just each of these divided by 18. So here's the overview again. Notice there's a lot of work to this if we do it by hand, and if we have a realistic data set. And a lot of decisions we have to make, and the distribution itself depends on those decisions. So we're going to want to do several of these, hopefully not by hand. So we got to decide on the number of classes, choose an appropriate class width, find the class limits, determine the frequency in each of the classes. That's a lot of work for one frequency distribution. And again, remember this is for grouped frequency distributions. Being able to automate this would make life so much easier. It would allow us to look at different, the effect of different choices we make. So instead of 5, we'd be able to figure out, well, what does the frequency distribution look like if we chose 10 classes? What if we chose 50 classes? What if we chose 2 classes? What would it look like? And what stories do each of those frequency distributions tell us about the data? Here are the other characteristics. We've got the classes, boundaries, midpoints, relative frequencies, and cumulative frequencies. And we got a red star. It's good because that's the last page. We got 2 questions. Question number 2. Again, put this over in your notebook. On the left-hand side, write the question and your answer below it so you can transfer that into Moodle's quiz. What are the steps in constructing an ungrouped frequency distribution? And then question number 3, what are the steps in constructing a grouped frequency distribution? And a hint, one of those two is going to be a lot easier than the other. And what I'm getting at in these two questions, don't hit pause yet. What I'm getting at in these two questions is you'll see that the grouped frequency distribution steps are exactly the same as the ungrouped, except for you have to add a few things in taking your numeric variable and making it categorical. Take your numeric variable and making it categorical. And that's what these classes are doing. You're taking your numeric variable and you're classifying them. You're making them categorical. And that's it. Section 2.2 takes what we did today and makes pictures out of it. Okay, makes graphics out of it. Plus we get to see a lot of different types of graphics. And we'll see how to do all of this really fast in R. So, hope this was helpful. Talk to you later. Hello and welcome to section 2.2, graphical displays of data. Recall in the last lecture that we looked at how to create frequency distributions, both ungrouped and grouped. Today, or in this lecture, we're going to look at turning those frequency distributions into graphics that tell the story of the data. And I do want to emphasize the purpose of graphics is to tell the story of the data. The graphics that we see today are going to tell the story of the data to you, mainly because they look pretty ugly. But we're going to see in some of the SCAs, the statistical computing activities, how to pretty up those graphics so that they tell the story in a pleasing way to your audience. Remember, the graphics serve two purposes that are really the same purpose. The basic graphics tell you the story of the data, and then the publication quality graphics tell your audience the story of the data that you learned. So we're going to look at those utilitarian ugly graphics today, and in SCA, I believe it's SCA2, we're going to see how to create nice looking graphics that can help convey that story to your reader. We're going to look at how to create some bar charts, pie chart before that, but bar charts, both univariate bar chart that is for one categorical variable, but also some bivariate stacked and side-by-side bar charts. We'll look at histogram and its neighbor stem and leaf plot, and then line graph. We're going to look at different shapes of the distributions. Remember, these graphics are going to tell us about the data. Here's some rules on what graphs or graphics should have. They should stand alone without the original data. That is, in your paper, you provide a graphic instead of providing all of the data. The graphics have to have labels and values for both axes. When appropriate, a legend, a source, and date should be included. The source and the date are usually in the caption, however. And in a paper, the graphic must contain a number and a caption. So the first figure that you include is going to be called figure 1, and then you're going to give it a caption, a brief description of what that graphic says. The graphic must also be described in the prose, in your writing in the paper itself. Ooh, red star. So let's go to our first question. What do all graphics need? And remember, you should write this over on the left-hand side of your notes, the question and your answer, and you should hit pause to remember to gain some time here, because I'm going to hop back to the lecture. So we'll start with pie charts, probably the worst creation of statisticians. A pie chart shows how large each category is in relation to the whole. The whole is represented by the entire circle. The parts are slices of that pie. It's used to describe qualitative categorical data. It's pretty straightforward. You create your frequency distribution for it. You calculate the relative frequencies, and then you multiply each of those relative frequencies by 360 degrees, or 2 pi if you prefer. Here's the example. Calculate the housing types for students in a statistics class. 4 types of housing. This is the frequency distribution We learned about how to calculate that in the last lecture. 20, 15, 9, and 5. 49 is our sample size. So now we create relative frequencies. So the first relative frequency is 20 divided by 49. Second will be 15 over 49. Third will be 9 over 49. The last one will be 5 over 49. And then we create the central angle measures by multiplying those relative frequencies by 360 degrees. So we know that the apartment has to cover 147 degrees of that 360 degree circle. The dorm has to cover 31%, which is 110 degrees, etc. And then we just create the histogram, the pie chart, drawing a circle, a dot in the center, and then measure that this 41% is 147 degrees, and this 31% corresponds to 110 degrees, and this 18% is 66 degrees, etc. Rather difficult to create in all reality. It also suffers from the fact that slices have to be different colors, and brighter colors tend to draw our attention more. So the 10% slice, the gold, yellowish gold slice, tends to look bigger than the 10% that is allotted to it. Furthermore, it's kind of difficult without the 10 and the 18 actually stated there to compare the size of this slice to the size of that slice. Our eyes, our brains have trouble distinguishing central angles and the relative sizes of those. So, for all intents and purposes, unless someone tells you you must make a pie chart, avoid pie charts. A much easier chart to create and better all-around chart to create is a bar chart, which we'll see next. But we got the R, so let's go ahead and start R. If I can figure out how to do that. That didn't do it. That kind of did it. So I'm going to just start R. I've got a link to R in several places. This is one of them. You will probably have 2 links on your desktop, or 1 or 2 links on your desktop. But it'll be here. I've got several versions of R. This is an old version of R, but it works for me. Just started. First thing, always, new script. Notice there's overlap between the two. In PCs, there's going to be that overlap. In Macs, there may not be. So I'm going to tile vertically. Notice I clicked on the console window first. So the console window is over here. The script window is over there. So the first thing I'm going to do is load data. These pound signs or hashtags indicate a comment. Once R comes across one of them, it ignores everything else in that line. So I use 3 to indent more. Notice I move things around. I'm going to make this side bigger so you can see it. I'm going to load data from the internet. I'm going to read a CSV file from the internet. The function I'm going to use is read.csv. It requires that you specify the path to that location. What we're going to look at is the crime data set. Remember, you've got the pause button, so you can pause this and type it in. Notice that if I just run this, and by quote run this, that's Control R on a PC or Command Enter on a Mac, it's going to go to the internet. It's going to go to this particular URL, and it's going to read it, and it's going to spit it back out on over here on the console window. So this is that data set. It just printed it off. It didn't save it. R doesn't know this data set now. Since we are going to be using this data set, we need to save it into a variable. By bad habit, I call this variable DT for data. A good habit, and computer scientists would want to do this, is to name it something descriptive. So crime will be the crime data set, or they may want to do crime data set if they like their camel case, or capital C crime data set. I'm bad enough at typing that I just leave it as dt. I run that. Notice what happens over on the left. It just spits out dt equals read.csv of this URL. No errors because I typed everything correctly. And all this data set is now stored in the variable dt. If I want to see it, I'm going to type dt over on the console side. To run a line on the console side, you just have to hit enter, and boom, it spits out the entire data set. We got a variable repub. If I want to look at that variable repub, I can type repub here. On the script side, if I'm going to save it and use it later, or I can just explore over on this side, type repub, type it in, hit the enter key, and get an error. Error, object repub not found. There's going to be two reasons for that error. One, misspelling. Two, you didn't attach the data set. R only sees one variable at the moment. That one variable is dt, the entire data set. There are ways of peeking into the data set for R. Name of the data set, $sign says peek into, and then the variable name. And that will give us all the Republican values. Or if we're going to be doing this a lot and we don't want to type dt frequently, we can just attach the data. Run the attach, and then repub now gives us the data values. So if I don't attach, just typing the name of the variable gives me an error. I have to do the data set name $sign repub to get those values. Or if I just attach the entire data set, I can type repub or any of these variables to access them. Actually, if all I want is the names of the variables, I can use the names function. Similarly, if I want a summary of each of the variables, I can type summary. This is very useful because it tells us how R sees the variables themselves. If it gives a frequency distribution, R sees this variable as being a categorical variable. If it gives us the 6-number summary, R sees this as being a numeric variable. So back to repub, the minimum value is a negative 0.25, the maximum is 0.24, there's 3 missing values, the median is 0.01, the mean is 0.005. But that doesn't matter because we want to look at how to do a pie chart. Pie chart, let's do a pie chart of census 4. There's our census 4 variable. First thing we need to do is tabulate the values, that is, get a frequency distribution for it. We do that with the table function, and then to create the pie chart, we just use the pie function on that frequency distribution. And now, as you can see, it's kind of difficult for me to tell which of these two is bigger, Midwest or West. If I look at it long enough, I can tell that it's West, but it took me a long time to figure that out. I had to stop and think about it. Those aren't pretty colors, but this is just for you to understand the data itself. So the pie function, when it's applied to a frequency distribution, gives us a pie chart. And to create that frequency distribution, it's the table function. Let's see if I can get back to this. Okay. Moving on from a pie chart, we go to the bar graphs, or the bar charts. A bar graph is just like a pie chart, except instead of pieces of a circle, it's bars of a certain height. The height of those bars represents the frequency of the data, of the values in the data set. It's for qualitative data. Pareto charts are for nominal data. It orders the bar heights from lowest to highest or highest to lowest. Your choice. Stacked bar graph is for looking at two different categorical variables where the bars are stacked, and then we've got the side by side. It's where the bars are side by side, clearly. Of all of these, if I've got the bottom two are for two categorical variables, Pareto is only for nominal, the bar is for nominal and ordinal. between the stacked and the side-by-side, I personally prefer the side-by-side. It's a personal preference. I don't know that there's any science behind it other than it's my personal preference. So here we are creating a bar graph from our data that we've already found the frequency distribution for. The apartment bar is going to be 20 high, the dorm bar is going to be 15 high, the house bar is going to be 9 high, the sorority fraternity bar is going to be 5 high, because those are the frequencies. That's all there is to this. And now I don't have to squint and try to estimate which of these is bigger and which is smaller. And by the way, this happens to be a Pareto chart because it's going from largest to smallest or smallest to largest. We got the R, so let's see how we can do a bar graph or a bar chart in R. The function is bar plot. Again, it's applied to a frequency distribution. And there's our bar plot. The height of Midwest corresponds to the frequency of Midwest states. The height of Northeast to the frequency of Northeast states, etc. If I want to turn this into a Pareto, I just have to sort. And now we see that the South is the most frequent, Northeast is the least frequent. Pretty straightforward. By the way, the space that I left here and here are optional. Those spaces are for me as the reader to better understand what I'm typing and to make sure I don't make mistakes. If I don't include those spaces, there's a good chance that I will forget the closing parenthesis. I'll run that line and I'll get a plus mark down here. The plus mark indicates that R is waiting for some more input. It's waiting for something from me. Usually it's a closing parenthesis or a closing brace. In this case, I know it's a closing parenthesis. Two ways of dealing with it. If I know it's a closing parenthesis, I can just highlight that parenthesis and run it. It runs the line, prints out the bar chart, and we get back to a less than sign. If I wasn't sure what the problem was, I click over on the console side and I'll hit the escape button and then enter, and I get back to the less than sign, or maybe that's a greater than sign. But the key is use spaces for you so that you can tell what you're typing. Here's how to do the Pareto chart by hand. You just order it and you get that. Notice this is a horizontal bar chart. Here's how to do horizontal in R. HORIZ equals true. There's a comma here. Horiz stands for horizontal. There's true. Now we've got ourselves a horizontal Pareto chart. Here's stacked. Stacked bar charts are for looking at comparing two categorical variables. In this case, one variable is the sample letter and the other is housing type. So in the apartment housing type, sample A came up with about 20 of students who were in the apartment, and sample B came up with 13, because the height from here to here is 13. Here's how to do the stacked. Side by side looks exactly the same except the heights. These aren't stacked on top of each other. They're side by side, hence the name side by side. Let's see how to do side by side in R. First, we got to figure out that frequency distribution. We'll use the table command. Tables used for frequency distributions of categorical variables. We'll do census for, that's a comma. Let's do it by, what names do we have available? Here we go. Looking through these, there's lots and lots of variables. I'm going to do Dom Paul culture as my second. So this is our two-dimensional frequency distribution. This 5 here says that in our sample, 5 states are in the Midwest and are individualistic. This 7 is 7 states are in the Midwest and are moralistic. This 0 is 0 states in the Midwest are traditionalistic. 7 Western states are moralistic. 15 Southern states are traditionalistic. So that's our frequency distribution. And now we just apply our bar plot to this. Copy and paste is fantastic, isn't it? So here we are with this, a stacked individualistic. Altogether there's 17. Moralistic, altogether there's 17. Traditionalistic, altogether there's 17. These colors correspond to the census 4 region. Let's see if this works. Specify legend equals true. So the lightest is the west. So this would be the western states that are individualistic. This will be the southern that are individualistic. This is the northeast that are individualistic. This is the Midwest that are individualistic. This will be the south that are traditionalistic and the west that are traditionalistic. That's one way of looking at it, the data. We could switch the order. And now the base is going to be the region of the country, and the bar heights are going to be based on the dominant political culture. So in the Midwest, individualistic is about 5, moralistic is about 7. Northeast, south, west. Which of those two is better? This or this? The answer is it depends on what story you're trying to tell or to learn about the data. If you're trying to learn about the data, both are important to do. If you have trouble with the colors, you can specify different colors. Going to have to specify 4 colors here with col. C-O-L stands for colors. And pretty easy, we can just do 1 through 4. That's a colon, it indicates through, so this 1:4 is the numbers 1 through 4. 1, 2, 3, 4. And now we run this, and we can see much more clearly what the colors are. The west is the blue, the south is the green, the northeast is the red, the Midwest is the black. For this second, there's only 3. I'm going to do colors 4 through 7. 4 through 6. 4, 5, and 6 will be the colors we use. Ew. Probably should have guessed what the colors were. Blue, cyan, and magenta. Guess it could be worse. So those are side by side. Those are stacked. To do side by side, we just specify. We spell correctly, beside equals true. So to get side by side, we just have to specify beside equals true. And now we have side by side. This may be helpful to look in the Midwest and see that the moralistic outnumbers the individualistic. In the Northeast, the individualistic is about double the moralistic. In the South, strongly traditionalistic, with just a couple individualistic, and the West is much more spread out. And again, we could change the order. But we now have 4 colors we need to deal with. So the individualistics are kind of spread out over the 4 groups. The moralistic is totally missing in the South, and traditionalistic is Midwest and Northwest, totally missing. So again, which of these two is better? They both tell us a story about the data, therefore they are both important. Frequency histogram, or just a histogram, is a bar graph of a frequency distribution of quantitative data. Frequency histogram is based on your grouped distribution from last lecture. A relative frequency histogram is also based on your grouped frequency distribution, but it's a relative frequency distribution. Characteristics of histograms: it's a bar graph of a frequency distribution. Horizontal axis is a real number line. It's the values of your variable. The vertical axis is going to be the frequency within each of those classes. The width of the bars represents the class width. The bars in the histogram should touch. Tell that to Excel, because Excel doesn't let them touch unless you know the tricks. The height of each bar represents the frequency. So here's the example. Remember this example from last time? Took a long time to come up with this table of frequencies. Getting the graph is pretty straightforward though. There's 2 in the first class, 5 in the second class, 4 in the third class, 5, then 4 again. This was the hard part. Creating bar charts off of it, the easy part. This is for the frequency histogram, and doing it for the relative frequency, you get exactly the same shape. Exactly the same shape. You just got to call the vertical axis the relative frequency. Here's how to do a histogram in R. We'll do it on the violent crime rate in 1990. The function is hist for histogram. There's our basic histogram. That was pretty fast. By default, in this case, particularly, R is going to have class widths of 500. There's going to be 1, 2, 3, 4, 5 classes. There's an algorithm it goes through to figure out the quote optimal, but there's nothing optimal about these. You need to actually specify, you need to do multiple histograms so you get a better feel for what the data are. So here's how you specify. It's with the breaks option. This will give us about 11 breaks. Breaks are going to be close to the class boundaries. Going to be similar to the class boundaries. You want more than 11 breaks? How about 21 breaks? Again, the key is 51 breaks. The key is, what story are these telling us? And what's the best story for it to tell? There's 1,001 breaks. There's 5 breaks. There's 2 breaks. Notice that we could also, or realize that we can also, instead of just say the number of breaks, we can specify the actual class boundaries themselves. Also with the breaks slot, we're going to use the sequence function, seq for sequence. The lowest is 0, the highest I think was 2,500, and then the third slot here belongs to the number of classes you want. I'm sorry, ignore that. It doesn't belong to the classes you want, number of classes. It belongs to the class width. So if I want my class widths to be 100, that's what it's going to look like. If I want the class widths to be 200, ooh, I got an error down here. Some x not counted. Oh, that's because this function will set up values. I'm going to run just that part. At 0, 200, 400, 600, I'm adding 200 each time until I get to 2,400, because adding another 200 will put us beyond. And the Washington, D.C. is actually sitting out there above 2,400. It needs to be counted. So 2,600. And now it runs. 250. 10. Notice how quickly we're able to create these histograms. We don't have to focus on the particular calculations. We can choose our class widths and allow that to tell us the story of the data much more quickly. In all of these, the story of the data says, hey, look at this outlier. It's far from all the others. This happens to be the District of Columbia. Everything else seems to be clumped. Nice little bell shape-ish to it. And that was true when it was 100 for the class width. Again, bell shape, not quite so smooth, but a bell shape nonetheless. When we use 2,500, when we use 200, this actually looks like the best of them, but it looks like the best to me because I still got that outlier and I've got a nice curve over on the left. So notice how quickly we did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 histograms. If we were stuck doing these by hand, you'd still be doing the first one. Stem and leaf plot is an old-time histogram. It's also for quantitative data. There's a lot of steps to it. Again, it takes a long time to do it. You're going to want to do one of these at least once, but the reality is once you can do a histogram, there's no reason to do a stem and leaf plot. So here we've got the ACT scores. The stem is going to be the tens place. So this stem will be a 1, the leaf will be 8, the stem is 2, the leaf is 3, the stem is 2, the leaf is 4. And then we just collect on the stems and write out the leaves. So we got 18, 19, 18, 18, 17 are ACT scores, 23, 24, 27, 26, 22, 27, 29, etc. are the ACT scores. It's better to do these in order, by the way. So the data values are 17, 18, 18, 18, 19, 20, 21, 22, 23, 24, 24, 25, etc. If you want, in R, the function is stem and here's your stem and leaf plot. Here's the key. Decimal point is 2 to the right of it, so this is going to be 0, 2 to the right of this is a decimal place, so that'll be 70. It'll be 130, 130, 140, 160, 160, 170, because these are by twos. 260, 280, 280, 280, 300, 300, 310, 330, 340, 350, 390, 430, 430, etc. This is 2460, this is 1240, this is 1050, 1080. Line graphs. The last graph for today is using the data or measurements over time. It's just a scatter plot, connected the dots, where the horizontal axis is time. The vertical axis is our variable of interest. So here's the example with the consumer price index. CPI is a measure of the average change in the value over time for a, quote, basket of goods and services for a typical American. It's an index calculated by the Bureau of Labor and Statistics. The table below shows the actual values of the CPI from several years from 1920 to 2010, actually every decade. So in 1920 the CPI was 20, so it cost $20 for that basket of goods. In the year 2000 it cost $172.20 for that same basket of goods. Technically not the same basket. Some items were switched out and put in over time, but they were equivalent when they were switched out and replaced. Here's the line graph. Notice the horizontal axis is the year. Vertical axis is the CPI. And you can look, it was pretty consistent until 1970, and then the price increased dramatically over the next 40 years. Let's see how to do this in R. First, we got to specify the variable values. This was the years. Happened to be a sequence from 1920 to 2010 every 10 years. Then the CPI itself is equal to C. C is a function that collects several values into one vector. I'm going to be switching back and forth a lot. 20, 16.7, 14, 24.1, 29.6, 82.4, 130.7, 172, 2.2, finally to 18.1. So those are the variables we got. Run them. Notice there's no errors over here. And then we just do a plot. X variable comes first. That would be the year in this case. The Y variable comes next, which is the CPI. And then this has to be a line and dot. Got lines and dots. One way of doing that is to specify type is equal to lowercase b. And there's our line graph. X-axis, or X variable, Y variable, and to get both lines and dots, you would do type equals b. If you want lines, that will be a lowercase l. That is a lowercase l. Notice the dots go away. But you can add them back with the points command. And now the dots are back. You're going to learn how to make this graph look much more appealing, but that is for a different slideshow. So here's the summary. For qualitative data, that is for categorical data, we got pie charts and bar graphs. We got the Pareto chart if the data are nominal. Side-by-side bar and stacked bar when you've got two categorical variables that you're looking at. For quantitative data, you've got the histogram. You've got the stem and leaf plot, which if you turn your head sideways, looks an awful lot like that histogram. And then we've got the line graph if the horizontal axis or the x variable is time. And now we got our red star. It's pretty good because that's the last page here. Let's see how bad I've messed it up. Aha! We got it back. So question number 2. And again, I would recommend writing the question and your answer on the left-hand side of your notes. So question 2, which graphics can only be used for a single categorical variable? Key is the word single and the word categorical. Go ahead and hit pause. Question number 3, which graphics can only be used for a single numeric variable? Single numeric. And both question 2 and question 3 have multiple answers. Don't forget to submit these into Moodle. And that's it. I hope this was helpful. Take care. Hello and welcome to section 2.3, an additional section on analyzing graphs. This is not computational in structure. This is more of an interpretation section and a better understanding of what makes a good graph and, in many ways, more importantly, what makes a bad graph. So the objective is to identify misleading characteristics of a graph with the hope that you will avoid them yourself. There we go. So title, axis, source. This is how to properly label a graph. The middle part really is the only thing done in your statistical program. The title and the source and the caption and the numbering is done in your word processing or typesetting program. So the bar part, this middle part, is all that's done in your statistical program. The title and the source stuff is done in your word processor. A time series graph is a line graph that is used to display a variable whose values change over time. We've seen this already. We called it a line graph in the last section. This should ring a bell as something like panel data from chapter 1. It should be able to go back over your notes, press pause, go back over your notes and see what panel data was. This is a way of describing panel data for one or a very small number of people. Cross-sectional graph is a way of displaying information collected at only one point in time. Again, that should remind us of something we talked about in chapter 1 about cross-sectional data. A pictograph is a bar graph that uses pictures of objects instead of bars. They look really spiffy, but they're really dangerous. So let's go ahead and we got a red star, so let's go to our first question. How do pictographs differ from bar charts? So again, over on your left side of your notes, right? How do pictographs differ from bar charts? Answer that. Hit pause right now, and you're back. So let's move on. So here's an example of how pictographs can be deceiving. The one that you're going to see in the newspapers are the one on the right, and the one on the left is the quote correct monthly housing. There are at least three things wrong with the incorrect pictograph. For one, I'm going to draw your attention to the axis values and compare here. Two, I'm going to say what is the area of the 94 versus the area of the 2006 house on the left? Well, the 2006 is double the 94, which corresponds to it actually increasing by double. Hint, it's a ratio level variable, so we can meaningfully talk about doubling and halving. Whereas in the incorrect, going from 94 to 2006, it doesn't double in size, it quadruples in size. Because not only are you doubling the height, but you're doubling the width to keep the right form. So our eyes are saying, oh my goodness, it increased by a factor of 4. Even though we try to focus on the scale on the left, and it only increases by a factor of 2, our mind, our gut reaction to this is it increases by a factor of 4. So that's another way that this particular pictograph is deceiving. I've given you two. Question number 2, what are 3 things misleading about this particular pictograph? And I would recommend that, again, you write over on the left this question, your answer. Also pause and go back and look at that particular pictograph, see if you can figure out another thing that's misleading about it. Scaling of graphs. Another important feature to look out for is that the graph is scaled properly. If you stretch or shrink the scale on the y-axis, the shape of the graph may change dramatically. A line that rises gently on one scale may look very steep with a different scale. Make sure that you choose the correct scale, and by correct, I mean the scale that forces the graphic to show you the story of the data. In other words, make sure that it represents the data well. You don't want you to force the data to tell a story. Your graphic should allow the data to tell its story. It takes practice. So here's an example. Looking at this quickly really doesn't seem like there's anything wrong here. Consider the graph below, U.S. federal minimum wage hour rates. Unadjusted for inflation, what errors can you find in the graph? How should they be fixed? So the dates along the x-axis, so this is a time series plot, also known from last time as a line graph. Vertical axis is the minimum hourly wage in dollars. So as you, over time, things increase in terms of dollars, and it looks pretty awesome because your minimum hourly wage is increasing over time. So what's wrong with this? Well, the fact that in 1956 a dollar doesn't buy quite as much as a dollar did in 2008. So perhaps we should, instead of unadjusting it, we should adjust for inflation. Notice the x-axis does not have a consistent scale. The years are as few as 1 apart. I didn't even notice that, my goodness. There's 1 apart here, there's 6 apart here, there's 5 apart, 6, 5, 2, 4, etc. So you should stretch this, shrink this so that each inch along the horizontal axis corresponds to a single time limit. So maybe each of these marks should be 3 years instead of something. So change the x-axis, correct graph can be found in exercise 12 in the chapter 2 exercises. But that's not the only thing. Maybe you should adjust this for inflation. Now we're going to talk about some shapes of graphs. Four basic shapes are uniform, symmetric, right-skewed, and left-skewed. The right-skewed I will frequently call positively skewed, and skewed to the left I will frequently call negatively skewed, simply because I have trouble with left and right. The name outlier is a data value that falls outside the quote normal shape of the graph or the typical shape of the graph. We've already seen outliers back in section 2.2. The District of Columbia was an outlier in terms of the violent crime rate in 1990. Its little bar in the histogram was far away from the rest of them. So here's what a uniform distribution looks like. The frequency of each class is relatively the same. If you're dealing with sample data, it's unlikely that you'll get bars all the exact same height, even if the population has a uniform distribution to it. Symmetrical. Data lie evenly on both sides of the distribution, whatever that means. I want to talk about the skewed, two skews, and then come back to the symmetrical. That might make this a little bit more meaningful. Skewed to the right or positively skewed. The key for skew is to locate the tail. The tail is the side where the data just keeps lingering on and on, as opposed to in this case, as opposed to the left side where it just kind of stops quickly. The right side just keeps going on and on. So there's a right tail here. So this is skewed to the right or skewed positively. Skewed right because the tail's on the right. Skewed positively because the tail's on the positive side of the middle. Contrast that with skewed to the left. Again, the data just keeps going on and on and on. It stops rather quickly here. So this is left skewed because the tail is on the left, or it's negatively skewed because it's on the negative side of the middle. With that said, symmetric data have neither a right skewed nor a left skewed. Notice here it kind of stops at about the same distance. It's not perfectly symmetrical in the mathematical sense. The key, and here's the key that I tell people, it's in order to, if you want to conclude that data seems symmetrical, it's try to determine which side gives you the tail. If you have to stop and think a little bit about it, like at least a second, then it's symmetrical enough. We're actually going to, in the next chapter, come up with a definition of symmetrical and a way of determining if the data are, quote, symmetrical enough. But for now, just look and see, okay, are the data obviously skewed right or obviously skewed left? And if the answer to both of those is no, then it's symmetrical enough. So let's describe the overall shape of this distribution. The middle seems to be somewhere around here. It doesn't seem to have a tail on either side. I mean, if I squinted hard, I could probably figure out a tail, but because I'm not seeing any obvious tail, I'm going to say this is symmetric. The average is somewhere around 80. I don't see any outliers. If there is one bar way, way over here, I'd say, yeah, there's an outlier. If there was a bar way, way over here, I'd say, yeah, there's an outlier. So there's the smooth curve that they're talking about. The average seems to be about 80. Yeah, symmetric, no outliers. Red star. So the third one, how does one determine the tail of a distribution of a graphic? Go ahead and hit pause. Hopefully your answer is written in your notes so that you can later transfer them to the Moodle quiz. And that's the end of this rather short chapter, or short section. It actually is the end of this chapter. So make sure you keep sending me those questions, post those questions to the discussion board, and I will talk to you later. Take care. Hello and welcome to section 3.2, Measures of Dispersion, purpose of this section is clearly to determine ways of measuring the dispersion of a data set. What do we mean by dispersion? We mean how spread out the data are. Hence, these are also called measures of spread. We're going to look at 4 measures of spread in this lecture, postponing the 5th one, the interquartile range, until the next. So here's the gut definition of a measure of spread. It's a measure of how much we can expect a value of the data to differ from the appropriate measure of center. So because of that, that means that we've got measures of spread for the mode, we've got measures of spread for the median, we've got measures of spread for the mean. We've got lots of measures of spread, all of them trying to define this, trying to measure the same thing, the spread of the data. Or we can also think of spread and dispersion as being the uncertainty in your data value. That is, if I've got a data set with a very small level of dispersion, you're much more certain about where that individual value is going to be than if you've got a very, very largely dispersed data set, where you got a value and you have no idea if it's to the left tail, to the right tail, close to the middle, a million miles away. Note that there are many, many, many measures of dispersion. How one defines spread or dispersion and what properties one wants in such a measure determine the formula that is being used. So be aware of that. I see a red star, so let's pop over to the interlecture question, number 1. What is the main purpose of a measure of dispersion, aka a measure of spread? Again, I recommend writing on the left-hand side of your notebook the question, your answer underneath of that, so that when you do go into Moodle to finish this quiz, you'll have the answers right there. And of course, hit pause, and we're back. The first measure of spread, and the weakest one that we've got, is just the range. The range of your data is just the largest value minus the smallest value. So the range is a single number. It's not 2 numbers, it's a single number. So if we're looking at heights of students in this Stat 200 class, the range is going to be 13 inches. 13.2 inches actually. So a single number. The difference between the highest value and the lowest value. That's it. Since it's based on 2 specific values, the range is going to be very unstable. That is, if I send 3 people out to draw a sample from the same population, you're going to get different samples, by the way, then the ranges have a very strong chance of varying quite drastically between the 2 samples. That's what I mean by unstable, or it's not robust. A much better measure of dispersion is called the variance. This one is for the population variance. The population variance is the average squared distance of the population values from the mean. So I've got my cursor. So xi is a data value or a value in the population. Mu, recall, is the population mean. Capital N, recall, is the population size. And we're going to call sigma squared the population variance. That will be the symbol for the population variance. And what we're doing is just adding up every value in the population minus the mean. We're going to square that, add them all up, and divide by the population size. Similar to the population variance is the sample variance. This is the one that's actually going to be useful for us. Notice that the formula looks exactly the same except for 3 parts. Let's call it 3 parts. Part 1 is the symbol for sample variance is an S squared. For the population variance, it was sigma squared. Recall that population parameters tend to be Greek letters and sample parameters tend to be Latin letters. So it's S squared for the sample variance, sigma squared for the population variance. That's one difference. Second difference is you're subtracting off x bar, which is the sample mean. For the population variance, you're subtracting off mu, the population mean. Here we're subtracting off x bar, the sample mean. And 2, instead of dividing by n, we're dividing by n minus 1. And we'll explain why a little bit later. So again, it's each data value minus the mean of the data squared, added up divided by n minus 1. And that will give you the sample variance. So let's calculate some variances. Very small, simple toy data set here. So let's assume the data represent the actual weight changes for a sample of fitness club members. So for A, we're going to calculate the sample variance. And for B, assume that the data represent the actual weight changes of every member. So for B, we're going to calculate the population variance of these 5 values. So again, notice the numbers are meaningless unless you add context to them. Does 32564, is that the sample or is that the population? You need to know. By the way, in this class, unless stated otherwise, that's going to be a sample. So let's do the calculations. Here's the function. Here's the formula for the sample variance. We've got the values x sub I, which are just the 32564. X bar is going to be 4 because the sample mean of 32564 is 4. N is 5, which means that n minus 1 is going to be 4. So all we have to do is take each of those x values, subtract off 4, square it, add them all together, and then divide by 4. And that's what we're doing here. Data values, the deviations, which is the data value minus the sample mean. Notice if we add up the deviations, we get 0, which is a good thing. The squared deviations, the xi minus the x bar, yeah, the bar is there somewhere, squared. Notice if we add these up, we don't get 0. And now if we add these up, 14140 gives us 10. And now all we have to do is divide by little n minus 1. 10 divided by 5 minus 1 is 2.5, so the sample variance is 2.5. We can do this in R. For a sample of size 5, you may not need to, because it's very straightforward putting this table together and doing all the calculations. But once we get into sample sizes of 50, 100, 10,000, you're going to want to be able to do this on a computer. The function to calculate the sample variance is var, V-A-R, V-A-R for variance. First line, we define a variable called weight. We're going to put inside of weight 5 values, a 3, a 2, a 5, a 6, and a 4. Notice you've got the little c to combine all of these values into one variable. And then we calculate the variance of weight. That's it. So now B, remember, was for a population variance. We can do this the long way. We would essentially just end up dividing by n, 5, instead of n minus 1. Or we can do this on a computer. For a sample of size 5, and not a big deal. For a sample of size 5,000, that is a big deal. So again, here's our data. To calculate the population variance, you could do the sample variance times 4 over 5. N minus 1 over n. Why n minus 1 over n? Well, let's go back to the formulas. There we go. We want to calculate this number. We've got this number. Notice the difference is the denominator. So we're going to multiply this number, the sample variance, by n minus 1 here. It'll cancel out the n minus 1s, n minus 1 over capital N. So what you'll be left with is just the sum of the xi minus the mean squared over capital N. So 4 over 5. If you're going to calculate population variance a lot, you may want to create a function for it. This is the first place that we see the extensibility of R. We'll create a function called varpop, the variance of the population, I guess. We're going to set it equal to this keyword called function. We're going to give it just one variable, x, that'll be the data. That's a brace, an open brace, and that's a closed brace down here. And then the actual calculation is just x minus the mean of the x's squared and the average of those. It's the average because you're dividing by the number, capital N. And you would use it as varpop of weights. You would have to create this function in every script that you need the population variance in. Thing is, we rarely have the entire population. We tend to deal with just the sample populations. Hence, the var is the sample variance. So here's the big question. Where does the formula actually come from? What does it tell us? What does it do for us? So we can think of variance as an average distance that the values in a set lie from the mean. Maybe they lay from the mean. I think they lie from the mean. So while it's not an actual average, and we're thinking of the sample variance here, the variance is usually very close to the average, and conceptually it's a good way to think about what this variance is actually calculating. So on your notes, I'm sure you got the variance formula there. So to derive this formula for variance, we're going to use a method similar to finding average distances or squared deviations from the mean. So first we must know the actual deviation from the mean. Well, that's just xi minus x bar. That's a deviation. That's how far that individual value is from the mean. And then we're going to square those to get a distance, or technically a squared distance. And then we're going to find the average of all of those. How do you find an average? Well, you add them up, divide by the sample size. Well, we're not entirely dividing by the sample size. We're dividing by the sample size minus 1. But essentially, this is just the deviances squared, so it's a squared distance. And this part will just be an average squared distance from the data point to the mean. So yn minus 1, and this is pretty important, the fundamental purpose of sample statistics is to estimate a population parameter. So the n minus 1 is there so that s squared is a good estimator of sigma squared. Now, that's the reason for n minus 1. And then mathematics is the other reason for that. Laboratory activity D as in dog, looks at estimators and what makes a good estimator and what do we mean by good estimator. And at that point, you'll see, oh yeah, unbiased estimators are, all things equal, are good things. And dividing by n minus 1 gives us an unbiased estimator of sigma squared. The standard deviation is closely related to the variance. Standard deviation is also a measure of how much we might expect a typical member of the data to differ from the mean. In words, the definition seems very, very similar. In fact, it's probably exactly the same. I like to copy and paste things. The only difference is the formula and what we mean by how much we might expect it to differ. Sigma squared is the variance. Sigma is the standard deviation. Those are for the population, by the way. So the population standard deviation is just the square root of the population variance. And the sample standard deviation is equal to the square root of the sample variance. So the big question comes up, if the sample standard deviation, the sample variance, or the population standard deviation and the population variance really tell us the same information, why are we pardon me, why are we introducing the standard deviation? And the reason is the units of the standard deviation are going to be exactly the same as the units of your data. So if your data are inches, your standard deviation units are going to be inches. If your data are years, your standard deviation units will be years. For the variance, it'll be the square of that unit, which is much more difficult to see on a histogram. I can see things that are in the same units of the data because the histogram is in the units of the data. But seeing it in terms of the square, that's much more difficult to see. Thus, standard deviation is much more interpretable and should be used in all of your papers instead of the variance. Which brings up a related question. Why do we cover the variance first? The reason we cover the variance first is because it's much more intuitive as to what it's trying to measure. The square rooting of the variance just brings the units down into what we're used to. Also, mathematicians love to use a variance because variances add. Standard deviations do not add. So, mathematicians like the variance. Everybody else on the face of this planet love the standard deviations. Ooh, we got a red star. So, question 2. Why should one report the standard deviation instead of the variance? Again, write the question on the left-hand side, answer it underneath. Go ahead and pause, and we're back. So let's calculate the standard deviation. So let's find the sample standard deviation with the data shown below. I challenge you to do this by hand. Here it is in R. Just take the data, wrap it in a C function, send it to the variable. Since there's no context to what these numbers actually mean, we'll just say x is equal to those values. And then the function to calculate the sample standard deviation is just SD. That's it. If you need to calculate the population standard deviation, we're going to have to go back to the function you created, varpop, calculate the population variance, and then take the square root of that. SQRT is the square root function. But again, statisticians rarely calculate population parameters. They estimate them, but they estimate them with the sample statistics. Hence, SD is the sample standard deviation, and VAR is the sample variance. Here's a use, or I guess we're going to say it's an application of the standard deviation. Financial people love to use variance and standard deviation because they indicate risk of an investment. So we're looking into investing a portion of recent bonus into the stock market. I guess Mark's doing it, we're not. While researching different companies, he discovers the following standard deviations of 1 year of daily stock closing prices. Pro facto, the standard deviation is $1.02. Yardsmith, it's $9.67. In other words, the standard deviation of Yardsmith is much larger than that of pro facto. So all things being equal, there is much more variability in Yardsmith than there is in pro facto. So if you want a nice, stable stock investment, you'll go with pro facto instead of Yardsmith, which is what the solution says. Hence, stable. Note that looking at standard deviations is just one component of evaluating market prices or plans or things like that. Another measure of spread is called the coefficient of variation. The coefficient of variation is just the standard deviation divided by the mean times 100%. If you're looking at the population coefficient of variation, it'll be sigma over mu. If you're looking at the sample coefficient of variation, it'll be S over x bar. Why do we introduce yet another coefficient of variation? It's because the coefficient of variation is used to compare dispersions for two variables. Hence, our previous example, which I don't want to say in front of anyone from Hawks, this is completely useless. Because if pro facto has a standard deviation of $1.02, but it trades at $1, well, that's an incredible change, incredible width of it. Whereas Yardsmith, it's $9.67, but if it's trading at $1,000 a share, that's really not much of a variation. So while we do like to look at the standard deviation as being a measure of risk, really it should be the coefficient of variation, which this gets to. Example 314, we got two graphs, and we're trying to figure out which has the greater standard deviation relative to its mean. In other words, which has a greater coefficient of variation. If we ignore the bottom numbers, which of these two graphics is more spread out? And it's very clear that the price of U.S. farmland is much more variable, if we ignore the bottom numbers, much more variable than is the annual average rainfall. And that's what the coefficient of variation really does. It ignores the bottom numbers and just looks at the shape of the graphs, or quantifies how spread out the graph is. We can do the actual calculations, find out the coefficient of variation for data set A is 28.9%, and for B it's 36.7%. That really doesn't surprise us because we just decided that B is much more spread out than A is. And that's what the coefficient of variation is measuring. It's how spread out is the data if we ignore the actual values at the bottom. And dividing by that x bar allows us to ignore those values at the bottom. So those are measures of spread, or measures of dispersion. The last two topics for this section really don't sit well with that idea of measures of center, measures of spread. They really probably should be on their own section, but this is where Hawks is putting it, and between the two of us, it's good as place as any to put them. We're going to look at the empirical rule and Chebyshev's theorem. The empirical rule says that when the data follow a bell-shaped distribution, an interesting pattern emerges in the data values. About 68% of the data is within one standard deviation of the mean. That is, about 68% is between the values of mu minus sigma and mu plus sigma. About 95% is within two standard deviations of the mean. That is, about 95% is between mu minus 2 sigma and mu plus 2 sigma. And almost all of it, 99.7%, is within three standard deviations of the mean. And that's all the empirical rule says. Notice it's when the data follow a bell-shaped distribution, these are good estimates. If the data do not follow a bell-shaped distribution, these are not necessarily good estimates. In fact, they tend to be pretty poor. So if the data follow a nice little bell shape here, then 68% is within one standard deviation of the mean. 95% is within 2. 99.7% is within 3. And almost all is within 4. So here's an application of it. Distribution of weights of newborn babies is bell-shaped with a mean of 3,000 grams. Wow, those are heavy babies. 3,000 grams. And a standard deviation of 500 grams. So we know that 68% of the babies are between 3,000 minus 500 and 3,000 plus 500. 95% is within 3,000 minus 2 times 500 and 3,000 plus 2 times 500. And 99.7% is within 3,000 minus 3 times 500 and 3,000 plus 3 times 500. So what the empirical rule says. A, what percentage of the newborn babies weigh between 2,000 and 4,000 grams? That's 95%, because 2,000 is 2 standard deviations below 3,000, and 4,000 is 2 standard deviations above it. So it's within 2 standard deviations of 3,000. What percentage of newborn babies weigh less than 3,500 grams? That one's not going to be so easy. We do know that 68% are between 2,500 and 500. 2,500 and 3,500, which tells us that 34% is between 3,000 and 3,500. We also know that half is less than 3,000, so we can use that calculation to get the answer. And we can calculate the range of birth rates that would contain the middle 68%, so it's between 2,500 and 3,500. Now here it is written out. Since we know the distribution of the data is bell-shaped, we can apply the empirical rule. We need to know how many standard deviations 2,000 grams and 4,000 grams are from the mean. Here are the calculations. It's 2 below to 2 above. According to the empirical rule, approximately 95% of the values lie within 2 standard deviations of the mean, so it's 95%. B takes a little bit more work. How many standard deviations of weight of 3,500 is away from the mean? Well, that's 1 above. So it's 1 standard deviation above the mean. It says that 68% of the data values lie within 1 standard deviation of the mean. That means that 34% lie between the mean and 1 above. And half is below 3,000 because it's a bell-shaped curve. It's symmetric, so the mean and the median are the same. So if the mean is 3,000, then half will be less than or equal to 3,000. So the 34 and the 50 add together to give us 84% of the newborn babies weigh less than 3,500 grams. Here's a picture of it. 2,500 to 3,500 contains 68%. Since it's symmetric, that means between 3,000 and 3,500, we've got 34%. And it's a symmetric distribution, so half of the data is less than 3,000. So the part that's not yellow is just 50% plus 34%, which gave us the 84%. And then C, also an easy calculation. We know 68% of the data lie within one standard deviation of the mean. So that's between 2,500 and 3,500. And the last topic is Chebyshev's theorem. Whereas the empirical rule is a nice rule of thumb. If the data come from a bell-shaped distribution, it gets you really good estimates. Chebyshev's theorem is a mathematical theorem that is always correct. It's not always helpful, but it's always correct. And the theorem statement is the proportion of data that lie within k, standard deviations of the mean, is at least 1 minus 1 over k squared. And k's got to be greater than 1. So if k is 2, then within 2 standard deviations of the mean is at least 3/4. Could be more than that. Could be a lot more than that. But it's at least 3/4. And the proportion of the data within 3 standard deviations of the mean, set k equal to 3, is about 89%. So at least 89% of the data is within 3 standard deviations of the mean. Could be a lot more than that. Could be just 88.8889%. So Chebyshev's always works, but it doesn't necessarily give us a good estimate. Empirical rule doesn't always work, but when it is applied to bell-shaped data, it does give us a good estimate. So here we'll apply Chebyshev's theorem. Suppose that in one small town, the average household income is $34,200, with a standard deviation of $2,200. What percentage of households earn between $27,600 and $40,800? Well, we just have to figure out how many standard deviations below the mean are 27,600 and how many above the mean are 40,800. That will tell us what the value of k is. And then we use Chebyshev's theorem to determine the minimum or the at least as much. So 6,600 is the distance. We know that the standard deviation is 2,200, so that's a -3. So 27,600 is 3 standard deviations below the mean. Similarly, 40,800 is 3 standard deviations above the mean. Thus, k is 3, and we know that at least 88.9% of the data is within those bounds. Could be a lot more. Can't be less. It absolutely cannot be less than 88.9%. So now let's compare the empirical rule and Chebyshev. Here the difference is Chebyshev's theorem always works, that is, it's always correct. The empirical rule requires the distribution is bell-shaped. The empirical rule tends to give better estimates than does Chebyshev's theorem. Chebyshev just gives a lower bound. Empirical rule tries to estimate the actual proportion. It's going to be off if the data is not bell-shaped, but if the data are bell-shaped, it's going to be a really good estimate, especially compared to Chebyshev's theorem. And while Chebyshev's theorem always works, it only serves as a lower bound, hence the at leasts in the theorem statements. We got a red star, so let's move on to question 3. Which is more helpful, the empirical rule or Chebyshev's theorem? Again, left-hand side of your notes, answer it in your notes so that you can eventually put it into the Moodle quiz. Go ahead and pause. I'm back. And that's it for this chapter. That's it for this section. Measures of dispersion. As we move forward in this class, the measure of dispersion that's going to be most useful for statisticians for some odd reason, is the variance or the standard deviation. That's just how it is. The range, note, we just got one small page dedicated to it, then we kind of left it. You can go ahead and ignore the range. It's not helpful at all. Empirical rule we're going to see pop up again in chapters 6, 7, 8, 9, 10, 11, 12. So you may want to spend a little bit of time learning the empirical rule. Chebyshev, we're not going to see it again after this chapter. So, well, except on, we won't see it again on the chapter. So, now you know the most important things from this section. But again, I want you to focus on how to get the computer to calculate these and how to interpret them. I also want you to figure out why measures of spread are important, especially if we talked about measures of center last lecture. How do those two relate? How are they different? Why would one be more useful than the other? Those are important questions to answer in any class, but especially in statistics. So that's it. I wish you a good day. Hello and welcome to section 3.3, measures of relative position. In some ways this should be section 2.2 and the measures of spread would be section 3.3 because measures of relative position are measures of some point in your data or in your distribution. Very similar to section 3.1 where we talked about a point in your data or in your distribution, but the point for section 3.1 was the mean, the median, or the mode. Here it's going to be some other point within your data. And so topics from a set of data, you're going to be able to calculate percentiles. Sometimes these are called quantiles, Q-U-A-N-T-I-L-E-S. 2, you're going to be able to calculate the quartiles. Then the 5-number summary, which is just all the quartiles together. Calculate the interquartile range, the IQR, which is also a measure of spread. So that kind of ties into the last lecture. We're going to be able to create a box plot and calculate some z-scores. And that z-scores may not sound too interesting now, but those z-scores will pop up again in chapters 6, 7, 8, 9, 10, 11, 12. Without z-scores, without understanding what z-scores do, we kind of lose a lot of this second half of the course. Okay, so we'll start with percentiles. Definition of percentile is those 100 divisions. In order to calculate a value's relative position, we can divide the data into equal parts and state in which part the value lies. That kind of underscores all of these measures of relative position. We may choose to divide the data up into any number of parts. For percentiles, we're dividing the data up into 100 parts. 100 cent. And those divisions, when you divide it up into 100 parts, is called a percentile. Here's how you calculate percentiles. You're going to locate the data value for the pth percentile, so you're going to be given the percentile, such as the 45th percentile, the 97th percentile, the 1.758th percentile. Those values are going to be the p. N will be the sample size, and this, believe it or not, is a lowercase l. L for location. And this is the formula to calculate the location. Notice it's the location, not the data value. So it's the location is just the sample size times the percentile over 100. Well, that percentile over 100 is just the proportion of the way through the data. So it kind of makes sense that this would be a location spot. Did I miss something? No. So when using the formula to find the location for the percentile's value in the data set, you must make sure of the following 2 rules. If the formula results in a decimal value for L, the location is the next larger whole number. If the formula results in a whole number, then the percentile's value is the arithmetic mean of the data value that is located at that location and at the next larger. This kind of sounds vaguely like how we calculate the median, which shouldn't surprise us because the median we're going to find out is the 50th percentile. So here's an example to see how to do this. Car manufacturers studying the highway MPG for a wide range of makes and models of vehicles. Stem and leaf plots given in the next slides. There's a lot of it. There's 135 data points. We need to find the 10th percentile and the 20th percentile. So here's the data. Here's the second page of the data. So we got one vehicle gets 12.1 mile per gallon, another vehicle gets 13.3, another is 14.1, then 15.5, and 15.6. So that's what the stem and leaf plot tells us. So here's the solution. First, we need to notice that the data are in an ordered array. That is, the lowest is 12.1 mile per gallon and the highest is 35.9 miles per gallon. There are 135 values, so n is 135. We want to calculate the 10th percentile, so p is 10. Substituting in the values, we get L is equal to 13.5. Notice 13.5 is not a whole number. Therefore, the next larger, we round that up to 14, and so the data point that is at position 14 will be the 10th percentile. And that data value is 17.3. So let's go back to the data to see that one more time. The 14th data value, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 17.3 is the 14th value. Therefore, 17.3 is the 10th percentile. In other words, approximately 10% of the values in the data set are less than or equal to 17.3. More importantly, if we gathered an infinite amount of data, 10% of the data values would be less than or equal to about 17.3. For B, we're looking at the 20th percentile. We still have n is equal to 135. Now we're given p is equal to 20 because it's the 20th percentile. We got 27 as value for L. This is a whole number, therefore we average the 27th and the 28th data values. Let's go back to the data. 27th and 28th data values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27th is 19.2. 28th is 19.3. Therefore, the 20th percentile would be the arithmetic mean of those two, or 19.25. So approximately 20% of the values in the data set are less than or equal to 19.25. And now we need to figure out a way of calculating the percentile of a given data value. So now we're given the data value, and we need to determine its percentile. So for instance, we're given 18.9 miles per gallon. We need to determine which percentile that corresponds to. It just inverts the previous equation. L is the location of that data value. N is the sample size. So L over N is actually the proportion of the way through the data that holds that value. Multiply by 100, that's the percent of the way through the data that holds the value. And by gosh, that's the percentile, P. So if the data from the previous example, the Nissan Xterra averaged 21.1 miles per gallon, what is its percentile? Well, here we go. We got to figure out what position 21.1 miles per gallon is in the data set. So let's scroll back. 21.1 is way down here or way up here. I'm not going to count that, but I'll let you count it. Happens to be the 49th value. So the value of 21.1 miles per gallon is 49 out of 135 of the way through the data. 49 out of 135 is 0.36, multiply that by 100. So that 21.1 is about 36, is about the 30, is about the 36th percentile. Approximately 36% of the data values are less than or equal to. That is, the value 21.1 miles per gallon is in the 36th percentile of the data set. Ooh, we got a red star. Here we go. This will be the intra-lecture question, the first one of this lecture. Question 1, what is the percentile? Again, write the question on your notebook, answer it so that you can transfer that question and answer, or just that answer, to Moodle for the lecture quiz. Pause, And we're back. Now we're going to look at quartiles. Recall that the percentiles divide the data up into 100, whereas the quartiles are going to divide it up into fourths. 4 for quart. The first quartile is about 25% of the data is less than or equal to it. Second is 50% is less than or equal. Third quartile is 3/4, or 75% of the data is less than or equal to. In other words, the first quartile is the 25th percentile. The second quartile is the 50th percentile, and the third quartile is the 75th percentile. Also recall that the second quartile, which is also the 50th percentile, is also the median. Here's a couple ways of calculating, or shall I say estimating, the quartiles. We're going to use a percentile method, which we just got through doing a couple examples on the percentile. We're going to use the approximation method, going this way. Approximation method is you find the median, drop the median, you find the median of the lower half to get Q1, median of the upper half to get Q3. And look at how these values compare. For a large data set, the values are going to be very close. We already know the data are in order from smallest to largest, and we already know that n is 135. Here's the data set. So using the percentile method, we want to find the 25th percentile. So p is 25. Do these calculations to find that the location is 33.75. Because that is not a whole number, we just look at the 34th value, which is 19.8 miles per gallon. That will be the first quartile, which is identical to the 25th percentile. Second quartile is the median, or the 50th percentile, thus n is equal to 135, p is equal to 50. That brings us to 67.5, round that up to 68. The median will be the 68th value, which is 23.6. The third quartile is to the 75th percentile, so p is 75, put it into the formula, 101 rounded up to 102, so it'll be the 102nd value, which is 25.3. So the third quartile is 25.3. We can also do the approximation method, divide the data in half. We get the 68th position, which is the median, is 23.6. We've calculated that many times. So the second quartile is 23.6. First quartile is going to be the median of the lower half, which comes out to be 19.8. And the third quartile is the median of the upper half, which is 25.3. They're very, very close. And for large data sets, they are going to tend to be close. And remember all the times I've said it's approximately this, or about a certain percent of the data is less than or equal to. When you've got data, the best you can do is just approximates or abouts. If you got the entire population, you can get exact. Next example, find the quartiles of a data set. So we got two data sets. We got data set A and data set B. We can use the approximation method. There's the quartile. There's the median, second quartile, 70.5. Q1 and Q3 can be estimated, 65 and 78. So 3 of the 5 number summary is going to be 65, 70.5, and 78. Using this second set of data, again, we start with the median, go through the exact same calculations to get estimated values. So 3 of the 5 numbers for the B data set are 67, 75, and 79. Of course, we can use R to do these rather quickly, give it the data, do summary of that data set, and this will give you the first and third quartiles. It'll give you the median. It also gives you the min and the max, which are the other 2 numbers in the 5 number summary, and it will also give you a mean. Know that these values are not the same as those received when the approximation method is used. So which is correct? They both are. Because remember, medians don't have to be unique. And that extends to all the quartiles and percentiles. They don't have to be unique. Oops, red star. Question 2, again, write this over on the left-hand side, answer it beneath. How do percentiles and quartiles differ? Hit pause, and we're back. 5-number summary and box plots. 5-number summary consists of the 5 quartiles, the minimum value, which is Q0, first quartile, which is Q1, second quartile, which is Q2, third quartile, Q3, and the maximum, which is Q4. 5-number summary is made up of these 5 numbers listed in order from smallest to largest. Why do we need the 5-number summary? Well, it gives us a good feel for the distribution of the data. So write the 5-number summary for the data in example 3.2. We've calculated the quartiles already. All we have to do is figure out what the minimum, 12.1, and the maximum, 35.9, values are. And there's our 5-number summary. Minimum, Q1, Q2, Q3, maximum. We are going to illustrate the 5-number summary using a box plot. Technically, it's called a box and whiskers plot. Box and whiskers plot, in this case, it's a horizontal box and whiskers plot. It looks like this. It specifies what the minimum value and the maximum values are. Those are the endpoints of the whiskers. And the box endpoints are Q1 and Q3. And the median is indicated by a thick line inside that box. The range between Q1 and Q3 is called the interquartile range. It's just Q3 minus Q1. It's a single number. About half the data occurs inside the box. About a quarter of the data occurs above the box, and about a quarter occurs below. And this is what I just said. Here's the actual formula for the interquartile range. It's Q3 minus Q1. Here's how we create the box plot. We're going to begin with the 5-number summary. We're going to determine a nice little scale horizontal axis that fits all those values nicely. We're now going to mark those 5 numbers on the graphic. The minimum, Q1, Q2, Q3, the maximum. We're going to draw the box in Q1 to Q3, a thick horizontal vertical line at the median, and then we show the whiskers going out for the box to the min and the max. We can do this in R with the box plot command, load in the data, and just apply box plot to the data. If you want something that looks like this graphic, you have to specify horizontal equals true. A vertical box plot is the default, and the color is orange. COL for color, and that will color the box. It's a lot faster and a lot more accurate than doing it by hand. We're going to interpret box plots now. We have 4 subbasins. We got the Upper Mississippi, the Ohio, Tennessee, the Missouri, and the Arkansas Red River subbasins. Notice this is not a typical box plot because the top whisker and the bottom whisker are at 90th percentile and the 10th percentile, which we see over here. We also see the mean as a dot. That will help us see the skew of the data set. So for instance, Missouri seems to be skewed up because the mean is above the median. The Upper Mississippi and the Ohio, Tennessee seem to be rather symmetric, and the Arkansas Red River seems to be skewed up as well. So here are the questions. What did the top and bottom bars represent in these box plots according to the key? They represent the 90th and the 10th percentiles. Which subbasin had the highest median average? Highest median average. The median is the solid horizontal line, so it looks like it's the Missouri. Which subbasin had the lowest average spring? Lowest average. So it looks like the lowest average is going to be the Ohio, Tennessee. If we're looking at the average, it looks like that's going to be lower than the Arkansas Red River. If we're looking at the medians, however, the Arkansas Red River is definitely below the Ohio, Tennessee. And which subbasin had the largest interquartile range? In other words, which subbasin had the largest spread to the data? That's clearly Missouri, because the box is the largest of all the other three. Last topic today is our z-scores, or our standard scores. When we can compare two data values from two completely different populations by comparing their relative or their respective percentiles. We can also determine how the values relate to the respective means of their data sets. Z-scores do this latter. It's called the standard score or the z-score. Again, we're going to see the z-score pop up in chapter 6, 7, 8, 9, 10, 11, 12. The standard score tells us how far a value is from the mean, specifically how many standard deviations it is from the mean. The formula for the population standard score, that is, if you are given the population mean and standard deviation, it's just the value you have minus the population mean divided by the population standard deviation. For the sample standard score, it's x minus x bar, the sample mean, divided by s, which is the sample standard deviation. So it's always x minus a mean divided by a standard deviation. Example, mean score in the math section of the SAT test is 500 with a standard deviation of 150. What is the standard score for a student who scored 630? So 630 is x, 500 is mu, and 150 is sigma. So the z is just going to be 630 minus 500 divided by 150. So a person who scored 500 on the SAT, a person who scored 630 on an SAT has a z-score of 0.87. In other words, this student's test score is about 0.87 standard deviations above the mean. Jody scored an 87 on her calculus test and was bragging to her best friend about how well she'd done. Poor Jody. She said that her class had a mean of 80 and a standard deviation of 5. Therefore, she had done better than the class average, which is true. Jody got an 87. The average was 80, so definitely above. Her best friend Ashley was disappointed. She'd scored only an 82 on her calculus test. However, the mean for her class was 73 with a standard deviation of 6. So who really did better on her test? Jody or Ashley? And we're going to do this compared to the rest of the class. So Jody's z-score is 87 minus 80 divided by 5. And Ashley's will be 82 minus 73 divided by 6. So for Jody, it's 1.4. For Ashley, it's 1.5. Thus, compared to everyone else in the class, Ashley actually did better. Compared to everybody else in the class, Ashley actually did better. Ashley's score was actually 1.5 standard deviations above average, whereas Jody's score was only 1.4 standard deviations above average. Here we are calculating z-scores using R. Let's go back to the A. Let's calculate the z-score corresponding to our first value. Now there is no z-score function native to R, but sourcing this file will give us one. We just give it the data and we specify z-score of the data, and then in brackets, which data value do you want to get the z-score for? If we want to get the first z-score, we put a 1 in brackets. If we leave the brackets off completely and just have z-score of A, then we get all the z-scores. The output for this tells us that the first value has a z-score of negative 1.47196. Thus, it is about 1.47 standard deviations below average. About 1.5 standard deviations below average. Below because the z-score is negative. Below average because all z-scores are done with respect to average. If the z-score is 0, then that person scored average. Yeah, there's one more question. Question 3. I must have missed the red star. Again, write the question in your notes on the left, answer it below. When should one use a box plot instead of a histogram? This one's going to take you some thought. Think about what the histogram tells you. Think about what the box plot tells you. Think about the examples that we gave in this lecture for box plots. Spend some time, this is the last part of this lecture, by the way. Spend some time thinking about the strengths of histograms, the strengths of box plots. And now, when should a box plot be used instead of a histogram? Go ahead and hit pause, but we are done. And so that's the end of Chapter 3. In Chapter 3, we're now summarizing our data using numbers. In Chapter 2, we summarized our data using graphics. Chapter 3, it's using numbers. We had several important numbers that we looked at. The mean, the median, the mode, standard deviation, the interquartile range. We also looked at measures of position, the z-score. Don't forget the empirical rule and Chebyshev's theorem. Although you could forget Chebyshev's theorem and life would go on. The empirical rule is actually very important, as is the z-score. Understanding both of those will help us when we get to Chapter 7. And that's it. Hopefully this was helpful. Hello and welcome to Section 4.1. This will be the first section of the Chapter 4. Purpose of Chapter 4 is to introduce you to probability theory. The vast majority of Chapter 4 is going to be review. It's going to be a review of stuff that you learned back in middle school and high school. There are no intra-lecture questions posted. However, there are quizzes in Moodle. So the answers for the Moodle quizzes for each of these Chapter 4 sections will be not in the lecture. Got it? You write not in the lecture for each of those, you get full credit. If you don't write it, you don't get full credit. So the objectives for Section 4.1: identify the sample space of a probability event, calculate basic probabilities, determine if two events are mutually exclusive, and determine if two events are independent. Mutually exclusive and independent are two things that you're going to need to be very careful of. There's a lot of confusion between the two. If two events are mutually exclusive, then both cannot happen at the same time. If two events are independent, then having one happen doesn't affect the other. So here's some terminology. A probability experiment or a trial is a process with a result determined by chance, such as flipping a coin. Each individual result that is possible for a probability experiment is an outcome. So there are two outcomes for the coin flipping. Outcome 1 is a head, outcome 2 is a tail. The sample space is the set of all possible outcomes for any given probability experiment. Therefore, the sample space is heads and tails, or heads comma tails. An event is a subset of outcomes from a sample space. So an event could be just head. An event could be just tail. An event could be head or tail. Or an event here could be none of the above. Examples of probability experiments include flipping a coin, tossing a pair of die, drawing a raffle ticket. Those are the basics. In each of these examples, there is more than one possible result, and the result is determined at random. Example 4.1. Consider an experiment in which a coin is tossed, and then a six-sided die is rolled. So A, we need to list the outcomes of the sample space for the experiment. See, coin toss, then six-sided die is rolled. Okay. List the outcomes in the event: tossing a tail, then rolling an odd number. Okay. So here are the solutions. Each outcome consists of a coin toss and a die roll. For example, you can get a head and then a 3. We're going to denote a head followed by a 3 as H3. Using this notation, we've got 12 outcomes, 12 possible outcomes. And the set of those 12 possible outcomes is going to be the sample space. You can get a head and then a 1, a head and then a 2, a head then a 3, ... a tail then a 5, then a tail and a 6. It's 2 times 6 possible outcomes. So the sample space is just those 12 possible outcomes. So B, we're going to choose the members of the sample space that fit the event, quote, tossing a tail, then rolling an odd number. Tossing a tail and then rolling an odd number. There's only 3 odd numbers, 1, 3, and 5. So the 3 possible outcomes of this sample space are T1, T3, T5. Next example. Let's consider the experiment in which a red 6-sided die and a blue 6-sided die are rolled together. Use a pattern to help list the outcomes in the sample space. List the outcomes in the event. The sum of the numbers rolled on the 2 dice equals 6. Okay, many patterns that we could use. This is one that they're looking at. Why would we use a quote pattern here instead of listing all of them out? There's 36 possible outcomes. 6 for the first, 6 for the second. 6 times 6 gives us 36. Then we'd have to list out 36 outcomes for the entire sample space. Here, we can just give a pattern for what they're going to be. Or we can list them all out if we'd like to have these drawings. Notice the sample space is 1 and 1, 2 and 1, 3 and 1, 4 and 1, 5 and 1, 6 and 1, etc. If all we care about is the sum of the numbers that come up, then the sample space would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because 2 through 12 is the sums. Now keep the sample space in mind. Note that rolling a 1 on the red die and a 2 on the blue die is different than rolling a 2 and a 1 if we care about the actual outcomes. However, if we care about just the sum, then those two are going to be identical outcomes. Part B, we're going to list the outcomes of the event, quote, the sum of the numbers rolled on the 2 dice equals 6. So we're going to go back and look to see there's one here, 5, 1, 4, 2, 3, 3, 2, 4, 1, 5. Those all give us a sum of 6. So we could actually say the probability of getting a 6 when rolling 2 dice is 6, 1, 2, 3, 4, 5. Sorry, it's 5. 1, 2, 3, 4, 5. 5 out of 36. A tree diagram can be used to represent the outcomes of an experiment, especially in the early phases when you're just trying to learn why it's 6 times 6 instead of 6 plus 6. The tree begins with the possible outcomes of the first stage and then branches for each additional possibility. We're going to see tree diagrams in the future, so it would be good to be able to write these out eventually. The number of possibilities in the bottom row of the tree is equal to the number of outcomes in the sample space. So let's consider a family with 3 children. Use a tree diagram to find the sample space for the gender of each child in regard to birth order. So again, ordering here does matter. We're doing it oldest, middle, youngest. So here it is. The first child can either be a girl or a boy. Second can be girl, boy, or girl and boy. And then girl, boy, girl, boy, girl, boy, girl, boy. So the bottom here, GGG, would indicate that all 3 children were girls. GGB would be a girl, girl, followed by a boy. GBG would be a girl, then a boy, then a girl. Notice that this looks like a tree, especially if you turn it upside down. And so using this tree diagram as a guide, we can see that there's going to be 8 outcomes. 2 times 2 times 2. 3 children, so 2 to the power of 3. And now let's look at 3 methods for calculating the probability of an outcome. This is also usually thought of in terms of three ways of understanding probability. There's subjective, the experimental, and there's classical. What we've used so far is classical. What the course is going to be using in the future will be mostly experimental. Sometimes it's called frequency probability, or sometimes relative frequency probability. In a future course, subjective probability will be renamed Bayesian probability, and we'll see that subjective probability is actually the most useful of the three. But that's for a future course way down the line. Subjective probability, according to Hawks, is simply an educated guess regarding the chance that an event will occur. This is Hawks. This is not reality, but you won't understand the reality until you get into a future stat course. And again, subjective probability or Bayesian probability will be the most useful. But we're not there yet. Experimental probability or relative frequency probability talks about using data to estimate a probability in an event. So if E is an event, then P of E, the probability that E occurs, is given by F over N, where F is the frequency and N is the total number of times the experiment is performed. So if I want to estimate or find the probability of randomly selecting a sophomore from campus, I could ask 500 people on campus if they're a sophomore, and of those 500, 295 said they are a sophomore. N would be 500, the number of people I asked, and therefore I would estimate the probability of a sophomore being 295 over 500. And that's going to be the cornerstone. This experimental probability or this relative frequency probability will be the cornerstone of the second half of the course. Mainly because the classical probability very quickly the classical probability very quickly will become useless. We don't know the actual probability of selecting a student who is a sophomore, so we just have to estimate it. And that estimation and the using of the estimated probabilities is this experimental probability. The benefit or the theoretical background that we can use the experimental probability is called the law of large numbers. As the sample size increases, the proportion or the means of your sample approaches the means or the proportions of the population. And then classical probability, if all outcomes are equally likely, and this is actually a very important requirement that the outcomes are equally likely, then the probability of E is equal to the number of elements in the E divided by the number of elements in the sample space. Hence, when we were talking about what's the probability of getting a 6 when rolling 2 die, and by getting a 6 I mean adding up the dice together, of getting it was just 5, the number of ways of the dice adding up to 6, divided by 36, the possible number of outcomes. Example 4 is identifying the types of probability. Determine whether each probability is subjective, experimental, or classical. Again, experimental is also referred to as relative frequency or just as frequentist. Classical is also referred to as axiomatic. AXIOMATIC. Probability of selecting the queen of spades out of a well-shuffled standard deck of cards is 1 over 52. That's clearly classical. There's only one queen of spades out of the 52 cards in the deck. We know this. We don't have to estimate it. We're not guessing at it. An economist predicts a 20% chance that technology stocks will decrease in value over the next year. From the information given, that will be subjective, although this economist may have used data to come up with that, in which case it would be experimental. Police officer wishes to know the probability that a driver chosen at random will be driving under the influence on a Friday night. So he records the number of drivers at a roadblock, the number of drivers drinking with blood alcohol levels over the legal limit. He determines the probability is 3%. That is very clearly a relative frequency or an experimental probability because it's based on the experiment that he performed. We just discussed that. Beck is allergic to peanuts for the next example. Poor Beck. At a large dinner party one evening, he notices that the cheesecake options on the dessert table contain the following flavors: 10 slices of chocolate, 12 slices of caramel, 12 slices of peanut butter chocolate, and 8 slices of strawberry. Assuming that the desserts are served to a guest at random, what's the probability that Beck's cheesecake contains peanuts? It's 12 divided by 10 plus 12 plus 12 plus 8. And what's the probability that Beck's dessert does not contain chocolate? That's going to be 12 plus 8 divided by 10 plus 12 plus 12 plus 8. In the first case, it's because 12 of those, the numerator 12, contain peanut butter. And in the second case, it's a numerator of 12 plus 8 does not contain chocolate. However, were I Beck, I wouldn't eat cheesecake at all because even a 28% chance, it's not worth it. Consider a beginning archer who only manages to hit the target half the time. What's the probability that in 3 shots, the archer will hit the target all 3 times? That's going to be 1 over 8, or 12.5%. Here's why. Each time, she has a 50% chance of hitting the target. So 50% chance to hit the first time, 50 the second, 50 the third. To hit it all 3 times, it's got to hit it the first, and the second, and the third time. Here's the tree diagram. Notice in only one of these 8 cases does she hit the target all 3 times. So it's 1 over 8, or 12.5%. Consider a family with 6 boys. What's the probability that the 7th child will also be a boy? Okay. Families due to have a girl, but reality states just the opposite. If you've got 6 boys, it's more likely that you'll have a 7th boy. However, we're supposed to pretend that each time it's a 50% chance of getting a boy or a girl. So you got 6 boys followed by a girl, or 6 boys followed by a boy. Of these, 1 out of the 2 is a boy, so a 50% chance. Again, this assumes that the outcomes are equally likely. The reality is that if you've had 6 boys, it's more likely that you'll have a 7th boy. It's not 50% chance. And also, even on your first child, it's not a 50% chance that you'll have a boy. It's actually a less than 50% chance that you'll have a boy. It's a 49-point-something% chance. But we're simplifying things here so that because we can multiply by half very easily. In biology, we learn that many diseases are genetic. One example of such is Huntington's disease, which causes a neurological disorder as person ages. Each person has 2 Huntington genes, one inherited from each parent. If the individual inherits a mutated Huntington gene from either of his or her parents, that person will develop the disease. Notice it's from either of the parents. TV show House, the character who Dr. House calls 13, inherited the disease from her mother. So if 13 has a child with a person who has 2 healthy Huntington disease, what's the probability your child will develop Huntington's? Quite simply, the answer is going to be 1/2. Because going to get a good gene from the parent, from the father, and a bad gene from her, 50%. And that's it for section 4.1. Remember, go to Moodle, take the quiz, and for each of your answers, write something like, this was not asked in the lecture. And that's it. Hope you all have a good day. Hello and welcome to section 4.5, where we're learning about the addition rules of probability. In other words, we're looking at probability of the union of two events. So we're going to use addition rules to calculate probability. That's the objective for today. There are three properties of probability. For any event, E is going to be our generic event. The probability of E is going to be between 0 and 1 inclusive. For any sample space, the generic sample spaces can be a cursive S. The probability of being an element of that sample space is 1, because remember the sample space is a set of all possible outcomes. And 3, for an empty set, the probability of empty set is 0. So the probability of nothing happening is 0. The complement is a very important concept that you're going to be using in Chapter 5. Chapter 4 really only has two concepts that are extremely important. One is complement. The other is going to be the concept of independence. Independence we're going to be using in Chapter 11, but complement we're going to be using quite a bit in Chapters 5 and 6. The complement of an event E is denoted as E to the power of C. It's not really to a power of, it's just superscripted C. In some sources this will be a prime. In some sources it'll be bar over the E. I like the C. It's pretty nice. The complement of E is the set of all outcomes that are not in E. So describe the complement of each of the following events. A red card out of a standard deck of cards. The event is choose a red card, so the complement will be choose a not red card, which means the complement is going to be choose a black card out of a standard deck of cards. Pardon me. Out of 31 students in your stat class, 15 are out sick with the flu. So the event E is being out sick with the flu. The complement of E is going to be not being out sick with the flu. So in this case, E complement will be able to attend class or not being sick. In your area, 91% of phone customers use phone south. So the event is customer using phone south. The complement will be customer not using phone south. So the complement E complement will be customer using something other than phone south. And that's what all of the solutions tell us. The complement rule for probability, and this is the most important part, is that the probability of an event plus the probability of its complement is 1. This is kind of like put a star next to it in your notes, circle it, happy face around it, because this we're going to be using a lot in Chapter 5. For some problems, and this is actually why we're going to use it a lot in Chapter 5, for some problems the probability of a complement is much easier to calculate than the probability of the event itself. This is especially true when you're dealing with infinite sets or infinite sample spaces. For these problems you can calculate the probability of the complement and subtract that value from 1. Here's an example. You're worried that there is a 35% chance that you'll fail your upcoming test. What's the probability that you will pass the test? It's going to be the complement of failing, so it's going to be 1 minus 35%. If there's a 5% chance that none of the items on a scratch-off will be a winner, what's the probability that at least one will win? Well, at least 1 means the probability of a 1 or a 0. I'm sorry. At least 1, that's the probability of a 1, a 2, a 3, a 4, a 5, all the way up there. So that's going to be 1 minus the probability of a 0. So here's the solution for the first. 65%, pretty straightforward. The second is much more complicated. Probability of at least one winner is 1 minus the probability of no winners. And we're told the probability of no winners is 5%. Which means that the probability of at least one is going to be 95%. And I do want to emphasize here, make sure you understand that no winners and at least one winners are complementary events. So pause until you understand that. Roll a pair of standard 6-sided dice. What is the probability that neither die is a 3? That's going to be pretty straightforward to calculate if you use complements. If you do it brute force, then you're going to have to list out all 36 possibilities and determine how many of those neither has a 3. Or we can just use complements. So these are the outcomes that have a 3. Remember, E is not having a 3, so E complement will be having a 3. So there are 11 elements in E complement, so the probability of being an E complement is 11 over 36. Therefore, the probability of being an E is 25 over 36. Which is about 70%. So you have about a 70% chance of rolling 2 dice and not getting a 3 on either one. The addition rules for probability. This is the addition rule for probability. There is a simplification to it that may be useful or may be allowed, but this is the rule. And the probability of, given two events, the probability of being in event E or in event F, or both, is just the probability of being in E plus the probability of being in F minus the probability of being in both. Cerise is looking for a new condo to rent. Her realtor provided with the following list of amenities for 17 available properties. There's the list. Close to the subway was 6. 7 were low maintenance fee. 5 had green space. 2 were newly renovated. Close to the subway and low maintenance were 2. So 1 and 2, there were 2 in that, which meant that there were, green space and newly renovated was just 1. If Cerise's realtor selects the first condo they visit at random, what's the probability the property is either close to a subway or has a low maintenance fee? Close to a subway we'll call E, low maintenance fee we'll call F. So let's verify that the realtor has accurately counted the total number of properties. Remember, there were 17 properties. 6 were of type 1, 7 were of type 2, 5 were of type 3, 2 were of type 4, which gave us 20, but we know that there is a overlap of 3. And we were told what this overlap was. 2 are both low maintenance and close to a subway, and 1 is both newly renovated and green spaced. So 17 individual properties. We're going to use the OR. That tells us we'll be using the addition rule. E or F. That's equal to probability of E plus a probability of F minus the probability of both. There are 16 that are close to a subway, 7 that are low fee, and we're also told that 2 are both. So 6 plus 7 minus 2 is 11, so about a 64% chance. Suppose that after a vote in the U.S. Senate on a proposed health care bill, the following table shows the breakdown of the votes by party. 23 versus 21, 43 versus 7, 2 versus 4. If a lobbyist stops a random senator after the vote, what's the probability the senator will be either a Republican or voted against the bill? So either a Republican or voted against the bill. That's just going to equal the probability of it being a Republican, 50, plus the probability of voting against the bill, 32, minus the 7 that were counted twice, divided by 100 or whatever. Republican voted against the bill, counted twice, gives us a 75% chance the lobbyist will have dinner with the senator he wants. roll a pair of dice. What's the probability of rolling either a total less than 4 or a total equal to 10? Total less than 4 will be E. Total equal to 10 will be F. We want the probability of E or F. That's just the probability of E plus the probability of F minus the probability of E and F. Less than 4 plus the probability of 10 minus the probability of less than 4 and 10. Well, what's the probability of it being both less than 4 and equal to 10? Well, that's 0 because this is the empty set. And from our 3 requirements for probability, that means that this probability is equal to 0. And we just pay attention to the first two. In other words, less than 4 and 10 are mutually exclusive events. One can happen, the other could happen, but both cannot happen. So there's 3 that are less than 4, there's 3 that are 10, so it's going to be 6 out of 36. Again, the key, these two events are mutually exclusive, and that leads to a 0% chance of both occurring. If events E and F are mutually exclusive, then the addition rule is much easier. And apparently Hawks didn't give us the formula. It's just the probability of E plus the probability of F. There's no need to subtract off anything because what you're subtracting off is just 0. Caleb is very excited that it's finally time to purchase his first new car. After much thought, he's narrowed his choices down to 4. Because it's taken him so long to make up his mind, his friends have started to bet on which car he will choose. They've given each car a probability based on how likely they think Caleb is to choose that car. Devin's betting that Caleb will choose either a Toyota or a Jeep. Find the probability that Devin's right. And here's the probabilities that they've assigned. Probability of a Toyota or a Jeep. It's just going to be the probability of a Toyota plus the probability of a Jeep minus the probability of a Toyota and a Jeep. But that probability of both is 0 because he's purchasing his first new car. Only one car. So Devin has a 75% chance of correctly picking which car Caleb will buy. Example 416, we're going to extend the addition rule to more than just 2 events. We got these probabilities, and we're asked what's the probability that the driver will refuel at Shell, Exxon, or Chevron. Shell, Exxon, or Chevron. These are mutually exclusive events, therefore the probability is just going to be the sum of the individual probabilities. The probability of the union is the sum of the probabilities, if the events are mutually exclusive. And that's the end for section 4.2. Again, don't forget to complete the quiz in Moodle, and for each of the questions, write something like, "This was not covered on the lecture." And that's it. Take care. Hello and welcome to section 4.3. This is the third section in chapter 4, probability theory. Here we're looking at the multiplication rules for probability, which eventually will lead to conditional probability and independence. So we're going to use multiplication rules to calculate probability. Multi-stage experiment is an experiment with 2 or more steps or stages. We've seen examples of this. The roll the die and then flip a coin is a multi-stage experiment. The flipping the coin 3 times is a multi-stage experiment. That's a 3-stage experiment. An experiment performed with replacement refers to placing an object back into consideration before performing the next stage of the experiment. Those examples I just gave you were, quote, with replacement because you could end up with, actually the first one with roll the die and then flip a coin is not with experiment because once you roll the die you can't get a 1, 2, 3, 4, 5, or 6 for the second term. We did have an earlier example of probability of getting a queen of spades, if all we're doing is drawing one card, then we don't need to talk about with or without replacement. But if we're talking about drawing two cards, what's the probability that either one is a queen of spades? Well, now we got to think about, am I putting the first card back after I draw the first card, or do I keep that first card in my hand? If I put the card back, it's with replacement. And the calculations tend to be a little bit easier when you're doing things with replacement. If I hold on to that first card, then it's without replacement. And the calculations get a little bit more difficult, not too much. Two events are independent if one event happening does not influence the probability of the other event happening. So that's independent. Multiplication rule for probability of independent events, and I want to emphasize this is for independent events right now. If E and F are independent, then the probability of E and F occurring is equal to the probability of E times the probability of F. That's it. Suppose two cards from a standard deck. I choose two cards from a standard deck with replacement. That means I draw a card, look at it, put the card back, reshuffle, draw a second card. What's the probability of choosing a king and then a queen? Well, since I put the card back, the outcome of the first doesn't impact the outcome of the second draw. So these are going to be two independent events. So it's just going to be the probability of choosing a king times the probability of choosing a queen. So that's going to be 4 out of 52 times 4 out of 52, or 1/13 times 1/13, which is about 0.6% chance. Assume that a study by Human Resources has found that the probabilities of an employee being written up for the following infractions are the values shown in the following table. So this is probability of being written up at work. And we're going to assume that each infraction is independent of the others. This is given information to us. We would have to know that they're independent. We can't just look at the problem and understand, hey, they're independent. We have to be told they're independent. What's the probability that a given employee will be written up for being late to work, taking unauthorized breaks, and leaving early? Late to work, unauthorized breaks, and leaving early. So we're looking at the probability of late to work and unauthorized breaks and leaving early. So it's just the product of those three probabilities because these are independent events. So about 1% chance. Said a different way, about 1% of the people at that company get written up for being late to work, taking unauthorized breaks, and leaving early. That seems rather high to me. An experiment performed without replacement means that the objects are not placed back into consideration. That means that the two draws are going to be dependent, most likely. Two events are dependent if one event happening affects the probability of the other event happening. So we're looking back at our king and queen example. We want to know the probability of drawing a king and then a queen if the cards are drawn without replacement. So this is going to be a good one. The situation is essentially the same as drawing two cards from a standard deck. So instead of thinking of it as draw one card and then draw the other, you can think of this as just drawing two cards. And you're asking what's the probability of the first card I drew being a king and the second being a queen. By determining the probability of drawing a king from a standard deck of cards. Begin by doing that. It's just 1 out of 13. Now, let's assume that when I drew the first card, it was a king. So given the first card is a king, what's the probability that the second one is a queen? Well, there's 4 queens in the deck, but the deck only has 51 cards left in it. Because I didn't put that king back. There's only 51 cards left in the deck. Thus, the probability of a queen, given that the king was drawn first, without replacement, is 4 out of 51. So the probability of getting a king and then a queen is just going to be the product of about 0.06. I'm sorry, by about 0.6%. Now what we've actually done is we've started talking about conditional probability without telling you that we're talking about conditional probability. Here's the key that this is conditional probability. It's the word given. Conditional probability, denoted by probability of f given e, that vertical bar is read as, quote, given, is a probability of event f occurring given that the event e occurs first. If event e and f are independent, then the probability of f given e is just probability of f, which leads to a nice definition of independence for us. One card's already been chosen from a standard deck without replacement. What's the probability of now choosing a second card and it being red, given the first card was a diamond? So we're asked, what's the probability of the second being red, given the first was a diamond? Red given diamond is just 25 over 51, because we didn't put the card back. There's only 25 cards that are red when the first card was a diamond, which is also red, by the way. So now here's the actual multiplication rule for probability. Given two events, E and F, the probability of E and F occurring is just the probability of E times the probability of F given E, which is identical to the probability of F times the probability of E given F. These two formulas are exactly the same. The one you use depends on the data that's given to you. So it's the probability of choosing two face cards in a row. We're going to assume the cards are chosen without replacement. Here we're dealing with dependent events, so we use the multiplication rule. When the first card is picked, all 12 face cards are available out of 52, so the probability of the first one is a face card is 12 out of 52. Now, given that the first one is a face card, then there's only 11 left that are face cards out of the 51 cards remaining in the deck. So the total probability will be 12 over 52 times 11 over 51, which is about a 5% chance. Assume that there are 17 men, 24 women in the Rotary Club. 2 members are chosen at random each year to serve on the scholarship committee. What's the probability of choosing 2 members at random, the first being a man and the second being a woman? We're choosing 2 members. The first choice will influence the probability of the second. There's 41 people altogether. So the probability of a man and a woman is just the probability of a man times the probability of a woman, given the first was a man. Probability of man is 17 out of 41. So given the first one was a man, the probability of the second one being a woman is just 24 out of 40. It's 24 because there's 24 women in the Rotary Club. It's 40 because there are 40 that are remaining after the first one was chosen. So there's about a 1/4 chance. We can also write conditional probability, and this is sometimes referred to as the definition of conditional probability. The probability of F given E is the probability of E and F divided by the probability of E. If E and F are independent, then the probability of E and F is just the probability of E times the probability of F. The probability of E's cancel out, so we're given the probability of F given E is just equal to the probability of F. And that's a very nice definition of independence. Out of 300 applicants for a job, 212 are female and 110 are female and have a graduate degree. What's the probability that a randomly chosen applicant has a graduate degree given she's female? So now we're told the person we got is female. What's the probability that she has a graduate degree? 212 female, 110 female graduate degree, so this probability is just going to be 110 over 212. If 152 of the applicants have graduate degrees, what's the probability that a randomly chosen applicant is female, given the applicant has a graduate degree? 152 is the denominator. 110 is the numerator. So the probability is just going to be 110 over 152. The key is female and graduate degree divided by female. Female and graduate degree divided by graduate degree. The emphasis here is that probability of F given E is not necessarily the same as probability of E given F. Order matters with conditional probability. The reason order matters is you're given different information. Probability of F given E, you're given that E is true and you need to calculate the probability of F. Whereas in probability of E given F, you're given F is true and you need to calculate a completely different probability of E. And now for the fundamental counting principle. For a multi-stage experiment with n stages, where the first stage has k1 outcomes, the second stage has k2 outcomes, the third stage has k3 outcomes, and so on, the total number of possible outcomes is k1 times k2 times k3 times ... times kn. We've already seen this. With the roll a die, then flip a coin, k1 was 6, k2 was 2, the total number of outcomes was 12. 6 times 2. Flipping the coin 3 times, k1 was 2, k2 was 2, k3 was 2, 2 times 2 times 2 was 8. There were 8 possible outcomes. Rolling 2 dice, k1 was 6, k2 was 6, 6 times 6 is 36. There were 36 possible outcomes. So we've already experienced this, we're just giving a nice name for it. Kilby begins her first year in an online degree program in July. The first semester she will randomly be assigned to one section for each of 4 different core courses. If there are 8 English 1 sections, 12 college algebra sections, 11 American history sections, and 5 phys ed, physical science sections, how many different options are there for Kilby's schedule for her first semester? Well, it's just 8 times 12 times 11 times 5 from the fundamental counting principle. $52.80. The governing board at a local charity, Mission Stateville, is electing a new vice president and secretary to replace outgoing board members. If the board consists of 11 members who don't already hold an office, how many different ways can the 2 positions be filled if no one may hold more than 1 office? Go ahead and hit pause to figure this out. And you're back. 2 slots to fill. It's going to be without replacement because you can't hold both offices. There are 11 choices for the first position, 10 choices for the second. That leaves 110 possible ways to elect the new officers. Example, Robin is preparing an afternoon snack for her twins, Matthew and Lainey. She wants to give each child 1 item. She has the following snacks on hand: carrots, raisins, crackers, grapes, apples, yogurt, and granola bars. If she randomly chooses 1 snack for Matthew and 1 snack for Lainey, what's the probability each child gets the same snack as yesterday? Here's the solution. You probably want to hit pause to come up with the solution yourself before you read the solution here. You need to count the number of ways in which Robin can randomly choose a snack for her twins. Again, we can think of this as 2 slots to fill, 1 for each twin. 7 possibilities for each child. There's no requirement that the twins have different snacks, or conversely have the same snack, so the total number of ways she can prepare the snacks is 7 times 7. Now we need to count the number of ways that she can choose the same afternoon snack as yesterday. there's only one thing they had yesterday. So the probability is just going to be 1 divided by the 49 total number of snacks. So about 2% chance. And that's it. Thank you very much. Hello and welcome to section 4.4. This is the fourth section of chapter 4. We're going to look at combinations and permutations. These are just functions that allow you to quickly calculate total number of possible outcomes. So the objective, calculate numbers of permutations and combinations. Before we get to that, we have to define what a factorial is. A factorial of n, a positive integer, denoted by n exclamation point, or called n factorial, is just the product of n times n minus 1 times n minus 2 all the way down to 1. So 1 factorial is equal to 1, 2 factorial is equal to 2 times 1, or 2, 3 factorial is equal to 3 times 2 times 1, which is 6. By agreement, 0 factorial is equal to 1. You might want to be careful on that one. So let's calculate the following factorial expressions. A is 7 factorial. That's just going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. B is 4 factorial over 0 factorial. That's numerator is going to be 4 times 3 times 2 times 1. Denominator is going to be just 1. C, 95 factorial over 93 factorial. That's just going to be 95 times 94. Why? Because 95 factorial is equal to 95 times 94 times 93 factorial. And then you're dividing off by that 93 factorial, so you're left with just 95 times 94. D, the numerator is going to be 5 times 4 times 3 times 2 times 1. Denominator, well, 5 minus 3 is 2, so denominator is just going to be 2 times 1, 2 factorial. E, numerator is going to be 6 times 5 times 4 times 3 times 2 times 1. Denominator is going to be 2 times 1 times 4 times 3 times 2 times 1, because 6 minus 2 is 4. So 7 factorial is 5040. 4 factorial over 0 factorial is 24. 95 factorial divided by 93 factorial is 95 times 94. Five factorial over 2 factorial is just 60. And 6 factorial over 2 factorial times 4 factorial is 15. Now we're going to define the difference between a combination and a permutation. Let's do with permutation first. A permutation is a selection of objects from a group where the arrangement matters. Combination, the arrangement doesn't matter. So an example when you would use a permutation is you want to select a president, vice president, secretary from a group of people. The actual positions are named and they matter. Combination would be I want to select a group of 3 people from a larger class of 50. I'm just selecting 3 people in this group by not naming the positions. It's just 3. So the arrangement matters, that leads to permutations. The arrangement is irrelevant, that leads to a combination. So the calculations are very similar-ish. When order is not important, the following formula is used to calculate the number of combinations. It's NCR, or N choose R, is just N factorial, the larger number, divided by R factorial times N minus R factorial. So if I want to choose a group of 3 people out of our class of 30, N is 30, R is 3. So it'll be 30 factorial divided by 3 factorial times 27 factorial. When the order is important, the following formula is used to calculate the number of permutations. So if I want to choose a president, vice president, and secretary from our class of 30, N's again going to be 30, R again is going to be 3, but the number of permutations is just n factorial over 27 factorial. Notice the number of combinations cannot be larger than the number of permutations, and the number of combinations will be equal only when r is equal to 1 or 0. In other words, when r is 1 or 0, order is not important versus order is important. That means the same thing because there's only one or no position to fill. It's like choosing a president from our class of 30. Whether or not the order matters within that one position, it's not a question to ask because there's only that one position. Given a group of 3 friends, how many ways can you arrange the way that they stand in line for the movies? Standing in line matters, the order matters in that. So it'll be 3 factorial divided by 3 minus 3 factorial. How many ways can I choose 2 of them to ride in a car together? I'm just choosing 2. I'm not saying one gets shotgun, the other doesn't. I'm just choosing 2. So A is going to be permutations, B will be combinations. That'll be 3 choose 2. So there are 6 ways that they can stand in line. Here's the actual listing of those 6 ways. As for the second part, we're just choosing 2 from a group of 3, so it's called 3 choose 2. 3 factorial, 2 factorial, and then 3 minus 2 factorial. So you can also think of this as the total number of people, factorial, divided by the number of people in the group you care about, factorial, times the number of people in the rest of the group. We start with 3 friends, we want 2 in the car, this is what's not in the car. And here are the possible options for who gets to ride. Class of 18 fifth graders is holding elections for class president, vice president, and secretary. How many different ways can the officers be elected? Since we've actually named these positions, this is going to be permutations. R is 3, N is 18. It's almost 5,000 ways. Consider that a cafeteria is serving the following vegetables: carrots, green beans, lima beans, celery, corn, broccoli, and spinach. Bill wishes to order a vegetable plate with 3 different vegetables. How many ways can this plate be prepared? Well, this is one where order doesn't matter. So it's going to be 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7 will be N. 3 will be R. So this will be 7 choose 3. $35. Suppose that a Little League baseball coach is randomly listing the 9 starting baseball players in batting order for their second game. At this level, the batting order is randomly chosen to give all players an opportunity to experience different batting positions. What's the probability that the order chosen for the second game is exactly the same as that of the first game? Since we're focusing on the order itself, this will be permutations. N and R are both 9. And we're looking at the probability, so the denominator is going to be N permute 9. 9 permute 9, and the numerator is going to be 1 because there was only one ordering that we had yesterday. Nine permute 9 is equal to 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 9 factorial. And 0 factorial is 1, so this is 9 factorial, or 9 permute 9. So there are that many possible batting orders. The probability of getting the exact one from yesterday is just 1 divided by that. So pretty low probability. Maya has a bag of 15 blocks, each of which is a different color, including red, blue, and yellow. Maya reaches into the bag and pulls out 3 blocks. What's the probability that the blocks she has chosen are red, blue, and yellow? From the way this is stated, this looks like a combination, because it doesn't say that the blocks have to be in that order, that she first pulls out a red, then a blue, then a yellow, just that there are red, blue, and yellow. Out of those 15, so it's going to be 15, choose 3. 455. How many combinations contain the red, blue, and yellow blocks? Order does not matter, so there's only one way to choose those colors. Thus, the probability that Maya chooses red, blue, and yellow is calculated as such. Just 1 over that. Last topic will be special permutations. Special permutations involve objects that are identical. Number of distinguishable permutations of n objects of which k1 are alike, k2 are alike, and so forth is given by this. We've actually already dealt with this in terms of permutations. We start out with n in our permutations, and we divide by k that belong to the group we care about, and n minus k that belong to the group we didn't care about. If we only have 2 groups, then k2 is just going to be n minus k1, or n minus r. Make sure that your k1, k2 all the way adds up to n. Tennessee, good example. Mississippi is the other usual example. How many different ways can you arrange the letters in the word Tennessee? Notice that the n's, the e's, and the s's are all the same as each other. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 letters in Tennessee. There's 1 T, 4 E's, 2 N's, and 2 S's, which means the total number of ways is going to be 9 factorial divided by 1 factorial times 4 factorial times 2 factorial times 2 factorial. $37.80. And that's it. Again, Mississippi is the other usual example. How many ways can you arrange the letters in Mississippi if the I's, the S's, and the P's all look the same as the other I's, S's, and P's? Something to think about. So that's the end of this section. I think there's one more in the course, one more in the chapter. Enjoy. Hello and welcome to section 4.5. This will be the last section of chapter 4 and probability theory. In this section we're going to combine the probability techniques of the first 2 and the counting techniques of the last sections into one nice little ball of probability. So we're going to use the basic counting rules to calculate probabilities. In this section, we'll look at counting problems that have more complicated solutions than just 1 over the total number of possibilities. A helpful trick for these problems is to look for certain key terms. The key terms are important because they define the method to be used to find the correct answer. Words to look for include at least, at most, greater than, less than, between, etc. So here we'll start out with a nice little example. A group of 12 tourists is visiting London. At one particular museum, a discounted admission is given to groups of at least 10. So A, how many combinations of tourists can be made for the museum visit so that the group receives the discounted rate? In other words, we want to find the number of ways of having 10 and 11 and 12 chosen out of that group of 12. And B, suppose that a group of tourists does get the discount. What's the probability it was made up of 11 tourists? In other words, in A, we got the total number of ways that you can get the discount, and now we're given that they got the discount. What's the probability that it was made up of 11? So here's the solution. Keywords in this problem are at least. So if at least 10 are required, then the group that gets the discount has to be 10, 11, or 12. Now we calculate the number of combinations to get 10, number of combinations to get 11, and number of combinations to get 12. Then add them together. And notice that these are combinations because we aren't putting the tourists in any line. We're just getting groups of those tourists. So here's how to get the group of 10 tourists. It's 12 choose 10, group of 11, 12 choose 11. Remember that 12, by the way. And 12 choose 12, which is just 1. As we know, the question implies that the group will get a discount if 10, 11, or 12. So the number of ways is just the sum of those, 66 plus 12 plus 1. So there are 79 ways that this group can get that discount. Now B, we need to calculate this probability. So we're given the group received the discount. What's the probability that it's a group of 11? So the numerator is going to be the number of ways of getting groups of 11, and the denominator is going to be the number of ways of getting the discount. Well, we've already figured that ways of getting a discount is 79, and we figured out the ways of getting a group of 11 is 12, so the probability is going to be 12 over 79. Jack is setting a password on his computer. He's told that his password must contain at least 3, but no more than 5 characters. He may use either letters or numbers. At least 3, but no more than 5 characters. Wow. So A, how many different possibilities are there for his password if each character can only be used once? Notice that this is without replacement. And then suppose that Jack's computer randomly sets his password using all the restrictions given above. What's the probability that his password is an arrangement of the letters in his name? Jack. So here's the solution for A. It's got to be at least and no more. Those are some keywords there. At least 3, no more than 5. So it's got to be 3, 4, or 5. So we got to count the number of ways that you can get 3, the number of ways you can get 4, and the number of ways you can get 5. The order of characters is important, so this will be permutations. There's 36 characters to choose from, 26 letters, 10 digits. So here's the calculation for 3. It's 36 permute 3. For 4 characters, it's 36 permute 4. And for 5 characters, it's 36 permute 5. So the total number of possible passwords is just the sum of those, which is about 46.7 million possibilities. To find the probability of a randomly chosen password would include only the 4 letters from Jack's name. Find the we use the number from part A as the denominator. That's the n of s. That's our sample space. To find the numerator, the number of ways you can get the event, calculate the number of permutations of 4 from a set of 4. Four permute 4 is just 4 factorial, which is 24. So the actual probability is that 24 divided by the total number of possible passwords. So it's rather small. Now the way that they calculated this is, never mind. It's n of e divided by n of s. You don't need to know what e and s are except into calculating what n of e and n of s are. Tina is packing her suitcase to go on a weekend trip. She wants to pack 3 shirts, 2 pairs of pants, and 2 pairs of shoes. She has 9 shirts, 5 pants, and 4 pairs of shoes to choose from. How many ways can Tina pack her suitcase? We do need to assume that everything matches, which means that we are in the independent realm. This will be 9 choose 3, times 5, choose 2, times 4, choose 2. Because in the 9 shirts, she's choosing 3. Of the 5 pairs of pants, she's choosing 2. And of the 4 pairs of shoes, she's also choosing 2. So there's the number of ways that she can select her shirts, number of ways that she can get her pants, and number of ways she can get her shoes. So the total number of ways from the fundamental counting principle is just that product, 84 times 10 times 6. I do want to emphasize the word and here implies multiply. It's and being you have to choose this and choose those pants and choose those shoes. In probability, or indicates adding, and indicates multiplying. And here's an interesting little drawing that might help see this. Shirts, pants, shoes. They're independent of each other because we specified everything matches. There's 84 ways of getting her shirts, 10 of her pants, 6 of her shoes. So by the fundamental counting principle, it's just the product of those. An elementary school principal is putting together a committee of 6 teachers, to head up the Springs Festival. There are 8 first grade, 9 second grade, and 7 third grade teachers at the school. How many ways can the committee be formed? Notice we're not specifying that the committee has to contain a certain number of any of the grades. There's 8, 17, 24 teachers altogether, so the number of ways the committee can be formed is just 24, choose 6. How many ways can the committee be formed if there must be 2 teachers chosen from each grade? It's going to be 8, choose 2, times 9, choose 2, times 7, choose 2, for the same reason of Tina's suitcase. And suppose the committee is chosen at random with no restrictions, so we're in the case of A. What's the probability that 2 teachers from each grade are represented? So the denominator, the bottom, is going to be A, and the top is going to be B. Because A is the number of possible outcomes, and B is going to be the number of possible outcomes in the event. "24, choose 6. 8, choose 2. Times 9, choose 2. Times 7, choose 2. And then the probability will just be this 21,168 divided by the total number, n of s, of 134,596. So even if you're not focusing on making sure that the committee consists of 2 first grader teachers, 2 second grade teachers, 2 third grade teachers, there's still a 15.73% chance that it's going to happen naturally, just out of randomness. And that's it. Notice how this section took all of our combinations and permutation stuff and used it to calculate probabilities of events. And it comes back to n of e divided by n of s. Of course, we are assuming independence and all of those outcomes are equally likely. But it's n of e over n of s. N of e over n of s. And that's it. The end of chapter 4. The next lecture will be on specific probability distributions and things that we can do with discrete distributions. So stay tuned. Hello and welcome to section 5.1. This is the chapter, or this section introduces the chapter that deals with discrete distributions. This chapter is going to cover some named and therefore important discrete distributions. This section is just looking at some basics of discrete distributions. So by the end of this lecture, you should be able to understand the difference between discrete and continuous distributions, or discrete and continuous random variables. Chapter 6 will deal with the continuous ones. To know the purpose of the probability mass function, explain the 3 requirements for a function to be a probability mass function, and that's an important one. Calculate probabilities using the probability mass function, determine sample space. Sample space also very important because it helps give you a better understanding of which distributions the data could actually come from. And then calculate the expected value and variance of a distribution. Expected value and standard deviation will be the important ones, and standard deviation is just the square root of the variance. So let's start with the definition of what a random variable is. A random variable is a variable whose numeric value is determined by the outcome of a probability experiment. You can think of this as an outcome from the future. Some examples. Statistician's favorite flavor of ice cream. You don't know that until you actually measure it. Ask the statistician. A student's level of approval of a congressional decision. You don't know that until you measure it, aka ask the student. The year a Knox College professor is born. You don't know that until you ask, until you perform that experiment. So all of these are random variables. Random variables have or they follow probability distributions. It's this fact that they follow probability distributions that allows us to understand the randomness of a random variable. And I want to say that just because it's random doesn't mean we don't know anything about the possible outcomes. In fact, we know a lot about those possible outcomes. We don't know what the exact outcome is going to be, but we know everything about it. We know the expected value. We know the uncertainty in that estimate. We know the medians. We know probabilities of specific outcomes. So we know everything about that future outcome except for what that future outcome is going to be. These are the three requirements for a function to be a PMF. All the probabilities have to be between 0 and 1. This is true in general. Probabilities can't be greater than 1. Can't be less than 0. The sum of the probabilities over the sample space is 1. Cursive S is called the sample space. It's the set of all values of x that can happen, that have a non-zero probability of happening. So this notation, this is summation over all the values of x that are in the sample space of that probability of the value. The little x is going to be the value. The big X is just going to be big X's. These are random variables. Sometimes we'll have big Y for a different random variable. So the sum over the entire sample space of the probabilities will be 1. And the probability of a union is no more than the sum of the individual probabilities. This comes from chapter 4. So the probability of A union B is less than or equal to the probability of A plus the probability of B for events A and B. They are equal if the intersection of A and B is empty. It's less than if the intersection is not empty. So let's create a probability mass function for this experiment. Flip a coin 3 times, count the number of heads flipped. So the outcome, or the random variable, is going to be the number of heads flipped in those 3 coins. From this, we know that the sample space is going to be 0, 1, 2, and 3. How do we know that it's 0, 1, 2, and 3? Well, we're flipping the coin 3 times. So the largest number of heads we can get is going to be 3 heads. And the smallest will be 0. And they're going to be counts. This is discrete, so we can expect it to be some sort of counts. So the sample space is the set 0, 1, 2, 3. Second step is to determine the probability of each of those 4 outcomes. We're going to rely on 2 assumptions. 3, the coin has 2 sides, that'll be 1. 2, the coin is fair and the flips are independent. Coin is fair indicates that the probability of a head is 1/2. Flips are independent means that the outcome of one flip is not going to influence the outcome of another. So if these are true, there are 8 possible outcomes of the flips, not of the random variable, but of the flips. You can get 3 tails. You can get tail, tail, head, tail, head, tail, head, tail, tail. You can get head, head, tail, head, tail, head, tail, head, head. Or you can get 3 heads. The random variable is the number of heads. So if you get tail, 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 you have 0. If you get head, 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 you get 3. If you get tail, head, tail, you get 1. Probability of getting 3 tails is 1/2 times 1/2 times 1/2, which is 1/8. So the probability of the outcome 0 is 1/8. Similarly, the probability of the outcome 3 is 1/8, because the only way to get 3 is head, head, head. 1/2 times 1/2 times 1/2. These 3 outcomes from the flips give you the same random variable value of 1, because they all have 1 head. Probability of tail, tail, head is 1/8. Probability of tail, head, tail is 1/8. Probability of head, tail, tail is 1/8. So the probability of getting 1 head is 1/8 plus 1/8 plus 1/8. Probability of getting 2 tails, of getting 2 heads is just head, head, tail, head, tail, head, tail, tail, head, 1/8 plus 1/8 plus 1/8, 3/8. In other words, there's 3 ways of arranging these outcomes so you get 2 heads times 1/2 times 1/2 times 1/2. Here's another way that we can represent this. This will be graphically. Sample space is listed along the bottom. The height of the bar corresponds to the probability of that specific outcome. We could represent the probability mass function in this way as well. Probability of the random variable equaling some value, some specified value, is 0.125 if this x is 0 or 3. It's 0.375 if this little x is 1 or 2, and it's 0 otherwise. Notice this formula is also not unique. We could also represent it as 3 choose x times 0.125. And keep this in mind when we get to the binomial distribution, which will be in the next section. Remember that population parameter is a function of the population. Contrast this with a statistic being a sample of the data. We want to use those statistics to estimate the population usually, and we'll do that in the second half of the course. Here we're going to look at ways of calculating those population parameters when we know what the distribution is. Some population parameters that we care most about will be the mean, the standard deviation, which is the square root of the variance, and the median. The definition of the expected value, or the mean, of a discrete random variable, so the expected value of x, where x is our random variable, is just the sum over all values of x in the sample space of the quantity x times its probability. Recall from chapter 3, mu, which is the population mean. When we're dealing with distributions, we can also use expected value of x. It's just equal to the sum of x times 1 over n. Of x times, well, if each outcome in the population is equally likely to be observed, then the probability of observing that person is just 1 over n. And I suppose that should be a capital N. Expected value is just a long-run average of those outcomes. Variance of a distribution is a measure of uncertainty in each outcome. It's the opposite of the word precision. I like the word uncertainty. The variance of a discrete random variable is given by, that's v of x. We could also use sigma squared, just the sum over all the x's in the sample space of the quantity x minus mu squared times the probability of that outcome. Population variance, remember, was the same thing except 1 over n. And this is perfect if every outcome is equally likely. Here we're dealing with unequally likely outcomes. Here's the wonderful definition of the median. Notice that this explains why I hand waved, saying it's about half is below and about half is above, because dealing with the actual definition of the median gives me a headache sometimes. When the distribution is continuous, we can just deal with the probability of x being less than or equal to the median. That's tilde on top. Tildes are located to the left of the 1, is just equal to 0.5. Note that this implies that for a discrete distribution, the median is not necessarily unique, whereas for continuous distributions, it will be. Here's an example. 3 coins. Flipping through a coin 3 times, the probability mass function, remember, we came up with was this. Let's calculate the mean, the variance, and the median from definitions. Expected value of x is just the sum over all x that are in the sample space of the value times its probability. There are 4 things in the sample space, 0, 1, 2, and 3. So it's 0 times the probability of a 0, plus 1 times the probability of a 1, plus 2 times the probability of a 2, plus 3 times the probability of a 3, which gives us 1.5. So the expected number of heads on 3 flips of a fair coin is 1.5. Doesn't surprise us. Variance, same thing. Adding up over all x's in the sample space of the value minus the mean squared times the probability of the value. So 0 minus the mean squared times the probability of a 0, plus 1 minus the mean squared times the probability of a 1, plus 2 minus the mean squared times the probability of a 2, plus 3 minus the mean squared times the probability of a 3. Add them all up, you get 0.75. Standard deviation, therefore, is 0.866. That's the definition of the median. I think the best way of using it is using cumulative sums of the probabilities. So you order it from 0 outcomes, from lowest to highest. Start with the lowest outcome probability, see if it's greater than or equal to 0.5. If it's not, go to the next one and add the probability onto it. So here x equals 0, probability of that is 0.125. It's not greater than or equal to 0.5, so 0 is not a median. Probability of a 1 was 0.375. So the cumulative probability at 1 is 0.125 plus 0.375. And that is greater than or equal to 0.5. So 1 is a median. Note that since it comes out exactly equal to 0.5, the next value is also the median. 2 is also a median. And every number between 1 and 2. So 1.5 is a median. 1.6 is a median. Here's the R code. The X and P lines are going to be common to all the calculations. It's the last one that shows you how to perform the calculation to get the parameter. So we've seen things like this P line, so we're defining the variable P as equal to, and we're using the C function to combine all of these values into one vector. It's 0.125, 0.375, 0.375, 0.125. So running that second line, P will now contain those 4 values. The first line, this is a new construct for us. We're saying x is equal to the values from 0 to 3. That's a colon, so this will be 0, 1, 2, and 3. In some computer languages, you'll have, instead of a colon, 3 lower dots, kind of like this, to indicate 0 through 3. But for R, it's just a colon. And now that we've got the sample space and the probability of each of those outcomes, we can calculate the mean as just the sum of all those x's times their probabilities. 1.5. For the variance, it's just the sum of the value minus the mean squared. This is a caret. This is the thing on top of the 6. it's read as, quote, to the power of. So this caret 2 will mean to the power of 2, or squared, times p, added up. And the standard deviation is just the square root of that. The function to take the square root in R is sqrt. For the median, we use the function cumulative sum, or cum sum. And we look for the first place where it gets to be 0.5 or greater. And that first place, remember, the sample space is 0, 1, 2, 3, 0, 1, 2, 3, 0, 1. So 1 is a median. Remember, since this is exactly 0.5, then not only is 1 a median, but so is 2, and every number between 1 and 2. Example 2, ice hockey. My Stat 225 course, we did a project where the students predicted the outcome of a future ice hockey game between the Portland Winterhawks and the Prince George Cougars. Go Hawks. I took all of their probabilities and averaged them for the entire class for the number of points scored by the Winterhawks. So the class as a whole said the probability of them scoring 0 points was 0.1, 1 point was 0.1, 2 points is 0.2, 3 points is 0.4, and 4 points and 5 points are 0.1 each. So let's calculate the expected number of goals, the uncertainty of that, aka the variance, and the median. So here's a graph of that. Using the formula for the expected value, we're adding up over all the x's in the sample space. Sample space 0, 1, 2, 3, 4, 5 of the value times its probability. And we get 2.6. So the expected number of goals to be made by the Winterhawks is 2.6. You do not round that to the nearest integer. The expected value is a long-run average. Averages don't have to be in the sample space. So the expected value is 2.6. It's not 2, it's not 3, it's 2.6. Variance, going to use the formula again. Plug and chug, get 1.84. Standard deviation, therefore, is 1.356. We could use the standard deviation with the empirical rule to say that the probability of the Winterhawks scoring between 1.2 and 3.9 is about 68%. We can actually calculate it exactly. It's 60%. The median, start with 0. Probability is 0.1. That's not at least 0.5. Add the probability of a 1. So we're at 0.2 now. That's not at least 0.5. Add the probability of 2 goals. That's 0.4. That's not at least 0.5. Add the probability of 3 goals. That comes up to be 0.8. That is greater than or equal to 0.5. So 3 is a median. In fact, since the probability of 3 or less is greater than 0.5, we know that 3 is the only median. If these had added up to exactly 0.5, then we'd know that 3 and 4 were both medians, as well as everything between 3 and 4. But since it came out to be something greater than 0.5, we know that 3 is the only median. We can do it in R quickly. X line, this is the values 0 through 5. Again, there's that colon notation. So run that first line. X is now the vector 0, 1, 2, 3, 4, 5. P, this combined function, the C function of 0.1, 0.1, 0.2, 0.4, 0.1, 0.4. And the mean is just the sum of the x's times their probabilities, 2.6. The variance is just the sum of the x minus mu squared times p's. And the standard deviation is just the square of that variance. And the cum sum function R, that's cum sum for x equals 0, cum sum for x equals 1, for x equals 2, for x equals 3. Boom. X equals 3 is the median. Again, cum sum is the cumulative sum of those probabilities. So these values are probability of x being less than or equal to 0, 1, 2, 3, 4, 5. So here's a summary of what we did today in this introduction to discrete distributions. We looked at probability mass functions and saw how they describe the probabilities of each outcome in the sample space. We saw that probabilities can be calculated by adding the individual probabilities. This reflects Chapter 4 very clearly. The expected value is a weighted sum of the outcomes, weighted by the probabilities. Expected value and mean are synonymous. The variance is a weighted sum of the distances between the outcomes and the mean, again weighted by that probability. And the median is the value, again, not necessarily in the sample space, such that at least half is less than or equal to it and at least half is greater than or equal to it. In the future, we're going to look at some named discrete distributions. Bernoulli binomial on the next, Poisson later, hypergeometric later. I misspelled hypergeometric, I guess. We're going to use R to calculate those probabilities, expected values, if we wish it to. You can find many uses for these probability distributions in modeling the real-world events around us. And then when we get to Chapter 6, we'll repeat this for some continuous distributions. And we're going to continue understanding how the data generating process helps us to better estimate the parameters. The readings will be Section 5.1 in Hawks, Appendix A1 and R for starters. Here are the intra-lecture questions, not entirely intra-lecture, but we'll pretend. Question 1, what is a random variable? Again, I would suggest in your notes, write the question on the left-hand side and answer it so that you can transfer that into Moodle's quizzes. What is a random variable? Question 2 is, what is a sample space? And question 3 is, what is the difference between an expected value and a mean? And that's it. Hello and welcome to section 5.3, the Poisson distribution. Here we introduce a second discrete distribution, and I'd like you to keep comparing it to the binomial to see what the similarities and the differences really are. So by the end of this lecture, you should be able to determine what random variables follow a Poisson distribution by using the definition of a Poisson, calculate the probabilities from a Poisson distribution both by hand and by R, and calculate the expected value, variance, median, probability associated with that Poisson random variable. So here's the definition. A random variable that is a count of successes over an area or a time period follows a Poisson distribution with an average rate parameter of lambda. Contrast this with the binomial distribution, which was a count of successes over a certain number of trials. Here it's over a time period. So examples, heads flipped in an hour, as opposed to heads flipped in 10 flips, which would be binomial. Here it's heads flipped in an hour. Number of dents on a car. Number of errors on a page. Number of terrorist attacks in a year. Number of bacteria in a swimming pool. Influenza cases in a week. Wars in a year. The binomial would be the number of states or countries at war in a year. Notice there's an upper bound to that. Or binomial would be the number of people in this class with influenza in a week. That also has an upper bound. Notice in each of those cases you're measuring number of successes out of a total population of n. Bacteria in a swimming pool would be a Poisson. A number of swimming pools in Galesburg with bacteria would be binomial. Notice what I'm getting at here is that for a binomial, it's the number of successes out of a number of trials. So the sample space is 0 through n. Whereas for a Poisson distribution, it's not the number of successes over trials, it's the number of successes in a time period or an area, in which case there is no upper bound. Therefore, the sample space for Poisson is 0, 1, 2, 3, 4, ... It can be proven, aka it's beyond the scope of this course, that the probability mass function for Poisson is, for a probability mass function, it's got the equals part. Random variable is x, the value is little x. It's equal to e to the power of negative lambda times lambda to the power of x, all over x factorial. This e is the natural log base. It's 2.7182, etc. Lambda is the average. That's the parameter that we have to give it. And x is the value that we want to find the probability of. It can be shown that the expected value and the variance for Poisson are both lambda. That's kind of cool. We'll go with an example. Let x be the number of heads flipped in a minute. Given that I average 24 flips per minute. Notice I didn't say I am flipping the coin guaranteed 24 times in this minute. I'm saying I average 24 flips per minute. If the coin is fair, then it's clear that x follows a Poisson distribution with lambda equal to 12. Probability of getting no heads, probability of getting at most 20 heads, and the probability of getting at least one head in the first 6 seconds. Probability of getting no heads in that minute, so we're asking what's the probability x is equal to 0. We're given lambda is equal to 12, so it's a plug and chug, e to the negative 12, 12 to the 0, all over 0 factorial. Recall from chapter 4, 0 factorial is 1. So this is equal to 0.000006114. In other words, if I actually do this experiment, flip the coin for a minute and come up with 0 heads, then either I don't average 24 flips per minute, or the coin is not fair, or I should go out and buy a couple lottery tickets, because this outcome is extremely rare. On R, this would be d plus 0, lambda equals 12. Again, d is for the probability, calculating the probabilities of equals. Here, Poisson is for the Poisson distribution. 0, we're calculating the probability x is equal to 0, and we have to specify that lambda is 12, because we're given lambda is 12. Part 2, what's the probability of getting at most 20 heads in that minute? So probability of x being less than or equal to 20, of the random variable being less than or equal to 20. This is a quote simple application of the probability mass function. This is equal to the probability x equals 0 plus probability x equals 1 plus the probability of x equals 2 plus the probability of x equals 3. Okay, I'll stop there until we get to 20. Here's the PMF. We're just adding up for all those various values of x from 0 to 20. Easy way, since this is a less than or equal to, is to use the P form. Again, the stem is POIS for the Poisson. We're calculating the probability of x being less than or equal to 20, and lambda is still 12. Probability of getting at least one head in the first 6 seconds, at least. Notice x was flips heads in a minute. We want to do this in 6 seconds, so we have to define a new random variable. 6 seconds is a tenth of a minute. So the expected number of heads is just going to be 12 divided by 10. The number of heads in a minute divided by 10, because now we're in terms of 6 seconds. Plug and chug. Y greater than or equal to 1. So I guess this should be a y. So we're summing up from y is equal to 1 all the way up to infinity. This is going to take a long time if we do it this way. But recall the complements rule. Probability of y being greater than or equal to 1 is equal to 1 minus the probability of y equaling 0. And this part here is the probability that y is equal to 0. 1 minus that. If it's y equals 2, we'll use a d for the equals and a 0. So there's about a 70% chance that I get at least one head in 6 seconds. Complements rule comes in really handy when dealing with Poissons. Let x be the number of wars in a year. From the binomial slide deck, we know that the average rate of wars in a year is 1 over 0.8462141. Section 5.1 gave us this. This 1 divided that would be 1.181734. So that's lambda for 1 year. I want to know what's the probability that we have 5 years without a war. If this is lambda for 1 year, the lambda for 5 years will be just 5 times that. Boom. And so probability of y is equal to 0 is just 0.002715796. This is about 1 over 500, so we'd expect a 5-year peace streak to happen about once every 500 years, which seems to be borne out by reality. Real estate developer in Galesburg is looking to determine if it would be profitable to renovate the Ferris building downtown into a boutique hotel. To help determine this, he asked a student of mine who graduated last year to help estimate it. John, the student, estimated that the rate would be about 150 people per week. The developer decided that a minimum of 130 per week would be needed to turn a profit. So if John is right, what proportion of weeks will not be profitable? So we're given lambda is equal to 150. We want to know the probability of being 130 or less. Or I'm sorry, less than 130. So this is a probability. This is not a cumulative probability because a cumulative would be less than or equal to. So we make it a less than or equal to by dropping the 130 by 1. It's now a cumulative probability. So we use P, Poisson, because it's a Poisson, 129, and we're given that lambda is equal to 150. So about 4.5% of the weeks will not be profitable. Another example, Galesburg crime. There's actually a few examples in part of example 4. Reportedly, the number of violent crimes in Galesburg was 96 last year. So we're going to use that for our lambda. If there were 4 violent crimes last week, is there significant evidence of an uptick in the crime rate? Okay, so lambda is 96 per year. I got 4 violent crimes last week, so we can make that lambda in terms of weeks by dividing 96 by 52. So if the number of violent crimes in a week, if x is that, and we're asked to calculate probability of x being greater than or equal to 4, and interpreting that, we're given x follows a Poisson with lambda equal to 96. This is crimes in a year, divided by 52, so that would be crimes in a week. This is in the wrong direction. It needs to be less than or equal to. So this would be 1 minus x less than or equal to 3. It's a less than or equal to, so we can use the p form of Poisson. 3, lambda is 96 out of 52. And we get 0.116. So what this means is if the crime rate stayed the same, that is 96 per year, then we'd observe 4 crimes a week about 11% of the time. That's rather large, really, taking everything into consideration. So it's not really evidence that the crime rate's gone up. That isn't evidence. Crime rate may have gone up, but this doesn't provide sufficient evidence for that. So let's say there were 16 violent crimes last month. Notice part A, it was 4 in a week. So we'd expect 16 in a month if it's 4 in a week for 4 weeks. So this really is, in some ways, the same question as last, but we're holding that increase of crime for, instead of over a week, we're doing it over a month. So really we're asking, does increasing the sample size affect the probabilities? So we're asking what's the probability, and we're supposed to interpret the probability of x being greater than or equal to 16. Given that lambda is 96 over 12, because it's in terms of 12 months. Greater than or equal to 16 is 1 minus, less than or equal to 15. We're now less than or equal to, so we can use p form of Poisson, 15, lambda, and now we got probability being 0.00823. That is very small. In other words, if the crime rate stayed the same, we would expect to see 16 crimes in a month less than 1% of the time. So this would constitute some evidence that the crime rate did go up this year. Now, the good question that you're thinking is, okay, the last one it was 0.11 and this one's 0.008. The 0.11 it was relatively large, interpreted as being relatively large. 0.008 is relatively small. The 0.11 doesn't give us sufficient evidence. The 0.008 does. Where's the separation between doesn't give us the evidence and does give us the evidence? I'm not answering that now, but keep this in mind. In fact, over on the left-hand side of your notes, write something like, what's the difference or what's the separation between not enough evidence and enough evidence? Circle it, make it stand out a little bit, maybe put alpha around it a few times, just so that we can refer back to that in the future. So here's a summary of the Poisson. Poisson distribution models the number of successes over a time period or an area. Parameter of a Poisson distribution is lambda. This lambda is both the mean and the variance. We know the probability mass function of the Poisson that allows us to calculate probabilities from a Poisson random variable. In the future, we're going to look at the hypergeometric. Notice the hypergeometric is spelled correctly here, and also hypergeometric, we've bumped into that before in Lab B, or we're about ready to. Hypergeometric, like the binomial, models number of successes given a number of trials. So you got to figure out what is the key difference between the binomial and the hypergeometric. And then chapter 6 will be the continuous distributions. Here are the R functions. 2 of these we dealt with. 2 of those are implied. They all have the stem POIS, and they all require specifying lambda, because those are the keys to a Poisson distribution. The D form is for calculating probability of x equaling a value. The P form is for the CDF, calculating probability of x being less than or equal to a value. The R generates random values from a Poisson, and the Q form calculates the quantiles. So if I want to calculate the median, I do Q plus of 0.5 and specifying whatever value of lambda it is. If I want to calculate the 10th percentile, I put in 0.1 for p. The readings, Hawks was section 5.3, are for starters. This is appendix A7. And as usual, Wikipedia's got a pretty good page on the Poisson distribution. Gives you a nice flavor of how far you can go with these probability distributions. So here's the intra-lecture question for 5.3, or questions for 5.3. Question 1, what is the parameter of a Poisson distribution? It is the parameter of a Poisson. Hint, it's called lambda. Question 2, what's the difference between a binomial and a Poisson variable? I won't give you a hint on that one except to say go back over your notes to make sure that you have this written down. This is important. And what's the formula for the expected value of a Poisson? That's also a pretty easy one. So of these three, the second one's going to be the tough one. And that brings us to the end of the Poisson distribution. Take care. Hello and welcome to the last section of Chapter 5. This will be the last named discrete distribution we'll be working with. It's called the hypergeometric. This is featured in Lab B. So by the end of the lecture, you should be able to determine which random variables follow hypergeometric distribution using its definition, identify the three parameters of a hypergeometric distribution, and calculate the expected value of variance, mean, and probabilities associated with a hypergeometric random variable. Hypergeometric is rather difficult to work with, so don't expect too much work using the hypergeometric, doing things by hand. You'll see the probability mass function and understand what I mean when you do see that. The hypergeometric distribution describes the probability of obtaining x successes in k draws or trials without replacement from a finite population that contains exactly m successes and n failures. See, I told you it was kind of complicated. Two keys to this are it's without replacement, so you're drawing and you're not putting it back, and the population's finite. If you are doing it with replacement, or if the population is infinite, then you've got a binomial random variable here. So this is a binomial constrained to a finite population without replacement. Well, when you get to the lab, you'll understand that it's better, but as you work through this slide deck, you'll see why we tend to focus on the binomial. Examples. Number of hearts drawn from a deck without replacement. So I draw 5 cards. What's the probability? 3 are hearts if I don't replace. Finite population, capital N's 50, 2, and it's without replacement. Number of sophomores counted in the library without recounting somebody. Number of parolees that returned to the Hill Correctional Center in Galesburg. In each of these cases, it's without replacement and the population's finite. So key. So hypergeometric, finite, and no replacement. Now you'll find out, and I think the lab helps with this, that if your population is sufficiently large but not infinite, then the advantage of using the hypergeometric is very small. You might as well stick with the binomial. Recall that the probability mass function provides the probability of each element for the sample space. For a hypergeometric random variable, this is the sample space. See, notice automatically that we see that the hypergeometric is rather complicated to work with. For the binomial, it's just from 0 to n. Here, it's the larger of 0 and k minus n, all the way up to the minimum of k and m. How do we parameterize this? There's lots of ways of parameterizing the hypergeometric. That's another frustrating thing with the binomial. It's always n and p or n and pi. For the hypergeometric, there's at least a half dozen ways. In fact, Hawkes uses a way that's different from either R or the Forsberg text. We can do it by successes and total, or by successes and failures, or by a combination of the two. But fundamentally, the probability mass function here at the bottom is just number of ways to succeed times the number of ways to fail divided by the number of ways you can have those n trials. And these are combinations, so review of chapter 4 would not be unwise. So here's the probability mass function. It's m choose x times n choose k minus x divided by m plus n over choose k. X is the number of successes you care about. M is the number of successes in the population. In this case, little n is the number of failures in the population. So x is the number of successes in your sample. K minus x will be the number of failures in your sample. And then the denominator is just going to be the total population size divided by the total sample size. And notice the switch here, k is now the sample size, not n. And trust me, this is one of the better parameterizations of the hypergeometric. Here's another one. Here, k will be the population successes instead of little m. N will be the population size, which means n minus k will be the population failures. X will be the successes in your sample, n minus x will be the failures in your sample. Here, n will be the sample size, so n choose n will be the denominator. They say the same things. They're using different letters to represent what those things are, but they're saying the same thing. This is the number of ways of getting x successes from the population. This is the number of ways of getting your specific number of failures in your population. And this is the number of possible samples you can draw from that population. Same as it was for the previous. Expected value of a hypergeometric does not need to be memorized. You've got this in your notes, so make sure you know where you can locate it. It's just k, your sample size, times p, the probability of a success in the population. M is the number of successes, n is the number of failures, so n plus m is a population size. So this m over n plus m is just the probability of a success in the population. And that's the sample size, so it's essentially n times p, but we're using different letters. Here's the variance. It's your sample size times the probability of a success in the population times the probability of a failure in the population times an adjustment factor. Notice this is thinking back to binomial. This would be n times p times 1 minus p times some other number. Notice this number is always going to be between 0 and 1, which means that the variance of a hypergeometric is always going to be smaller than that of a binomial. That's important. Variance of a hypergeometric is always going to be less than or equal to, for extremely large sample sizes, that of a binomial, as long as k is not equal to 1. If k is equal to 1, then there is absolutely no difference between a binomial and a hypergeometric. Go back to the definition of a hypergeometric to see why that's the case. The big difference is with replacement or without. If you're only drawing one thing, it doesn't matter if you replace it or not. It's the same probability. This is another way of saying exactly what I did. Understand what the parameters represent. Don't get hung up on the formulas themselves. Understand that the expected value is just the sample size times the probability of a success in the population. The variance is n times p times 1 minus p times some adjustment factor. So here's a couple examples. Okay, here's a few examples. Let X be the number of spades drawn out of four draws from a deck of cards without replacement. If the deck is fair, then it's clear that X follows a hypergeometric. With M equal 13, the number of successes in the population is 13. N, the number of failures in the population, is 39. And our sample size K is 4. Success, failure, sample size. So here are the probabilities, or here are the questions. What's the probability of getting 1 spade? What's the probability of getting at most 3 spades? And what's the expected number of spades? Probability of getting 1 spade, plug and chug. Probability X is equal to 1. We're given M is 13, X is 1, N is 39, K is 4, 4 minus 1 is 3. A little check here. 13 plus 39 has to be 52. 1 plus 3 has to be 4. Why is that a check? This first refers to the number of ways of getting those successes. The second is the number of ways of getting those failures. And the total is just failures plus successes. So the probability of getting 1 spade is 0.438847539. Here it is in R. Probability that X is equal to 1, so it's D and a 1 there. This is a hypergeometric, so the stem is hyper. Parameters M is 13, N is 39, K is 4. By the way, this is the parameterization that R uses, M and K. Probability of getting at most 3 spades. This is a less than or equal to question. Less than or equal to 3. Since it is a cumulative, a less than or equal to, we can use the P version. 3. M, N, and K. So the probability of getting at most 3 spades is 0.9973589. In other words, pretty good chance that you'll get at most 3. What's the expected number of spades? Sample size times successes over trials. So the expected number of spades is going to be 1. Make sure this result makes sense, especially thinking about lab B. A quarter of the deck is spades. I draw 4, so I'd expect 1. Example 2, I wonder if Stat 200 attracts third-year students at a greater rate than other courses. So X will be the number of third years in Stat 200. We know that the number of third-year students at Knox is 356. We know the number of non-third years is 978. We got that from the registrar's website. Therefore, those are population numbers. In this stat course, there's 41 students. 18 are third years. So we need to calculate the probability X is greater than or equal to 18. Given M is 356, N is 978, and K is 41. This is in the wrong direction. It's got to be a less than or equal to. So using the complements rule, this is 1 minus probability of X is less than or equal to 17. This is what it is in R, 1 minus probability under hypergeometric of X being less than or equal to, oops, that should be a 17. So this number here should be 17, not 18. M, N, and K are given to us previously. This is probably around 0.005. Very small probability of this happening. Therefore, it appears as though third years are overrepresented in this course. Or I'm wrong about M, N, and K. I trust the registrar to give me these two numbers. I know I can count to 41. Therefore, I'm going to conclude that third years are indeed overrepresented. If we were to pretend this was a binomial, we get a probability of 0.00537. Not much of a difference between these two. And the reason why there's not much of a difference between the two is because the population size is, quote, rather large. It's 1,300 or so. So once you get a large population, hypergeometric and binomial are essentially the same thing. I wonder if my Math 121 attracts fourth-year students at a lower rate than other courses. Let X be the number of fourth years in my Math 121 course. According to the registrar's website, we know the number of fourth years at Knox is 278. Non-fourth years is 1056. In my 121, there are 30 students. 3 are fourth years. So I need to calculate the probability of X being less than or equal to 3, where X follows a hypergeometric distribution with M, N, and K equal to 278, 1056, and 30. P hyper, P because it's less than or equal to. We got it at the 3, I made it right this time. M, N, and K given to us by the registrar's website and me being able to count the class. This is 10%. Because the probability is not that small, there does not seem to be much evidence that Math 121 attracts fourth years at a lower rate than other courses. 10%, not that small. Again, this goes back to, I think it was the binomial slide deck where we started talking about, okay, what's the difference between, no, it was the Poisson and the crimes. What's the difference between not that much evidence and sufficient evidence? So you might want to write in the margin again, arrow there of asking the question. Difference between sufficient evidence and not sufficient evidence. By the way, 0.099 versus 0.102, hypergeometric versus binomial. Don't get me wrong, the hypergeometric is the correct distribution. And doing this by using R is pretty darn easy. So there's no reason to use the binomial approximation. But if you were doing it by hand or using some things that we will be doing in this class in the future that are predicated on the binomial, as long as your sample size is large enough, you can use those things, those future things, for both the binomial and the hypergeometric. So the summary. Hypergeometric models the number of successes out of a specific number of trials when the population is finite and the elements cannot be selected multiple times. There are multiple ways of parameterizing this distribution. I gave you 2 of them, but they all specify the sample size, the number of successes, the failures in the population in some way. You saw the PMFs of the hypergeometric, the mean and the variance of the hypergeometric. Again, you should not spend your time memorizing those. Have them in your notes and make sure you're able to access them and use them. In the future, this lecture is the end of the discrete distributions. The future will be continuous distributions. That'll start with chapter 6. We've got the 4 R functions. All of them have the stem of hyper for the hypergeometric. They all require you to specify M, N, and K. Again, the D is for the equals probabilities. The P is for less than or equal. The R is for generating a random sample from that distribution. And the Q is for the quantile. So if I want the median, I'll put 0.5 for P, and I'll be able to get the median. If I want the third quartile, I would put 0.75 in here for P and get the third quartile. Course readings, Section 5.4 in Hawks. This is Appendix A6 in R for Starters. Wikipedia's got an interesting page on the hypergeometric. Again, it'll give you a taste of where you can find the formulas if you forget them, and it'll show you a lot of things that we can do with this probability stuff. Which brings us to the 3 intra-lecture questions. Question 1, what are the 5 requirements for a random variable to follow a binomial distribution? Yes, this is for the binomial distribution. You must know those 5. 2, what's the difference between a binomial and a hypergeometric variable? And question 3, what's the difference between a binomial and a Poisson random variable? So a little hint here, seems like we're focusing on the binomial as being the most important distribution in this chapter. If it seems that way, then good, because it is. But also you're seeing how close the Poisson and the hypergeometric are to the binomial when they are close, and by extension when they're not close. And that's it. Take care. Hello and welcome to Chapter 6. In Chapter 6 we're talking about continuous distributions. Contrast this with the discrete distributions in Chapter 5. Chapter 6 in Hawks goes directly to the normal distribution, introduces some things that just kind of pop out of nowhere. To help see where those things come from, I'm introducing 2 other distributions, the uniform distribution, which will be this lecture, and the exponential distribution, which will be the next. So by the end of this lecture, you should be able to understand the difference between discrete and continuous random variables, know the purpose of the probability density function. Notice this is the probability density function, not the probability mass function. Be able to prove that the density is not a probability. Know the purpose of the cumulative distribution function, CDF. Hint, it's the same as the purpose of the CDF with discrete random variables. Be able to calculate probabilities using geometry or the CDF. In fact, we're going to figure out an easy way of calculating or creating the CDF for the uniform. And then understand the uniform distribution. It's 2 parameters. It's sample space, its expected value, its variance, standard deviation, median, things like that. So here's a definition of a continuous random variable. It's a random variable with a sample space consisting of an interval of values. That means for continuous random variables, there is always a value between 2 other values in it. So there is no next to with continuous random variables. For discrete random variables, you could list them off. There's a next to. After 1 came 2. After 2 came 3. For a continuous random variable, between any 2 values, there's always going to be another value. Examples of actually continuous random variables: student height, age of a car, time spent at a stoplight, distance a golf ball goes. Those are all continuous measures. There's also a category of random variables that are essentially continuous. They're not continuous, they're discrete, but we can pretend they're continuous and not lose too much, not create too much error. In much the same way that when we were dealing with a hypergeometric distribution, if the population was, quote, large enough, we could use the simpler binomial and we wouldn't introduce too many errors. Such examples of, quote, near continuous random variables would be GPA. Definitely a discrete distribution, but the distance between 2 levels of it is so small compared to the range that we can just pretend that it's continuous and not introduce too much by way of error. Annual salary. My salary is paid down to the penny. So the grid is a penny, but my salary is in tens of thousands of dollars. So that it's close enough to being continuous that we can pretend it's continuous. Same with gross domestic product, GDP per capita, crime rate, number of ears of corn grown in Iowa. That's definitely a discrete distribution, but the distance between one ear and the next ear, that grid, is so small compared to the number of ears grown that we can pretend that it's continuous and not lose too much. What I'm getting at here is, just like with the binomial, there are benefits to using the binomial when you can. Simplicity is the best. That even though the data are generated from a hypergeometric, if the population is large enough, we can pretend it's binomial and not introduce too much error, and then reap the reward of everything that comes from it being a binomial. Same thing here with these, quote, near continuous random variables. They're not continuous, they're discrete. But they're so close to being continuous that we can pretend they're continuous and reap all the benefits of a continuous random variable. And there are several. The first continuous random variable that we're going to talk about is the uniform distribution. The uniform distribution is a continuous distribution that describes random variables whose likelihood of occurring is constant across a specified interval. Notice the word probability is missing from that definition. When we start talking about continuous distributions, we have to start talking about likelihoods of events. We'll be able to retrieve probabilities in a lot of cases, but we have to start talking about likelihoods. If the random variable x has a uniform distribution, we're going to write x, and there's that tilde, is distributed as a uniform with parameters a and b. A is the lower bound, and b is the upper bound. If x is a uniform a-b distribution, then the sample space is all values between a and b. The expected value is just a plus b over 2. The variance is just the width of the interval squared over 12. Standard deviation is just the width of the interval divided by the square root of 12. In other words, it's the square root of the variance. This is the probability density function. For all x that's in the interval a to b, the likelihood is 1 over b minus a, or the density is 1 over b minus a. Outside that interval, the density or the likelihood is 0. It's a uniform distribution because each of the likelihoods is the same. In a probability density function, you're measuring the likelihood or the probability density. For the uniform, it's a constant between a and b. The height is going to be 1 over b minus a. Why is the height 1 over b minus a? This is a graph of the likelihood. Let me be clear. This is the graph of the density or the likelihood. This is not a graph of probabilities. We know it's not a graph of probabilities because if a is 0, for instance, and b is 1/2, this width is going to be 1/2, and the height is going to be 2. And you can't have probabilities that are greater than 1, so this is clearly not a probability. To obtain a probability, you just have to find the area corresponding to what you're trying to the event you're finding the probability of. So probabilities are just areas of the PDF functions. For most continuous distributions, that means we have to use calculus. For the uniform distribution, we can use high school algebra, or we can use 6th grade algebra. It's just squares and rectangles. Note now we know why it has to have a height of 1 over b minus a. It's because the interval length is a to b. The length is b minus a. And we know that the probability of something in this interval happening has to be 1. So the probability that x is between a and b has to equal 1. It's a rectangle, so b minus a, which is this width, times the height has to equal 1, because rectangles are width times heights. And therefore the height has to be 1 over b minus a. Note that the PDF has two purposes. One, it's to help the researcher understand the probability for a continuous distribution, and it's to help the researcher calculate probabilities of a continuous distribution. And in red, probabilities are areas under the density curve. Another thing that these PDFs can tell us is where the outcome is most likely. Here the likelihood is flat, therefore every value between A and B is equally likely. If there was a mound to this, then those things near those values around the peak, that's the word, peak, will be more likely. So let's see how we do this. There's only one stoplight between home and school in the morning, my home and my school. It regularly cycles among green, 175 seconds green, 5 seconds yellow, and 180 seconds red. There's only one stoplight. It's at Main and Academy. It's a doozy. Given that I stop at the light, in other words, given that the light's red, what's the probability that I wait at most 60 seconds? So let's define the random variable t as the time I spend waiting. And I want to find the probability that I wait at most 60 seconds. That t is less than or equal to 60. Because the time I wait does not depend on when I get there, notice it's the only light. If there were several lights I had to stop through, then it wouldn't be a uniform distribution. But because it's the only light, it is a uniform distribution. Because there's a definite lower and upper bound. The lowest that I will stop there will be for 0 seconds, and the highest that I'll stop there will be 180 seconds. Definite upper and lower bound. It's uniform distribution. We now have that t, the time I spend waiting at the light in seconds, is distributed according to uniform with parameters 0 and 180, or with minimum 0 and maximum 180 seconds. And again, we have to calculate probability t is less than or equal to 60, that I wait at most 60 seconds. The outside rectangle is the distribution of t. Specifically, it's the probability density function of t. The dark blue is the area that I want to calculate. It's the probability t is less than or equal to 60 seconds. To find the probability, it's just the area under the curve of the density curve, corresponding to this width. The height's 1 over 180. The width of the dark blue is 60, so the probability of waiting at most 60 seconds is just 60 over 180. This should ring some bells from chapter 4 when you were talking about equally likely events. Because the PDF of the uniform is just a rectangle, and because areas of PDFs are probabilities, and I want to emphasize that again, areas in PDFs are the probabilities. We just need to calculate the region of t less than or equal to 60. Height times width. So 33.3% chance that I wait at most 60 seconds. For the uniform, this is easy to do in our heads. If we want to use R, here's how we use R. Again, we're looking for a probability of t being less than or equal to something, so we use the p version. The stem for the uniform is UNIF. We're looking for the probability t is less than or equal to 60. And then we specify the parameters of the uniform. Min equals 0, max equals 180. And the keywords are min and max, not A and B. The CDF of a probability distribution, recall, is defined as a probability that the random variable is less than or equal to some value. Traditionally, we give this a capital F. For continuous distributions without knowledge of calculus, this is frequently rather difficult to calculate. However, for the uniform, we can just rely on middle school geometry. So we're back to our generic uniform distribution, ranges from A to B, which means the height is 1 over B minus A. We're going to let x move between A and B, and we need to calculate this area here. That's pretty easy. The area of this is just x minus A divided by B minus A. And surprise, you just calculated the CDF function. This is the CDF function. So if I want to calculate the probability that x is less than or equal to 6, I'd put 6 in here for x. 6 in here for x. And I would have to know A and B from the definition of the uniform. I want to be clear. Calculating CDF functions usually requires calculus. Usually requires integration. But for those who've had calculus, integration is just a fast way of finding areas. And in this case, we've got geometry to help us find the area. The quantile function is the inverse of the CDF. We've bumped into the quantile function several times in the past. The quantile function is a function of P. The CDF is a function of x. It's the same relationship here, by the way. CDF, it's a function of x that calculates P. Quantile function is a function of P that calculates x. They're inverses. So from the CDF, we know that P is equal to x minus A over B minus A. This is for the uniform. All we have to do is solve for x. So x is equal to P times the width plus A, the starting point. So this thing on the left is the quantile function. You're given P, you solve it for x. The first line, the thing on the right, was the CDF. You're given x to calculate P. Inverse functions. So here's the quantile function. We can use a capital Q to symbolize it. The quantile function for the uniform is just P times the width plus A, the starting point. So here's what we've learned in this slide deck. Actually, let's go back a page. So how can I use this quantile function? I can use it to calculate the median. Remember, the median is the 50th percentile. So to calculate the median of this uniform distribution, we put 0.5 in for P, 0.5 in for P, and solve. If we know what B and A are, we can come up with a number. If we don't know what B and A are, then we just got an expression. I will leave it as an exercise for you to show that the median of a uniform distribution is equal to the mean of the uniform distribution. All it takes is understanding what the quantile function is and a little simple algebra. So here's what we learned in this slide deck. Actually, before we get to this, let's go to our intra-lecture questions. There's 3 of them. Again, write the question over on the left-hand side of your notes, answer below it so you can transfer that into Moodle. Question 1, what is the difference between a discrete and a continuous random variable? Question 2, what is the definition of a uniform random variable? And question 3, what are the 2 parameters of a uniform distribution? Remember, you do have the pause button to use. Okay, let's go on to the uniform summary now. Here's what we learned in this slide deck. Continuous random variables describe different phenomena than discrete random variables. They describe things that are continuous instead of counts. In a discrete random variable, you talk about the probability mass function, which actually does give you a probability. In continuous, you talk about a probability density function, which gives you a likelihood. And you have to calculate areas in order to turn that likelihood into a probability. Probability is the area under the PDF curve. The CDF is probability that the random variable is less than or equal to some value. Uniform distribution describes a random variable where all values are equally likely. The mean of a uniform random variable is a plus b over 2. Turns out that that's also the median, and I gave you that as a fun exercise. Future, we're going to look at the exponential and normal distributions. We're going to practice calculating probabilities using formulas, tables, and R. Going to continue thinking about the relationship between random variables around us and their distributions. The key part for chapters 4, 5, and 6 is starting to look at the world around us and think in terms of probability distributions. Here's the 4 R functions. Notice the stem for each is UNIF for uniform. For the density function, the PDF, it's just D, uniform. Now we see what the D actually means. For the cumulative probability, it's P. For a random sample from this distribution, it's R. And then the quantile function is Q. And while we were here, we calculated the CDF. We calculated the PDF as well. And we calculated the quantile function by hand. We realized it's not that difficult. But let's be clear, it's not that difficult for this distribution. Once you go beyond something as simple as the uniform, it begins to get much more difficult. And sometimes you can't even determine what the quantile function or the CDF function is. It may not exist. The readings are, for starters, Appendix B1 and B2. There's nothing in Hawks. And uniform distribution continuous in Wikipedia. Now, this is as far as you have to go. If you've taken some calculus and you want to see how to use it, I give you the calculus extra. But if you don't know calculus, skip over this and you will lose nothing. So how does one directly calculate the expected value for a continuous distribution? You use calculus. Refer back to the discrete case for the expected value. It was x times the probability of x added up over everything in the sample space. In the continuous case, you're integrating over the sample space of x times the probability density function. So this is the definition of the expected value in the continuous case. Similarly, this is the formula for the variance in the continuous case. Notice again there's an x minus mu squared, and this f of x isn't a probability, but it sure looks like that's where the probability was in the discrete case. And instead of adding, you're integrating. There's another formula for the variance that's equivalent, and sometimes it's easier to use. Sometimes it's not. So let's see how to use these formulas. Expected value of x is the integral over the sample space of x times the density, dx. Sample space is all values between a and b. Of x times the density is just 1 over b minus a, dx. 1 over b minus a is a constant, so it can be pulled out. Integral of x dx is x squared over 2. X squared over 2. There's that 1 over b minus a, and it's evaluated between b and a, between x equals a and x equals b. X equals b, this is b squared over 2 times 1 minus b over a, subtracting off the evaluation at the lower bound, a squared, which gives us this next line. And now we can do some algebra stuff. B squared minus a squared is b minus a times b plus a. Why did I know to do that? Well, there's a b minus a out here, and I knew this was the difference of squares. So the b minus a's cancel, and I'm left with a plus b over 2. Variance, same idea. I'm using the second formula for the variance, calculating what's called the second moment. It's just the integral over the sample space of x squared times f of x dx, and then I'll subtract off the mean squared. Integral of x squared dx is x cubed over 3 times 1 over b minus a, evaluating between b and a, so it's b cubed minus a cubed over 3. And b cubed minus a cubed has a b minus a term to it. B cubed minus a cubed knows b minus a times b squared plus ab plus a squared. Now we got some canceling there going away. I combine these two fractions, a 1/3 and a 1/4. Common denominator is the 12. Ah, that's where the 12 comes from. Common denominator is 12, so this becomes 4 over 12, and this is 3 over 12. There's the 4, there's the 3. Cancels. Distribute the 4, distribute the 3. Combine like terms. B squared minus 2ab plus a squared we know is equal to b minus a squared. It's amazing how much high school algebra does come in handy sometimes. Which gives us our formula for the variance. Now it makes sense, the b minus a squared. I mean, the wider the interval, the more uncertain we are in the outcome, so it makes sense that the variance would depend on b minus a squared. Now we see where the 12 comes from. It comes from combining these two parts. And that's it for the Calculus Extra. Again, if you haven't had calculus, you shouldn't have watched that. And if you have had calculus, you see why you've had calculus. Take care. Hello, and welcome to the second lecture of Chapter 6. This one covers the exponential distribution, and the previous one covered the uniform distribution. The uniform distribution was very good at modeling stuff that had a definite lower and a definite upper bound, and was continuous, and you knew nothing else about it, other than it had a definite lower, a definite upper, and was a continuous random variable. An exponential distribution will be very useful when you've got a continuous random variable that has a definite lower bound of 0 and no hard upper bound. So it's bounded on one side. Examples of this would be wait times. So by the end of this lecture, you should be able to determine which random variables may follow an exponential distribution, specify the characteristics of an exponential distribution, compare and contrast exponential with uniform, calculate probabilities using the CDF, and quantiles using the CDF. So here's the characteristics. It's a continuous distribution, describes a random variable whose probability of occurring decreases with time. It's frequently used to model, quote, time until something occurs when there is no upper bound. We say x follows or has a distribution of an exponential. The parameter for an exponential is lambda. Lambda is the rate of the thing happening. Sample space is from 0 to infinity. There is no upper bound. There is a lower bound of 0, but there's no upper bound. Expected value is 1 over lambda. The variance is 1 over lambda squared, which means that the standard deviation and the expected value of the exponential are identical, 1 over lambda. The rate of something happening, if we remember our physics, the rate of 1 divided by the rate is just the frequency. So it makes sense that the expected value would be 1 over the rate, because it's an average frequency of it happening. This is what the exponential distribution looks like. Smooth, declining. The height happens at lambda when x equals 0. The probability density function is lambda times e to the power of negative lambda x for x greater than 0 and 0 otherwise. And again, it's important. Probabilities are areas under the density curve. Notice there's no rectangles here for us to play with, so calculating those areas is going to be a bit more difficult than it was in the uniform case. Let's go into 2 examples. Time between when I fill my bird feeder with seed and when Chunky the squirrel starts eating from the feeder follows an exponential distribution with an average time of 10 seconds. In other words, if we define t as the time in seconds until Chunky raids the bird feeder, t follows an exponential distribution with lambda equal to 1 over 10. Lambda is 1 over the mean. The mean is 1 over lambda. Lambda is 1 over the mean. We're given the average time is, the mean time is 10 seconds. So what's the probability that he waits at most a half minute before chowing down on some awesome seed? At most a half minute, so we're looking at the probability of t being less than or equal to 30. Dark color is what we need to calculate. Remember again, for continuous random variables, areas under the PDF curve are the probabilities. No rectangles to use. Can't use the tricks from last lecture. We're going to have to jump directly to the CDF function. I leave it as a proof for those who enjoy calculus to prove that this is indeed the CDF for the exponential distribution. What we did with the uniform, remember, is we created this ourselves. For the exponential, it's given to us, and we use it. For the normal, which is the next distribution in the next lecture, we realize there is no function, and we have to use something else. So we want to find the probability t less than or equal to 30. It's just the CDF at 30. Lambda is 0.1, x is 30. Here's the CDF function. 95% probability that Chunky will wait no more than 30 seconds to raid the feeder. This was a little bit more involved. If we got R open, might as well use R to do the calculations. It's a less than or equal to, so this is a p. The stem for the exponential is exp. We want to find the probability that t is less than or equal to 30, and we're told lambda is equal to 1/10. We're not calling it lambda here, we're calling it rate. So be aware that this has to be rate. Example 2. Time I wait until the Gold Express bus comes follows an exponential distribution. My average wait time is 5 minutes. In this cold of winter, it takes 10 minutes for frostbite to start. So given this, what's the probability that I will have frostbite before the bus arrives? In other words, given that 1 over lambda is 5, what's the probability that t is greater than 10? This is not a CDF, it has to be in the form of a less than or equal to. But using the complements rule, we can easily change this into from t greater than 10 to 1 minus probability of t being less than or equal to 10. Chapter 4 pops up every once in a while. This is probably the most important thing from Chapter 4, the complements rule. So now all we do is calculate the probability t is less than or equal to 10. That's the CDF at 10, given that lambda is 0.20. 1 over 5 is 0.20. Plug, chug, 13.5% chance that I get frostbite. Or it's 1 minus p exp of 10. Rate equals 0.2. Again, it's p because we're looking at the CDF function. It's exp because it's an exponential distribution. We can also calculate the median. Remember, the median is the value x tilde such that the CDF at x tilde is 1/2. The part on the left is the CDF function evaluated at x tilde, which is just 1 minus e to the negative lambda x tilde. 0.5 stays on the right. And all we're doing now is solving for x tilde. Subtract 1 from both sides, and then multiply through by -1. Gets us here. Take the natural log of both sides. Gets us here. Divide by -0.2. Gets us here. Remember, the log of 1/2 is negative log of 2. So the median is 3.466 minutes. And we can show in general that the median is just mu, the mean, times log 2. And this is the natural log of 2. Or instead of doing all this calculation, in R it's just Q because we're looking at the quantile at 0.5. This will give us the median. EXP because it's an exponential, and the rate is 1/5. It's 1 over mu. We could also calculate the 90th percentile. Set the CDF equal to 0.9 and solve for x star. Or just put 0.9 in the quantile function and solve. Before we get to the summary, let's go ahead and put in the intra-lecture questions. There's 3 of them as usual. And again, as usual, write these on the left side of your notes, answer them so you can transfer them into Moodle. 1. Give an example of a random variable that follows an exponential distribution, something other than the 2 examples that we did today. 2. What is the parameter of an exponential distribution? And 3. What are the mean and standard deviation of an exponential distribution? Give me the formula for those. And I did say mean and standard deviation. The reason I'm asking this is to set something in your mind so that you can contrast the exponential with the Poisson, because exponential and Poisson both use lambda as the parameter. So here's the summary. We reminded ourselves that probability is the area under the PDF curve. The CDF function is probability of x less than or equal to x. In this case, we needed calculus to find the CDF. Although the calculus extra is where we prove it, I just threw the formula at you. Exponential distribution describes a wait time random variable, the time until something happens. The mean and variance of an exponential random variable are 1 over lambda and 1 over lambda squared respectively, meaning that the standard deviation is going to be the square root of the variance. In other words, the standard deviation is 1 over lambda. Last distribution is the normal distribution. Normal distribution is the key distribution from Chapter 6. When we get to Chapter 7 and talk about the central limit theorem, I'll drive this home as to why the normal distribution is the most important. There is no formula to calculate the normal distribution probabilities. We can either use the table at the end of the book, no, or we can use R to do it. We're going to look at quantiles, otherwise known as percentiles, and we're going to, again, understand the difference between discrete and continuous random variables. Here are the R functions again. All of them have the stem exp for the expected value, and all of them require that you specify what their rate is, and the rate here is lambda. D for the density, the little f of x. P for the cumulative probability, the capital F of x. R to generate a random value. Q for the quantile. So the median, we'd use the Q exp and then put in 0.5. For the 10th percentile, we'd put in 0.1. For the 99th percentile, we'd put in 0.99. Nothing in Hawks about this. R for starters, it's appendix B5. Wikipedia's got the exponential distribution. In the Wikipedia page, you'll see that there's actually 2 parameterizations for the exponential. The one that we're using in class, which is lambda, and the one that the engineers tend to use theta, if memory serves me right. That's kind of the end. Again, if you are not a calculus person, you can stop here. If you are a calculus person, you want to see how to actually create that CDF function, continue on. So here's a proof of the exponential CDF. Remember the definition of the CDF, it's the probability, otherwise an area under this under the PDF curve, of the random variable being less than or equal to x. For the exponential, that means that you're integrating from 0 to that x value. F of t is the exponential PDF, probability density function, dt. Substitute f of t is just lambda e to the negative lambda t. This lambda doesn't depend upon t, so it can be pulled out. So we're integrating from 0 to x of e to the negative lambda t dt. Not too difficult. The integral of e to the negative lambda t is just negative 1 over lambda times e to the minus lambda t. Evaluated from t is 0 to x. This lambda and this lambda cancel, so we're left with just a negative e to the negative lambda t. Evaluated at x, subtract off this thing evaluated at 0. Here it is evaluated at x, subtract off, evaluated at 0. Notice e to the 0 is equal to 1. Subtracting off a negative 1 means you're adding 1. No simplification in the first term. So we're left with CDF being 1 minus e to the negative lambda x. Again, this is for those who want to see that their calculus time was well spent, that it's used a lot in statistics and probability theory, and I'm sure it's used other places, but really I don't care. It's all about the statistics and probability and how we're using the mathematics. So, I'm done. Have a good one. Hello and welcome to Chapter 6 from Hawks. This lecture will cover section 6.1 through 6.4. All four of those discuss the normal distribution. Because we spent some time building up things with the uniform distribution and the exponential distribution, we'll be able to cover the normal distribution in one rather lengthy lecture, but still just one lecture. By the end of this lecture, you should be able to discuss the differences between the uniform, exponential, and normal distributions, know the expected value and the mean of a normally distributed random variable. It's kind of tricky because remember, the mean and the expected value are the same thing. Sketch the graph of a normal distribution. Realize that capital N normal and lowercase n normal mean different things. The capital N normal refers to the distribution, and lowercase n normal just means typical or not surprising. You'll be able to calculate probabilities of normal random variables and quantiles of normal random variables. So here's the arc that we've been working on. Chapter 5, we looked at discrete distributions, which included probability mass functions, PMF, calculated means, variances, sample spaces for those discrete distributions. The discrete distributions we looked at were the Bernoulli, the binomial, the Poisson, and the hypergeometric. We also looked at generic discrete distributions in the first section of Chapter 5. Chapter 6 looks at continuous distributions. I introduced the uniform distribution so you could get an idea that probabilities for continuous distributions were actually areas under the PDF curve, which meant the PDF curve was not probabilities, they were probability densities or likelihoods. We used the uniform to illustrate how to calculate the CDF, the cumulative distribution function, using simple high school geometry. And then we moved on to look at how to calculate the mean, the variance, the sample space, the median, other quantiles on the uniform. So that section on the uniform just laid the foundation for all the other important features of continuous distributions. The second section was the exponential, where we did the same thing, but then we realized creating that CDF function, that cumulative distribution function, was not easy. And in that case, we had to use calculus to get it. Or it was given to us fully formed out of the sea foam. Your choice. So we went from the uniform, where we created it ourselves and got a good feel for how it was created, to the exponential, where we had to use calculus if we wanted to see how it was created. To this lecture, it's normal, and there is no CDF function, which means that in the uniform, we really didn't have to pay attention to the CDF. We could calculate those probabilities in our head. Exponential, we needed to use the CDF, but it was a nice simple form that we could use. For the normal, we got to go to a table or to a computer. And for much of the second half of the 19th century, a lot of effort was spent trying to create those tables. It was pretty easy in the early 19th century to create a CDF function for values of, we're going to see, z between -1 and +1. That was pretty easy to do. Once you got outside that -1 to +1 realm, it got harder and harder and harder to get good estimates of those probabilities. With the advent of computers, it's much easier. I mean, we could even do it. Today we're going to look at the normal, the probability density function for it, the CDF function for it, the mean variance sample space, median, quantiles, aka percentiles, same stuff. We're going to see the function, the PDF function. We're going to realize, okay, we don't need to memorize that. We're going to see that we can't write out the CDF function in any meaningful way, but we'll find out ways of calculating. The Gaussian distribution apparently was named, or no, apparently about it, it was named after Carl Friedrich Gauss, who advocated for its use, aka created it, or at least we think he created it. Those who stem from the German school of thought think he created it. His first paper, though, was 1809. It was Laplace who published a paper earlier than that using this distribution. That's why the French descendants call this the Gauss-Laplace, or just the Laplace distribution. But we're going to call it the normal distribution. Gauss said, hey, wait a minute, Laplace, I was working on this way back in 1794. No evidence of it except Gauss's word. Normal distribution arises from modeling observed randomness in astronomical and geodetic data. It arises in variables that have a specific expected value but demonstrate some minor random variation above and below. So, for instance, this pop that I'm drinking now says that it contains 100 milligrams of caffeine. So I would not be surprised if the distribution of caffeine in these bottles followed a normal curve. That is, the mean would be 100 and there'd be some variation above and below, because you can't get exactly 100 milligrams of caffeine every time. There are two parameters to the Gaussian distribution, or to the normal distribution: the mean and the standard deviation, mu and sigma. The most important distribution in statistics because of the central limit theorem, which we'll see in chapter 7. So for the record, if x, a random variable, follows or is distributed according to a normal distribution with mean mu and standard deviation sigma, then the PDF is lowercase f of x is this thing. Notice that the PDF depends on mu and sigma. Depends on sigma in a couple places. However, recall to chapter 3 when we looked at the standardized score, we can subtract off mu divided by sigma, and we actually come up with another normal distribution. It's a normal distribution that does not depend upon mu and sigma. It's a standard normal distribution with mean 0, standard deviation of 1. So the normal distribution has two parameters, mu and sigma. The standard normal distribution has no parameters. And it's the standard normal that is tabulated in books. Here's a graph of the standard normal PDF. Notice that it goes off on both sides forever. This should raise some memories of the empirical rule. You will see sometimes that the PDF is symbolized with a lowercase phi, Greek letter phi, lowercase phi, lowercase f, because it's a PDF. And the CDF will be an uppercase phi. I don't think I have an uppercase phi on here. Here's the mean. Notice it's also the median. Normal distribution is symmetric, so mean and median will be the same. Notice also it's the most likely value because the likelihood function, the PDF, is highest there. So this is the highest likely, or the most likely, value from this distribution. So the normal distribution, the mean, median, and mode are the same value. Here are the standard deviations. At this point, you should be able to say, hey, I know what percent of the data, or of this distribution, is between -1 and +1. And what percent is that? Nope. Oh, I'm sorry, I misheard you. Yeah, 68%. And what percent is between -2 and +2? Yep, about 95%. And between -3 and +3 is 99.7%-ish. Call the normal distribution is continuous, but it's not rectangular, and it can be proven that the CDF cannot be written out. Hence, late 19th century, early 20th century as well, working on estimating those probabilities. So you have to use a table or a computer. Table 1 tabulates this CDF. Computer calculations are easier to perform, however. They're more accurate and they are more precise. The stem is norm. You have to specify the mean, M, and the standard deviation, S. P for the cumulative probability, Q for the quantile, R for generating random values. The PQR is the same as it has been with all the other probability distributions. Stem is norm, and you have to specify M and S. So some examples. Intelligence quotient. By design, the IQ measures in the United States follow a normal distribution with mu equal to 100 and sigma equal to 15. This is by design. This is how they create this test. What proportion of the U.S. population has an IQ less than 90? In other words, what random variable do I use? In other words, if this is the distribution of IQs in the United States, I want to find the area under the curve less than 90. The purple area. I want to calculate the probability that x is less than or equal to 90. Given that x follows a normal distribution with mean, expected value of 100, and standard deviation of 15. Here it is in R. P for cumulative probability, norm is the stem for the normal, 90 is the value. We're specifying M is equal to 100 and S is equal to 15. This comes out to be about a quarter of the population. Wait a minute, I can hear you saying. I thought this P only worked when it was less than or equal to. What is going on here? Are you trying to pull something over on us? The answer is no. Remember that x follows a continuous distribution. In this case, it's a normal distribution. That means that the probability of x equaling 90 exactly is 0. Think back to the uniform distribution. It's an area, so it's the base times the height. If the base consists of a single point, then the width is 0. And a width of 0 times whatever height is going to give you a probability of 0. So for continuous distributions, less than or equal to are going to be exactly the same. What IQ value separates the lower 30 from the upper 70%? So we're looking for an IQ value. That tells me I'm going to be using a quantile. I'm looking for the 30th quantile, or the 30th percentile. So I'm looking for this value here, such that 30% is in purple. Q for quantile, we're looking at the 30th percentile, so it's 0.3 here. Then we specify the mean and standard deviation. 92.13399. So approximately 30% of Americans have an IQ score less than 92.13399, and approximately 70% of Americans, that's everyone else, have an IQ of more than 92.13399. 30%. It's pretty frequent still. So in other words, IQ of 90 and no big deal. By design, IQs, etc., what's the proportion of Americans that with an IQ score between, we haven't dealt with any between calculations yet, between 87 and 122. So we want this purple area, between 87 and 122. For calculating cumulative probabilities, it's got to be in the form of less than or equal to's. So I can do less than or equal to 122, but that covers everything here, not just what we want. But notice that this region is less than 122 minus less than 87. Looking for this. This is just the cumulative probability at the upper minus the cumulative probability at the lower. So approximately 75% of Americans have an IQ between 87 and 122. That's a lot. And now we'll go for above. We did a less than, a between, now we'll do an above. It's proportion of Americans have an IQ above 90. So this purple area. Complements rule, this purple area is just 1 minus the white area. 1 minus the white area. So again, about 3/4 of Americans have an IQ above 90. So let's do a learning check. I'm going to ask some questions. I'll pause, you answer them on your own out loud, because dog's watching you and you really do want to talk to it. What type of random variable will have a normal distribution? A random variable with a definite target and some random variation added to it will tend to have a normal distribution. What's the difference between capital N normal and lower n normal? Capital N normal refers to the distribution itself. Lower n normal refers to the fact that something is not unexpected. What is the sample space of a normal random variable? All real values. There is neither a lower bound nor an upper bound. What is the expected value of a normal random variable? Very good. That's mu. It's one of the parameters. What is the variance of a normal random variable? Yes, sigma squared. It's the square of one of the other parameters. Remember, there are two parameters, mu and sigma. The variance is just the square of sigma. What R function is used to calculate cumulative probability for normal? Yep, cumulative probability, so it starts with a P. For normal random variables, so it's P norm. And what R function is used to calculate the quantiles? Q norm. Q for quantiles, norm for normal random variable. In the future, we're going to keep working with the normal distribution simply because of the central limit theorem. And we're going to use this normal distribution to estimate population parameters. But this last one will be the second half of the course. Here are the R functions, none too surprising. The stem is norm, then we got the D, P, R, and Q. Notice when we were dealing with the discretes, we used the D a lot. Now that we've moved on continuous, we really don't use the D. I use the D norm to create those graphs, but really you don't use the D norm function at all. You focus on the P norm and the Q norm and the R norm. Here are some readings for you. R for starters, Appendix B3, C1 and C2. And Hawk, section 6.1 to 6.4. Normal distribution in Wikipedia is a good one. I haven't done the intra-lecture quiz or questions. Here we go. Question 1, give an example of a random variable that follows a normal distribution. Question 2, what are the two parameters of a normal distribution? And question 3, what are the mean and standard deviation of a normal distribution? 3 again will be really easy. 2 will be pretty easy. 1, that'll take some thought, but it'll be easy. Oops, went too far. So I guess I'm done. Hello and welcome to this last section of Chapter 6. This is where we're going to use the normal distribution to approximate the binomial distribution. Notice this is rather interesting because the normal distribution is continuous and the binomial distribution is discrete. So indeed we can approximate discrete distributions using the continuous distributions. So by the end of this lecture you're going to be able to describe the normal and the binomial distributions. You're going to see how the normal can be used to approximate the binomial. You're going to calculate the approximate binomial probabilities and understanding why the binomial is useful even if we have a computer to calculate them exactly. So here's the arc. We've examined recently discrete distributions, of which the binomial is 1, and continuous distributions, of which the normal is 1. We looked at probability mass functions, means, variances, sample spaces. For the discretes, we've looked at probability density functions, means, variances, sample spaces. The CDF can be applied to both discrete and continuous, as can median and quantiles. Today we're going to approximate one distribution with another. So the first thing we have to do is explain what we mean by approximating one distribution with another. The short answer is that the cumulative probabilities are close. That is, if x1 and x2 are different distributions that are approximately the same, then this relationship holds for all values of little x. Of course, there is a whole lot of detail hidden in that little tilde, that approximation sign. If x1 is approximately the same as x2, how close is close enough? How approximate is necessary? It's a question of precision, and we leave that up to the scientist, not the statistician. The scientist comes to me and says, I need the probabilities to be within 0.003 of each other. From that information, I can say, okay, I need a sample size of 1,300, or something like that. So we're going to approximate the binomial x1 with the normal x2. That is, we'd like to determine some rules on NP, mu, and sigma to ensure that this relationship, this approximation relationship, is true. Now, surprisingly, it's not as difficult as it seems to get a good first-order approximation. What do we remember about the binomial? We remember these 5 requirements. And again, you need to have these memorized. The number of trials is known. Each trial is a Bernoulli trial. Success probability is constant. Trials are independent. And the random variable is the number of successes in those trials. This led to an expected value and variance of NP and NP1 minus P. So from this, it's natural for us to see just how well this x2 distribution, which is a normal, how well this approximates the binomial, where the mean is NP and the variance is NP1 minus P. In other words, we want to see how far apart those CDFs are. So here's the CDF of a binomial 5.1. N is 5, P is 0.1. This is CDF. Here's the graph of a normal, 0.5 and 0.45. So this normal is, according to the rule, this will be the x2 distribution. And this should illustrate how close they are. Midway between the numbers 1, 2, 3, 4, 5, it's right on, or really, really close. The closer you are to one of the integers, the worse off it is. In fact, here is a animated graphic of the difference in the CDFs between the binomial and the normal. Sample size is up here. This is the value of x, and the height here for any value of x is binomial CDF minus normal CDF. Notice we have spikes at the integer values. Now, I would love to press play, but unfortunately this Adobe Acrobat type program isn't Adobe Acrobat, so I'm going to have to open up this file separately. Notice sample size is changing. Notice also the worst is getting smaller and smaller and smaller. So here we are at about 70. The worst is 0.05. We're coming up on 100. The worst looks to be about 0.045. And we just keep this running, and notice that the error, the worst error, tends to go to 0 as the sample size increases. But notice that it doesn't go to 0 too quickly. Here we are at the sample size of about 200, coming up on 200, and we're going to see that's only about 0.03. Worst error is 0.03, and we start over again. And I don't know how to stop that from continuing. 0.03 as the difference between the normal and the binomial CDF. That's 0.03, which is a probability, so that's a large difference. So if the correct probability is 0.57, then this error could be anywhere from, or this would be anywhere from 0.54 to 0.60. And that's a big range, big error introduced. But as you saw, as the sample size increased, that the worst absolute error went to 0. So large sample size, we can go ahead and say the normal and the binomial are close enough. That also kind of leads to the physicist who tells me I need to be within 0.03. 0.03, I can come back and say, okay, sample size needs to be at least 200. Or the physicist comes to me and she says I want it to be within 0.003. I'll come back with, okay, sample size needs to be at least 20,000 or whatever. So one conclusion is the approximation increases as values of n increase. We're going to see that again when we get to the central limit theorem in chapter 7. With additional exploration, we could come to a second conclusion that the approximation is better for values of p close to 0.5. The example I gave you, p was 0.1. So if p is close to 0.5, we don't need as large a sample size as we do if p is 0.1. So combining these two observations leads to the following, quote, rule of thumb. And this rule of thumb tends to change from source to source. The normal distribution is sufficiently close to the binomial if both np and n times 1 minus p are at least 5. I happen to think 15 or 20 is a better rule for that. And if I need a lot of precision, then I'll need NP to be at least 1,000 or maybe 2,000. And the approximation's improved by using, quote, a continuity correction of 0.5 added to or subtracted from the number value. We'll have an example of that shortly. This is not the best correction, but it's a good correction. So we're going to use a continuity correction factor to describe the area under the normal curve that approximates the probability that at least 2 people in a math class of 50 regularly cheat on their tests. Assume the number of people in the math class of 50 who consistently cheat on their tests has a binomial distribution with a mean of 5 and a standard deviation of 2.12. So in other words, if x is the number of students cheating in the class, x follows a binomial of 50 with a p of 0.1. We need to calculate the probability that x is greater than 2. So we're going to begin by converting the discrete number 2 into an interval by adding 0.5 and subtracting 0.5 from it. The discrete number 2 is changed to a continuous interval from 1.5 to 2.5. Here's a picture of that. So for the discrete, we could just use 2. For the continuous, because the probability of x equal to is 0, just like x equal to any single number, we need to change it into an interval. So that 2 will be replaced by the interval from 1.5 to 2.5. Now we're going to draw a normal curve with the mean of 5 and a standard deviation of 2.12. Those were given to us. And indicate the interval from 1.5 to 2.5 to represent the number 2. That's what this is. The red curve's the normal of mean 5, standard deviation of 2.12. And I've got the value of 2 in the double shaded, or the shaded and hashed. Now we're going to shade the area corresponding to the phrase, quote, at least 2, because we need to calculate the probability of at least 2. And that's the blue shaded area. It's this hashed part, which is 2 and above. So in other words, if x is binomial and y is the normal approximation, probability of x greater than 2 is about probability of y greater than or equal to 1.5, because it's everything blue. If I were calculating the probability of x being less than 2, it would be y less than or equal to 2.5. Use a normal distribution to estimate the probability of more than 55 girls being born in 100 births. So exactly, we need to calculate probability x is greater than 55. Given x follows a binomial distribution out of 100, p of 0.5. Using a normal approximation, that means we're going to define a y variable to follow a normal distribution. Y follow a normal distribution with the expected value of 50, 100 times 0.5, and variance of 100 times 0.5 times 1 minus 0.5. And we're going to calculate the probability that y is greater than that y is greater than 54.5. And there we go. Now we could calculate the exact answer of 13%. 1356 to 65. Notice how close the approximation is, though. This is using the p-binom, and this is using the p-norm. Very close. And the sample size is only 100. I say it's very close. We're off on the fifth digit. So if I need precision beyond the 5th digit, then I'm going to have a larger sample size. If I did not use the continuity correction, I'd be much further off. After many hours of studying, you believe you have a 90% probability of answering any given question correctly. Test is 50 true-false questions. Oh, that would be horrible if I gave you 50 true-false questions for the test. Or would it? Nah, I wouldn't do that. Assuming that your estimate is the true probability that you will answer a question correctly, let's estimate the probability that you'll miss no more than 4 questions. So each of the 50 true-false has a probability of 90% being right. We want to say missing no more than 4 questions, so the probability of missing will be 0.1. 50 questions, this is the exact distribution of x. This is the exact probability to calculate. We can approximate this binomial with a normal. Y will follow a normal distribution of expected value 50 times 0.1 and variance of 50 times 0.1 times 0.9. And we'd calculate the probability that y is less than or equal to 4.5. Oops, too far. 40%. The real answer is 43%, so I'm off by 2.5%. Many toothpaste commercials advertise that 3 out of 4 dentists recommend their brand of toothpaste. Using a normal distribution to estimate the probability that in a random survey of 400 dentists, so we'll be using random sampling, simple random sampling, exactly 300 will recommend brand X toothpaste. We're going to assume the commercials are correct, and therefore there's a 75% chance that any given dentist will recommend brand X. So if X is the number in that sample of 400, X follows exactly a binomial and a 400 p of 0.75, and we need to calculate exactly X equals 300. The approximation, y will follow a normal distribution, expected value of 400 times 0.75, variance of 400 times 0.75 times 0.25. And we need to calculate the probability that y is between 299.5 and 300.5. And we get 0.046, 04, 03, and the real answer is 0.046, 02, 432. So the normal distribution with the continuity correction did a very good job here as well. Without the continuity correction, this would be terrible. In fact, without the continuity correction, the probability estimated would be 0 because you'd be calculating the probability that y was equal to 300. So, learning check. What's meant by the normal distribution approximates the binomial. Correct. Their CDFs are, quote, close. What are 2 requirements for the approximation to be, quote, good? Right. N times p is at least 5, and n times 1 minus p is at least 5. Again, I would recommend higher numbers for those if I really, really care about the results. How do we make the approximation better? Yes, larger sample size. You'll find in statistics that a larger sample size solves a whole lot of problems. From the economic standpoint, however, larger sample size causes problems because it costs time, money, other resources to collect that larger sample size. What is a continuity correction? Why is it used? Very good. Continuity correction is used to help ensure that the normal approximation to the binomial is, quote, better. The continuity correction itself is to treat an equals as adding 0.5 and subtracting 0.5 and calculating that interval. In the future, we're going to explore the normal in greater detail. We're going to use the central limit theorem, which will be chapter 7, and discover that the binomial is not special, the normal distribution is. Here's a question that you may have. We have a computer We can easily calculate these binomial probabilities exactly. Why do we still need to approximate a binomial with the normal? And here's the answer. The examples that were given today were given where you could calculate exactly and approximately and compare, just so you get a feel for how good this approximation is. When we get to trying to estimate a single proportion, we're going to stick with the exact way of doing it, using the binomial distribution and everything we know about the binomial. However, when we start to look at comparing two proportions, or trying to estimate the difference between two proportions, two population proportions, we won't be able to use an exact distribution because we would need to find the distribution of the sum of two binomials, and that doesn't exist. However, we do know the distribution of the sum of two normals. That's a normal distribution. So we would have to use the normal approximation when we start comparing two proportions. Until we get there, we can use the exact form. Now with that said, some books, and I think Hawkes does this, Hawkes will use the normal approximation for even the one population parameter, population proportion estimating. So there is reason to look at this approximating the binomial, not just it's the next section in the chapter. Here are the R functions. We've seen these already, d binom, p binom, and p norm. Here's some readings. Appendix C, an R for starters, and Hawkes section 6.5, and then Wikipedia central limit theorem. Appendix C and the central limit theorem in Wikipedia will give you a good background for chapter 7. And this approximating the binomial distribution with the normal is actually a result of the central limit theorem. So questions, where are those questions? There they go. Question 1. Again, I recommend writing these questions in the left-hand side of your notes, answering them below so you can put them into Moodle quiz. What does it mean for one distribution to approximate another? Question 2. What are the mean and the standard deviation of a binomial? Question 3. What are the mean and standard deviation of a normal distribution? And that's it. Take care. Hello and welcome to section 7.1, where we introduce the central limit theorem. Central limit theorem, I would argue, is the most important theorem in all of introductory statistics. In fact, I'd argue it's the most important theorem in all of statistics. It helps to explain that when we have data that comes from a continuous distribution and we're trying to estimate the population mean, we don't really care that much about the distribution of the data. We just, quote, pretend that the data comes from a normal distribution because the central limit theorem says, hey, regardless of where the data comes from, the sample means follow a normal distribution. And it's the sample means that we're going to use to understand our population mean in the future. So from this point forward, when we're dealing with continuous data, the sample means are going to follow a normal distribution, or it's going to look like a normal distribution. And we see that in Lab C. So by the end of this lecture, you're going to be able to state the central limit theorem, state the requirements for applying it, and state its consequences. So in recent computing activities, we've examined drawing random samples from a known distribution. We've looked at calculating sample means from subsets of those distributions. We've created histograms of the distributions of those sample means. Today we're going to examine the central limit theorem, which kind of gives a mathematical explanation for everything that we've observed about those sample mean distributions. So here's the statement of the central limit theorem. Let x be a random variable with a mean, we're going to call that mean mu, and a finite variance, sigma squared. We're going to draw a random sample of size n from this distribution. So that first paragraph is all about the data itself. The data comes from some distribution with a mean and a variance. Second paragraph. Then the distribution of the sample sums converges to a normal distribution as n gets larger. So the first paragraph said we don't care about the distribution of the data. Second paragraph says, therefore, the distribution of the sample sums converges to a normal distribution. So the data could be exponential, the data could be uniform, the data could be binomial for all we care. It's the sample sums that are going to be normally distributed as n gets larger. Specifically, this thing on the left is just how we represent sample sums. We're adding up. This is a big summation, adding up over all n values in our sample, those values. It converges in distribution. That's what the d on top of the arrow means. It converges in distribution to a normal with the expected value of n times mu and a variance of n times sigma squared. We've actually kind of seen something like this in the past, but let's keep working forward. The proof of this theorem is beyond the scope of this course. I think the first time you get to see it is in Math 321. Happens at the end of Math 321 after you've learned about these things called moment-generating functions. So our first intra-lecture question is here. Again, on the left-hand side of your notes, write the question, write the answers, so that you can come back to it later. Remember, you got the pause button. So there are three main consequences. Central limit theorem tells us the following. One, it tells us that the sum of independent random variables is more normal than the distribution of the variable itself. Of course, if the data do come from a normal distribution, you already start at normal, so you don't have any place to go. But if you start at uniform, it takes a little bit to get to normal. If you start at exponential, it takes a little bit longer to get to normal. Recall that the binomial is the sum of independent Bernoulli random variables. We use that fact to prove things about the binomial, specifically the expected value and the expected value and the variance. Poisson happens to be the sum of independent Poissons. We've alluded to that in the past. But that means that as n increases, the binomial becomes more normal. And as lambda increases, the Poisson becomes more normal. It's because the Poisson is just the sum of independent Poissons, and a binomial is the sum of independent Bernoullis. It's kind of powerful right there. Second consequence is because the sample mean is just the sample sum divided by a constant, the central limit theorem tells us that the distribution of sample means will tend towards normal. And again, if the data starts with a normal, this tending towards happens immediately. If it starts with a uniform, it takes like 10 to get there. If it's an exponential, it takes like 50 or so. But eventually, those sample means will become as close to normally distributed as you want them to be. You just have to get a larger n sometimes. And the third, the speed of convergence depends on how closely the data are distributed to normal. The closer they are to normal, the faster. Thus, the normal, if the data actually do come from a normal distribution, then the sample means are immediately normal. The Poisson is closer to normal than many of the binomials, so you'd need a lambda smaller than the n for a binomial. So Poissons converge faster. Let's look at the next intra-lecture question. It's going to ask you about the uniform and the exponential. Oh, no, it won't. Well, it will pretty soon. So question 2 is state the second consequence of the central limit theorem. And then I'm going to pause. Then I'm going to go directly to question 3, which talks about the third consequence. Since the speed of convergence depends on how closely the data are to normal, as a missing L, which of these two will converge the fastest? If the data follow a uniform, will the sample means converge faster to the normal than if the data follow an exponential? Remember to write down the question on the left, answer it so that you can transfer it into Moodle. Again, if the data follow a uniform, will the sample means converge to normal faster than if the data follow an exponential? Pause, moving back. So here's one of the big uses that is used sometimes. Let x follow a binomial distribution. Remember, there are two parameters for binomial, n and p. We're going to use the central limit theorem to approximate the distribution of x. We actually did this back in section, I believe it was section 6.5. But here we're going to see why it actually works. Or we're going to apply a mathematical reasoning for why it works. Remember, the binomial is just the sum of n independent Bernoullis. That is, if y sub I follows that Bernoulli, then x, being the sum of those y's, follows a binomial of np. So according to the central limit theorem, since it's the sum of independent distributions, the x is going to be approximately normal with a mean and a variance. That mean is just going to be the mean of this binomial. Well, what's the mean of a binomial? It's n times p. And the variance is just going to be the variance of this binomial. Well, what's the variance of a binomial? N times p times 1 minus p. So this gets us directly to the approximation of the binomial with the normal in about one step. More importantly for us, okay, never mind. We're going to let x, for another example, follow a uniform AB. A is the minimum value, B is the maximum value. We're going to use the central limit theorem to estimate the distribution of the mean of a sample of size n. Remember that x bar, the mean, is just 1 over n times the sample total. And we represent the sample total this way. And so by the central limit theorem, t follows approximately. The dot on top of the tilde means approximately follows a normal distribution, n times mu, and n times sigma squared, where mu is the mean of the underlying distribution of the x distribution, and sigma squared is the variance of that underlying distribution of the x distribution. From our knowledge of the uniform, we know that the mean of the uniform is just a plus b over 2, and the variance is b minus a squared over 2. So the sample sum is approximately normally distributed with expected value n times a plus b over 2, and variance of n times b minus a squared over 12. Remember, the question was originally about the distribution of the sample mean, and x bar is just 1 over n times t. That means that x bar approximately, again, dot on top means approximately follows a normal distribution. Expected value of mu, n times mu divided by n, and n times sigma squared divided by n squared. So the expected value of x bar is a plus b over 2, which happens to be mu. And the variance of x bar is b minus a squared over 12n. Now notice something that we didn't notice before. The expected value of x bar is mu. The variance of x bar is smaller than the variance of x. So as n increases, the variance decreases to 0, which means these x bars that we actually measure from a sample, the observed x bars, are going to tend to be closer to the mu. So in other words, as n increases, the precision of our little x bar increases. So the big question that comes in here is, why is there an n in the denominator of the variance? Recall that the variance is defined as the sum of x minus mu squared times the probability of that x value. So the variance of a times x is just the sum of a times x minus a times mu squared times the probability of the x value. Factor out an a from both of these out front. That gives us an a squared times x minus mu squared times the probability of the x value. This is just a constant, has nothing to do with the I. Pull it out. So at a squared times the sum of the x minus mu squared times p of x. So the variance of ax is just a squared times the variance of x. In other words, where does that squaring come from? It comes from the fact that the random variable itself is squared in a variance. So when we found the variance of x bar, that was just the variance of 1 over n times t. Pull the 1 over n out front, it's 1 over n squared times the variance of t. There's 1 over n squared. This n times b minus a squared over 12, that's the variance of t. The n on top cancels with one of the n's on the bottom. That gets us our variance of x bar. So, a learning check. What is the main consequence for the central limit theorem? I'll just pause for a little bit. You can go ahead and hit the pause button to give yourself some more time. The main consequence for the central limit theorem is that the sample means will become more and more normal. What are the requirements for the central limit theorem? The expected value and variance both have to be finite, and the x's have to be independent. Why does this mean we should focus on the normal distribution as we move forward in the course? When we care to estimate the population mean, we're going to use the sample mean. And since the central limit theorem tells us the sample means are going to eventually follow a normal distribution as long as n is large enough, then we should just focus on this normal distribution. R for starters, this is Appendix C3. Hawks, this is Section 7.1. De Moivre-Laplace theorem is interesting. Of course, Wikipedia's got a really good entry on the central limit theorem. And that's the end for Section 7.1, the central limit theorem. And by the way, you will see the central limit theorem at least in the next 2 lectures, but in undergirding all lectures from this point forward in this course. So, enjoy! Hello and welcome to Section 7.2. Last section we looked at the central limit theorem. Here we're going to be applying the central limit theorem to the distribution of sample means. So by the end of this lecture you should be able to state the central limit theorem and to apply the central limit theorem to the problem of sampling distribution of the mean, or what most books just refer to as the sampling distribution. So here's the arc, what we've been talking about. So recently we've examined drawing random samples from a known distribution. We've calculated sample means from subsets of those distributions. We've created histograms of those distributions. We've seen that those histograms tell us that the sample mean distributions look pretty darn normal. In the last slide deck, we introduced the central limit theorem that says, yes, they do look pretty darn normal, and that's not an accident. We've looked at the central limit theorem and its requirements and its consequences. And the main consequence is the distribution, the sample means, tends towards normal as the sample size increases. So today we're going to examine the central limit theorem in terms of what it tells us specifically about the distribution of the sample mean. In the next lecture it'll be about the distribution of the sample proportion. But if you think back to section 7.1, in fact if you think back to when we first introduced the binomial distribution, we realize that the sample proportion and the sample mean are not that different at all. Mind blown. So here's the statement of the central limit theorem again. Let x be a random variable with a finite mean and finite variance. Let us draw a random sample of size n from this distribution. Remember, random sample means it's an independent sample. Each of those x values are independent of the others. And again, note that that first paragraph talks about the distribution of the data. So the data have a mean and a variance, and the data were generated from some sort of independent process. That's all we need from the data. The data is the prerequisite to the central limit theorem. So then, and here this part is the consequence of the central limit theorem, the distribution of the sample sums converges to a normal distribution. Notice the only thing we need from the data from paragraph 1 is that it has a mean, a variance, and is from a random sample. That tells us, paragraph 2, that the distribution of the sample sums converges to a normal distribution. So here's our first intra-lecture question. State the central limit theorem as I have stated it in this lecture. That question's pretty familiar to us. Again, write the question on the left-hand side, answer it on the left-hand side of your notes. Therefore, when you get to Moodle, you can write it in nice and easily. Here's a corollary of it. It's the distribution of the sample mean. So we're going to start with x being a random variable, mean mu finite variance sigma squared, draw a random sample size n from this distribution. In other words, that first paragraph, notice, is exactly the same as the first paragraph of the central limit theorem. Therefore, those tell us that we can now apply the central limit theorem. Consequence of this is the distribution of the sample mean is approximately normal. Here's some notation. X bar is the sample mean. Sub n, we're going to index it by n to indicate the sample size. This converges in distribution to a normal, expected value of mu, variance of 1 over n times the variance of the original data. Here's the proof. From the central limit theorem, we know this is true. We get this from that first paragraph. This first paragraph, same as in the central limit theorem, so this is the consequence of that first paragraph. Boom. Now we wonder about the distribution of x bar. Well, x bar sub n is just 1 over n times the sum of those xi's. Hey, look at this. The sum of the xi's, what distribution does that have? Normal. Boom. Expected value of the sum of the xi's is n mu. Expected value of 1 over n times the sum of the xi's is mu. The variance of the sum of the xi's is n sigma squared. The variance of 1 over n times those the sum of the xi's is 1 over n times sigma squared. Why are we dividing by n instead of having just sigma squared? Well, subproof 1, this is why the expected value of x bar is mu. I'll find the expected value of x bar sub n, substitute, pull out because expected value is a linear operation. Expected value of ax is a times the expected value of x. In this case, a is at 1 over n. We know the expected value of t is just n mu. The n's cancel. That was easy. Subproof 2 with the variances. If we want to find the variance of x bar sub n, substitute. It's 1 over n times t. Pull out that 1 over n. It's 1 over n squared. Why is it now squared? Look back to the lecture on section 7.1. It's because there's a square in the calculation of the variance of the random variable. Variance of t is just n sigma squared. That n and one of these cancel out, so we're left with 1 over n times sigma squared. And that brings us to the conclusion of the corollary. And this is exactly what we just showed. So let's have a couple intra-lecture questions. Question 2. How does the distribution of the sample mean depend on the distribution of the data? And might as well do question 3 now while we're at it. Since the speed of convergence depends on how closely the data are to normal, I got the L in there finally, I edited it. Which of these two will converge fastest, either the uniform or the exponential? Yep, question 1 and 3 are from the last slide deck. Question 2 is kind of is the most important part of this slide deck. So let's go back to some examples. Example 1. Let's say I draw a sample of size 14 from a population that has a mean of 126 and a variance of 42. What's the approximate distribution of the sample means? Notice I didn't tell you that x followed a normal distribution. I didn't tell you x followed a uniform distribution. I didn't tell you x followed an exponential distribution. It doesn't matter. I know x has a finite variance. Therefore, I can apply the central limit theorem. Whether or not n equals 14 is large enough for this approximation to be good, that's another question. All I want is an approximate distribution of the sample means. So this is a straightforward application of the main corollary from this section. Approximate distribution of the sample means x bar is approximately normally distributed with expected value mu of x bar being 126, the same as the expected value of the original distribution, and variance of being 1 over n times 42. 42 is the original variance, or I'm sorry, the variance of the original distribution. It's 1 over n times that sigma squared. 42 over 14 is 3, so x bar approximately normal, mean of 126, variance of 3. Example 2. I've been told that the average adult height for males in the United States has mean of 69 inches and standard deviation of 3. What's the probability of having the mean of a sample of size 2 being less than 65 inches? So in the last example, straightforward application, we didn't do anything with the distribution of x bar. Here we're going to do something with that x bar. We're going to ask what's the probability of observing an x bar being less than 65 inches. So we're asked ultimately, what is the probability of having the mean being less than 65? We're asked to calculate this. And if you want to do a sub 2 here, that would be fantastic. So we're asked to calculate the probability of x bar sub 2 being less than 65. That means we need to know the distribution of x bar sub 2. We're trying to solve a probability statement about x bar sub 2. We really need to know the distribution of x bar sub 2. So to calculate this, we're going to use the central limit theorem. X bar sub 2 is approximately normal, expected value the same as the original distribution, and variance equal to 1 over n times the original variance. Notice I told you the standard deviation was 3, therefore the variance is 9. So we know x bar sub 2, approximately normal, mean of 69, variance of 4.5. Now we use that to answer our original question about the probability of x bar being less than 65. Using R, this is P norm. Remember, it's got to be a less than part. 65 is from here. M is equal to 69. S, which for R needs to be the standard deviation. That's just the square root of the variance. The variance is 3 squared over 2. So this R code will get us 0.0297. In other words, there's about a 3% chance that I will observe an average being less than 65. Given that the mean of the population is 69 and the variance of the population is 9. In other words, this probability is small, and therefore my beliefs about the original population are unlikely. Thus, the probability of observing this event, given our assumptions are correct, is quite small. So either I did not observe this event, or my assumptions are not true. So example 1, straightforward application of the central limit theorem. Example 2, okay, now that we've got the distribution of x bar, let's see how we can use this. Okay, now my sample is size 10. Same mean and variance of the adult height for males. But now I'm doing a sample of size 10. I want to know what's the probability of that sample of size 10 being less than 65. Same statement, it's probability of x bar being less than 65, except in this case, n is now 10. So from the central limit theorem, x bar follows an approximately normal distribution with mean of 69 from the original distribution and variance of 1 over n times the original variance. And the original variance is 3 squared. So x bar now follows this distribution. Notice the expected value is the same, the variance is smaller. So as the sample size increases, the variance of x bar gets smaller. So again, I want to calculate probability of x bar being less than 65. This is P norm of 65. M is equal to 69. S, standard deviation, is just the square root of the variance of 0.9. This is 0.0000124. So again, very small probability. Meaning, if everything I said is true, then the probability of me observing this is small, incredibly small. It's 1 in 10 to the negative fifth. It's 1 in 10,000. Since the probability of me observing this is so small, I no longer really believe all of my assumptions. Maybe mu for the population isn't 69. Maybe the variance of the population isn't 9. Maybe the distribution of the population is so non-normal that the central limit theorem is not helping when n is equal to 10. But still, there is a 1 in 10,000 chance that my assumptions are correct and I observe this event. So it is possible. But it really brings into, really makes you doubt the assumptions. Fourth example, crime. The 2,000 violent crime rate for the 50 states plus DC are given in the data file crime. We need to find a 95% central confidence interval for the mean violent crime rate. This is not the first time you've seen the word confidence interval. That would be one of the labs. So here we're asked to calculate the 2.5th and the 97.5th percentiles of the sample means drawn from the 2,000 violent crime rate. Why is it the 2.5th and 97.5th? Note the difference is 95. And notice you got 2.5% below and 2.5% above. So that gives us the central part. So those two quantiles will give us the endpoints of that central 95% confidence interval. It's a confidence interval, so it's going to be an interval on the means. It's a confidence interval, so it's going to be an interval on the means. Probably want to put a star there, some googly eyes staring at it, and big expression of wow. One way of estimating this confidence interval is to apply the corollary to central limit theorem. From the data, we've got a mean of 441.55 and a standard deviation of 241.45. Thus, by the corollary to the central limit theorem, we have x bar is approximately normal, expected value of 441.55, and variance of 1 over n times the variance of the data itself. And so the endpoints for the 95% confidence interval are the 2.5th and 97.5th quantiles of that distribution, which in R we can do this way. Let's look at all the parts. That's a Q. Q norm is for the quantiles of a normal distribution. These are the 2% that you want, or the two proportions you want, the 2.5th percentile and the 97.5th percentile. Got to put them together in a C function, followed by a comma, followed by how you're defining this distribution, mean of 441.55, standard deviation of 241.45 divided by the square root of 51. I could have written this as a square root of 241.45 squared over 51, but the square root of a square, you're just pulling that 241.45 out front. So in other words, this is really just s over square root of n. So we're 95% confident that the actual mean is between 375 and 508. And that's violent crimes per 100,000. Confidence interval is on the mean. Review back what an observation interval is. That's on all the observations you've seen. Recall back what a prediction interval is. It's on all the observations you will see in the future. Confidence interval is about the means, the sample means. We could also, and this part is bootstrapping, we could also estimate the confidence interval from the data itself using a process that's called bootstrapping. Here's the code to do it, and this will give us a 95% confidence interval from 380 to 510. I'm going to go through the lines of this code very carefully shortly, but Notice that the confidence interval you get through bootstrapping is 380 to 510, but what we got from using a normal approximation was 375 to 508. In other words, not too different. Okay, so 5 lines, 6 lines. Here are the 2 key lines. They're inside the for loop, actually. This line is key, and this line is key. So let's look at the x equals line. We're drawing a sample from the violent crime rate in 2000. This is going to be a random sample. That's what the sample command does, draws it, and allows you, and it does replace equals true, which means it allows you to draw a state's violent crime rate more than once. If replace equals true isn't there, then this is just going to give you the same 51 values in a different order each time, but the same 51 values. And if it's the same 51 values, the mean of those values will be exactly the same each time. So we need the replace equals true to do bootstrapping. So this x equals line will draw a random sample from the violent crime rate in 2000, allowing for states to be chosen multiple times. Stores it in the variable x. Second line, second important line, we calculate the mean of that sample. We're going to store it in the variable called mn. Mn is for mean, but we're going to store it in this variable. Bracket I bracket, that is done to allow us to remember, or to allow R to remember each of those sample means. So x equals, that gives us the sample. This line gives us the sample mean of that sample, storing it in the variable mn in the ith position. And bracket I bracket will mean that this is stored in the ith position. We're going to do that 10,000 times. That's what the for loop does. First time through, I is equal to 1, because 1 colon 1e4 is 1, 2, 3, 4, all the way up to 10,000. First time through, I is equal to 1, draws a sample, calculates the mean of that sample, stores it in the variable mn in the first position. Closing brace goes back up here. I is now equal to 2. Draws another sample, calculates the mean of that, stores it in the variable mn in position 2. Closing brace goes back up here. I is now equal to 3. Draws a random sample, calculates the mean, stores it in position 3. This is continued 10,000 times. So at the end of this loop, at the end of these 4 lines, the variable mn will contain 10,000 values. Each of those 10,000 values will be a sample mean from this distribution. The bottom line gives us the endpoints of that 95% confidence interval. Remember, this is sample means, so an interval on sample means will be the confidence interval. Quantile function, you give it the vector first, and then you specify the percentiles you want. So we've explained every single line there except the first. In R, when you're building a vector, such as the way that we're doing it here, you need to tell R to set aside memory for that vector. This line tells R, hey, we're going to create the vector mn. It's going to be a numeric vector. It's going to hold numbers. And you just need to set aside memory so that we can build it. And then this loop will build it. And then at the end, we're going to use that mn. I strongly suggest at this point, you type this in, you run it, and you see that it actually does work. Your confidence interval will be slightly different. Why will your confidence interval be slightly different, or why could it be slightly different? Because this is a random sample. We're drawing a random sample, so your random sample will be different from my random sample. The fact that we're doing this 10,000 times means that the interval endpoints are probably going to be really, really close. If we want to make them even closer, we do this a million times, 1e6. So here's the question, why is there a difference between the 2 confidence intervals? Doing it bootstrap, it's 380 to 510. Doing it using the normal approximation, it's 375 to 508. The reason it's different is here we're assuming that the sample means follow a normal distribution. And here we're not making that assumption. Here we're saying, okay, data, I don't care what distribution you have. I don't care what the distribution of the sample means actually is. I want to have a good estimate for that confidence interval. Since the endpoints are so close to each other, that tells me that this normal approximation is not a bad approximation when the sample size is 51. If the sample size were 5,000, I would expect this interval to be the same as this interval. If the sample size were 5, I would not be surprised if this interval and this interval were very different. Did I give you all of them? I did give you all of them. Okay. So, learning check. What's the main consequence of the central limit theorem? Again, hit pause, come up with an answer, and then I'll give you the answer. The distribution of the sample means is approximately normal. What is the sampling distribution for the mean? Sampling distribution for the mean is normal with expected value of mu and variance of sigma squared over n. How does the sampling distribution for the mean depend on the distribution of the data? If the data are normal, then the sampling distribution for the mean is exactly normal. If it is not normal, then the farther the data distribution from normal is, the larger the sample size needs to be for this to be a good approximation. What is bootstrapping and what is its greatest use? Bootstrapping is using the data under repeated sampling to estimate a population parameter. And I would argue its greatest use is to estimate the confidence interval for the mean. Section 7.2 in Hawks, Appendix C3, and of course central limit theorem. You may want to also look at Wikipedia bootstrapping if you've got questions on bootstrapping. And that's it. See you in section 7.3. Hello and welcome to the last section of Chapter 7. Chapter 7 covers the central limit theorem in two of its most important applications. Section 7.1, you were introduced to the central limit theorem. 7.2, you saw its application to sample means. In this section, you're going to see its application to sample proportions. So by the end of this lecture, you should be able to state the central limit theorem, apply the central limit theorem to the problem of the sampling distribution of the proportion, estimate the sampling distribution for the proportion, and understand the relationship between the sample size and the precision of the estimate. We've been hinting at that there is a strong relationship between sample size and precision for a long time. Here we're going to actually see it in the form or in the guise of something we call power. Here's the arc. In recent computer activities, the SCAs, we've examined random draws, calculating sample means from subsets, histograms from those, and we've seen that those histograms illustrate that the sample means look pretty normal. And then we looked at the central limit theorem and saw, oh, that makes sense because the central limit theorem says sample means are going to tend to be normal, especially if the sample size is large. In the last slide deck, we also saw this application to the sample mean, so boom. Today we're going to examine the central limit theorem in terms of what it tells us about the distribution of the sample proportion, aka the sampling distribution of the proportion. So last time it was the mean, this time it's the proportion. So here's the central limit theorem again. Again, the first paragraph is the premise. These are things that must be met before you can apply the central limit theorem. Notice that the premises speak about the distribution of the data. The consequence of the central limit theorem, the second paragraph, talks about the distribution of the sample totals. So let x be a random variable with mean mu, finite variance sigma squared. Let us draw a random sample, in other words, all the x's are independent, of size n from this distribution. Notice we didn't specify that the data have to be normal or exponential or uniform or gamma or beta or whatever. We just said it has to have a mean and finite variance, and the data have to be random draw from this distribution. Consequence, then the distribution the sample sums converges to a normal distribution. Specifically, t, which is the sum of the xi's, converges in distribution to a normal with expected value n mu and variance n sigma squared. Which brings us to our first intra-lecture question. State the central limit theorem as I have stated it in this lecture. So again, write this over on the left-hand side, answer it below. This is really important because a lot of students in the past have thought the central limit theorem says the data become more normal. That's not true. The central limit theorem doesn't tell us anything about the distribution of the data. It requires that the data has a finite variance and a mean, but it doesn't say, therefore, the distribution of the data becomes more normal. No, it says the distribution of the sums becomes more normal. There we are. So there's the theorem statement. Here's the corollary for the sample proportion. We saw one of these with the sample mean. We're going to see it for the sample proportion. Let x follow a binomial distribution with parameter values n and p. Remember, n is a sample size and p is the probability of success on each of the trials. Let the x be a random sample from n Bernoulli random variables. There, notice again, remember back to 7.1, I framed the binomial as being just the sum of independent Bernoullis. We're using that here. Then the distribution of the sample proportion, which I'm going to call big P, which is defined as 1 over n times x, the number of successes from that binomial, or the number of successes from those n Bernoullis. So this is 1 over n times x. I've seen 1 over n times x before. I forget what that was. Converges in distribution to a normal with expected value little p. And variance of p times 1 minus p over n. So here we are for intra-lecture question number 2. If I can find it. What is the distribution of the sample proportion? This is an important one. Also, while you're here, look at how this distribution compares to the distribution of the sample mean. Going back. So here's the proof. From the central limit theorem, we know x follows an approximate normal distribution, expected value np, variance np 1 minus p. That's straight out application of the central limit theorem. Np is the expected value of x, np 1 minus p is the variance of x. Remember, we want to find the distribution or the approximate distribution of p, the sample proportions. So expected value of p, which is expected value of x over n. Pulling out that 1 over n, because expectation is a linear operator, we get expected value of x over n. We know the expected value of x from a previous slide is just np. The n's cancel out, and we're left with p. So the expected value of p is little p. So the expected value of your sample proportions is your population proportion. Normal distribution has an expected value and a variance, so let's calculate the variance of your sample proportions. Again, first step, substitution. We're going to factor out that n as an n squared. Check back to section 7.1 why we were factoring out an n squared. It has to do with the fact that the variance, you square the random variable. Variance of x is np 1 minus p. This n and one of these cancels out. P times 1 minus p over n. Therefore, sample proportions are approximately normally distributed. Expected value of p, variance of p times 1 minus p over n. Notice the expected value of p is little p. Since the expected value of p is little p, This is an unbiased estimator. And notice that as the sample size increases, the variance also, sample size increases, the variance decreases. In other words, as n increases, the precision will increase as well. The variance decreases, precision increases. So there's our result. Some examples. According to the U.S. Census, 18% of Americans are below the poverty line. If I randomly sample 10 people from the United States, what's the probability that more than 20 of them are below the poverty line? So notice I'm asking a probability question. It's what is the probability that more than 20% are below the poverty line? So I'm asked probability of p being greater than 0.20. Since we're doing trying to calculate a probability about the random variable p, we need to know the distribution of p. From the corollary to the central limit theorem that we covered today, p is approximately normal. Expected value of 0.18, because that's p in the population. And variance of p times 1 minus p over n. So big P is approximately normal, mean of 0.18, variance of 0.01476. I need to calculate the probability that P is greater than 0.2. Remember, in order to use cumulative probabilities, this has to be a less than. Complements rule from chapter 4 says probability of P being greater than something is 1 minus the probability of P being less than or equal to it. We've got a less than or equal here, so we can use the P norm, 0.2, 0.18, and this is standard deviation, so it's the square root of the variance. That gives us a probability of 0.4346. That's not small, not at all, so it wouldn't shock me if more than 20% of my sample is below the poverty line. Assuming that the population population proportion is 0.18, then the probability of me observing more than 20% being under the poverty line is 0.43 doesn't give me any evidence against my assumption of the 0.18. It's a coin flip, essentially. About half the time I'll be above 20%, about half the time I'll be below. Same assumption, the population proportion is 18%. I'm now going to sample 100 people instead of what I did in the previous example, increasing the sample size. And I want to calculate the same probability that more than 20% are below the poverty line. So again, we're asked to calculate the probability that p is greater than 0.2. We need to know the distribution of p. From the central limit theorem, it's 18%. 18% times 1 minus 18% over n. N here is 100. This gives us that distribution. I need to calculate the probability of p being greater than 0.2. It's 1 minus probability of p being less than or equal to 0.2. And I get a probability of 0.3. So also not a small value. It's about a third of the time I'll get a sample proportion being greater than 20%. If our assumption about the population is true, that is, if the population poverty rate indeed is 0.18. Notice the probability did go down, though. In the previous example, when n was 10, this was 0.46 or 0.47. It's gone down. It's 0.30, which makes sense because I collect more and more data. I would expect my observations to average out to being closer to the real average. Now my sample size is 1,000. I'm going to ask 1,000 people. The first it was 10, then 100, now 1,000. We're going to look at a 95% confidence interval for the sample proportion. Confidence interval is on those sample statistics, not on observations that we've seen, which is an observation interval, not on observations we're going to see in the future, which would be a prediction interval, but on the sample statistic, in this case, sample proportion. So with 1,000, I would expect to see 95% of the time somewhere between 0.156 and 0.204. So if reality is correct, I'm sorry, if my assumption about reality, 18% is correct, and I collect a sample size of 1,000, I expect 95% of the time the sample proportion is going to be between 15 and 20%. How to get that? I've got the proportion is normally distributed, so I'll use the norm stem. I'm looking at the quantiles, so I'll use Q norm. I'm doing the 2.5th percentile, the 97.5th percentile, and the rest just specifies that particular normal distribution. Now I'm going to ask 100,000 Americans. And I want to know the probability that more than 20% of them are below the poverty line. So I did 10, 100,000, now 100,000. And my confidence interval is 17.8 to 18.2. So I would expect 95% of the time my sample of 100,000 to be between 17.8 and 18.2. Got the 2 and the 8 switched. Between 17.2 and 18.8. So if I fell out of the interval of 17.2 to 18.8, I'd say, well, there's something wrong with my assumption of 18%. Here's a graph of the probability that the observed sample proportion is greater than 0.2 as graphed against the sample size. Our first example was 10, n equals 10. Our probability of observing it was way up here at about 0.46, I think. The second n was 100, and the probability we got was about 0.30. So as the sample size increases, the probability of observing a extreme event decreases. It doesn't go away. I mean, here we are with n equal to 1,000. We've still got a probability of about 0.08. So about 8% of the time, that sample of 1,000 will give me a sample proportion greater than 0.2. We can also look at this in terms of confidence intervals. As the sample size increases, the upper confidence bound and the lower confidence bound get closer and closer together. They never become the same. I mean, even out here at n equal to 1,000, there's still a sizable gap between the two. So this is where power comes in. Power is the ability to distinguish between a true and a false null hypothesis. In other words, we are assuming that the we're assuming that the population proportion is 0.18. Power is the ability to say, no, it's not, given our observations. So if we observe p being greater than 0.2, the probability of us saying, no, that 0.18 is wrong, gets bigger and bigger as the sample size increases. In terms of confidence intervals, remember the width of the confidence interval is the precision. The smaller the width, the higher the precision. As the sample size increases, our precision increases. Most of the benefit happens in the first couple hundred. What this means is, as the sample size increases, we're going to observe sample proportions closer and closer to our population proportion. You'll still get some above and some below, but they'll be much more concentrated around the sample proportion. Which brings us to intra-lecture question number 3. What is power? When we get to chapter 10, we'll have a much better understanding of power, but you got to dip your toes in here. So, learning check. What's the main consequence for the central limit theorem? The main consequence for the central limit theorem is that the sample means and sample proportions are much more normally distributed than the data itself. What is the sampling distribution for the proportion? The sampling distribution proportion, capital P, is approximately normal with expected value of little p and variance of p times 1 minus p over n. What effect does sample size have for precision in estimating the sample proportion? As the sample size increases, the precision increases as well. That was section 3. You may also want to glance through Appendix C3 and central limit theorem. You may also want to look at power in statistics on Wikipedia. And that's it for Chapter 7. In Chapter 8, we're going to use all of this central limit theorem stuff to start creating confidence intervals. And in Chapter 10, we're going to look at hypothesis testing. But in all reality, we understand what confidence intervals are at this point. But when we get to Chapter 8, we're going to get a much deeper appreciation for confidence intervals. And that's it. Hello and welcome to the video lecture on Chapter 8, where we introduce the theory of confidence intervals and how to calculate them by hand, which we should never want to do because calculating things by hand introduces errors in many, many places. It's much better to learn how to do these with a computer, which will be the next lecture, learning how to do confidence intervals on a computer, specifically using the R statistical environment. So I guess we get to start. By the end of this lecture, you should be able to state what a confidence interval concerns, what it is, state the theory behind calculating those confidence intervals, and understand that they represent a proportion, not a probability, but a proportion. So here's the entire arc of the course, or the story of the course thus far. The second examination would have taken place last week if we had a typical course. So before that, back when we were talking about probabilities, we calculated 3 types of intervals. We calculated the observation intervals, the confidence intervals, and the prediction intervals. And these 3 were actually intervals about different things. Even though it's all based on the data, they all were intervals about different things. The observation interval is intervals on observations that we have already had. Prediction interval is on observations that we will have in the future. So a 95% prediction interval tells us that 95% in the future we will be within this range. Whereas a 95% observation interval tells us that of everything that we've observed so far, 95% of those observations are in this range. Now contrast both of those with the confidence interval. Recall that the confidence interval was about the about the sample statistic. So we had confidence intervals looking at the sample mean, or confidence intervals looking at the sample proportion, or confidence intervals looking at the sample variance. And Chapter 8 onward, we're going to be using these confidence intervals in a much more mathematically balanced way. I'm laying out the theory today. We also examined the central limit theorem, and we looked at the normal distribution a lot. And when we talked about the central limit theorem, I said this tells us, this theorem is so important that it tells us that we can just focus on the normal distribution for a good first approximation anytime in the future. So that's why the normal distribution is so important. It's also why the central limit theorem is so important. And we're going to use both of those today to create this mathematical confidence interval. So today we'll look at confidence intervals that deal with population parameters. The confidence intervals we've dealt with in the past have looked at the sample statistics. Now we're going to do it for the population parameters. And remember, the goal of inferential statistics is to take our sample and draw conclusions about the population parameter. So now we're going to take our sample, and from that sample we're going to calculate a confidence interval, and that confidence interval is going to tell us about reasonable values for this population parameter. So let's start with the definition. A confidence interval is a set of values that theoretically contain the population parameter given proportion to the time when the experiment is performed many times. So it's a set of values. Usually it's an interval, so we have a lower bound and an upper bound, and we assume every value between those two, lower and the upper, constitute the interval. It contains the population parameter that we're interested in, a given proportion of the time. So if we're talking about like a 95% confidence interval, then theoretically the population parameter is in about 95% of those confidence intervals when we do this experiment over and over and over. When we do it for just once, then we just have to hope that the population parameter is in the interval. And be confident at a certain level that it is in the interval. And this is why it's important to replicate experiments over and over again. Because one confidence interval could be based on biased data, or data that's not representative of the population. And even we could use the best sampling method on the world, and we would get a set of data, a sample of that data that's not representative of the population. We'd never know that if all we do is do this once. And that's why replication is so important, so that we know that whether or not our first sample was representative or not. Because if it's unlikely that the sample is unrepresentative, then it's going to be doubly so if you have two samples and that they're both unrepresentative. So note that it gives information about the population parameter. It's a set of reasonable values for that parameter. Some population parameters we'll be looking at will be the mean, the variance, the proportion. It's a set of reasonable values. It's a function of the data. You collect data, and from that data you calculate the endpoints of that confidence interval. Since it's a function of the data, it's a random variable. And it is a result of a probability distribution calculation, and we'll see that later. So if LCL and UCL, LCL for lower confidence limit, and UCL be upper confidence limit, it was a 1 minus alpha times 100% confidence interval for parameter theta, and theta could be mu or sigma squared or p. And then about 1 minus alpha times 100% of the intervals under repeated experiments will contain that parameter. By default, we'll use alpha of 0.05, which means that we'll be talking about 95% confidence intervals, just by default. Which I say here, the confidence level C is 1 minus our alpha. By default, we're going to use alpha of 0.05 in this course. And the value of alpha will be reintroduced in Chapter 10 when we talk about hypothesis testing. It's going to be the theoretical or the nominal type 1 error rate. And those words will make sense when we get to Chapter 10 when we start talking about hypothesis testing. Note that alpha is selected by the researcher, therefore the confidence level is selected by the researcher. So unless it's stated otherwise, we're going to have alpha of 0.05 in this course. So let's get to our first intra-lecture question. That intra-lecture question will be, define the confidence interval. And again, I suggest writing down the question on the left-hand side of your notebook. Answer it below that. And this is especially important because understanding what a confidence interval is extremely important for understanding what you can learn from your data. Okay, so that's where we were. Let's move on to something called bootstrapping. In a previous class, we introduced bootstrapping. It's in SCA 5B, I believe, and obtaining a confidence interval for a population parameter. So let's look at the code again. This is how you would load in data from this path. It's geography.csv. These are the results of a previous class taking a geography quiz. 6 is the highest possible score on the quiz, 0 is the lowest. Load it in, attach the data set. If you want to, you can do summary of DT to see what the mean and the median are, see what the min and the max are, see what the first and the third quartile are. You could also calculate the standard deviation doing SD. You can do the IQR, interquartile range, using the IQR function. Then we performed these two lines multiple times. The first line draws a random sample from the variable score. That's the score that the students made on the quiz with replacement. So each time through, X is going to be a vector of scores. The second line, you find the mean of that, so this will calculate the sample mean of that particular sample of scores and store it into the variable st at the ith position. This is a for loop, so it will be doing these two lines, or everything between the two braces, 1 times 10 to the 4th times. So at the end of running this loop, you're going to have 10,000 sample means. Doing a histogram of those will show you the distribution of those sample means. And doing the quantiles from these two points, or these two levels, will give you the endpoints of a 95% confidence interval for the mean. And we've done this in the past. Here's what the histogram looks like. Notice the histogram looks rather normal. Considering that the actual data look nothing like a normal distribution, the distribution of the sample means definitely does look normal. That does not surprise us, or it should not surprise us, if we actually understand the central limit theorem, because what does the central limit theorem tell us? Sample means will be much more normally distributed than the data itself. And these are the endpoints of the 95% confidence interval. So we're 95% confident that the population mean mu is between 1.63 and 2.57. 1.633333 and 2.56667. Again, these are out of 6. So the mean is definitely going to be less than 50%. Because 50% is 3, and that's way, way over here. And just about all of the histogram is to the left of 3. So we're almost positive that the mean understanding of geography is less than 50%. This is fine if all we have is the data, and that's all we did here. We just looked at the data, we drew from the data, we dealt with the data as being representative of the population. We didn't say the data was normally distributed. We didn't say the data followed a binomial distribution. We just said, here's the data. If we can make an additional assumption about the data, specifically that the data are normally distributed, then we can go a little bit further. We don't have to do bootstrapping. We can just run a simple test. So recall that for large n from the central limit theorem, x bar is approximately normal with mean mu and variance sigma squared over n, where sigma squared is the variance of the data, or variance of the data generating process, and mu is the expected value of the data generating process. So this should look familiar from Chapter 7, Section 2. Now if we apply the z-transform from back in Chapter 3, we're going to subtract off mu from both sides, and we're going to divide by the square root of sigma squared over n. We're going to get that x bar minus mu over root sigma squared over n is approximately normal 0, 1. This is why it's called the z-score. This distribution, normal 0, 1, is also called the z distribution. This is normalizing the x-bar distribution. So we have x-bar minus mu over square root of sigma squared over n is approximately normal, approximately standard normal. That means the expression on the left is between the values of negative 1.96 and positive 1.96 about 95% of the time. How do I know that? Because the 2.5th percentile and the 97.5th percentile of the standard normal are negative 1.96 and positive 1.96. How do we know that? Q norm of 0.025 will give us the negative 1.96, and Q norm of 0.975 will give us the 1.96. And so we would say that a theoretical 95% confidence interval, a theoretical 95% interval for this quantity, this thing on the left, x bar minus mu over square root of sigma squared over n, is between negative 1.96 and 1.96 by definition. So this bottom statement would be a definitional statement. That is, if I have x that's normally distributed with mean mu and variance sigma squared, and I draw a sample of size n from the x distribution and calculate this, there's a 95% probability that it's going to be between negative 1.96 and positive 1.96. Because 95% of the time, it's between, this quantity is between negative 1.96 and positive 1.96. About 2.5% of the time, it's above 1.96, and about 2.5% of the time, it's less than negative 1.96. Now, we really don't care about the interval for this quantity. We want it for mu. We want a confidence interval for mu. Well, all we have to do is solve this equation, this equaling negative 1.96, for mu. And here's what we get. Here's the quantity equal to negative 1.96. We're solving for mu, remember. So we multiply both sides by the square root of sigma squared over n. And this is kind of important. This quantity, square root of sigma squared over n, is called the standard error. Now we got x bar minus mu is equal to negative 1.96 times the standard error. We subtract an x bar from both sides. Remember, we're solving for this mu. So we're subtracting x bar from both sides. We're left with the negative mu on the right. Multiply through by negative 1. We get that this is the upper bound for mu. So this we're going to call the upper bound on the 95% confidence interval for mu. I leave it as an exercise to show that this with a negative sign here is going to be the lower bound. How would you do that? This quantity equal to 1.96 and solve for mu. So we got it x bar minus 1.96 times the standard error and x bar plus 1.96 times the standard error are the two endpoints. We can symbolize it in just one expression, x bar plus and minus z of alpha over 2 times the standard error. If alpha is 0.05, then this will be a 1.96 out front. So we would call this, oddly enough, we would call this the confidence interval for mu. Technically, this would just provide the two endpoints of the confidence interval for mu. I'm going to go to the next intra-lecture question at this point. Oops. What is the distribution of the sample mean in this lecture? So what did we require the distribution of the sample mean to be? Notice, not the distribution of the sample. We're looking at the distribution of the sample mean. So what was that in this lecture? And again, write the question on the left side, your answer below it. Okay, so this confidence interval that we just calculated is for mu, and it works, this confidence interval is for mu, and it works when you're estimating mu, which makes sense. If you're trying to estimate the variance, you wouldn't use a confidence interval for mu. If you're able to calculate x bar and n, well, if you can't calculate x bar and n from the data, then I don't know what to say. This goes back, calculating x bar from the data is pretty straightforward, and as you're just counting the data size. And if you know sigma squared, remember sigma squared is the population variance. I don't know that we would ever know the population variance. And then last but not least, the data are generated from a normal process, or n is large enough so that the central limit theorem says that x bar is approximately normal. And again, the reality here for 4 is we just need x bar to be approximately normal. At no point in the last few slides did I say x has to follow any specific distribution. Every distributional statement we made was that x bar was normal, or approximately so. Going back to number 3, you have to know sigma squared, the population variance. Recall the definition of the population variance. In order to calculate it, you need to know what mu is. However, since we're trying to estimate mu, we don't know what mu is. Therefore, how do we know what sigma squared is? And in general, if we don't know sigma squared, then what we just did doesn't work. So your question to me is, why did we do it if we never know sigma squared, and therefore what we just did doesn't do anything for us? And the answer is, this process that we just did gave us an opportunity to show how confidence intervals are constructed, what they actually indicate, and how they can be useful. Kind of shaky on that last one. But now that we know the process in creating confidence intervals, we can fix this, quote, error, or try to figure out some way that we can get by without having to know sigma squared, and create a confidence interval from that, using the same theory behind it. And specifically, since we can't use the Z procedure, which we just did, it's also called the Wald, W-A-L-D, named after, I think it was Benjamin Wald. Could have been Abraham Wald. I probably should have looked that up. We're going to use a different procedure. If we know sigma squared, we can use this procedure we just did. If we don't know sigma squared, we can't, because we need to know sigma squared to do this procedure. Instead of the Z procedure, we'll use the T procedure. Here's the function that we will calculate. It's x bar minus mu. Numerator is the same as it was for the Z procedure. Denominator, we're looking at s squared over n. In the Z procedure, that was sigma squared. Here it's s squared. S squared would be the sample variance. And if we've got the sample, we can calculate s squared. And this quantity follows approximately a t distribution. T distribution has a parameter called the degrees of freedom. For one sample cases, the degrees of freedom is just equal to n minus 1. Now, with this said, we can go through the same procedure we did before with the z's to come up with the endpoints of a confidence interval using the t. It's x bar plus or minus this distributional multiplier times the standard error. Just in this case, the standard error is the square root of s squared over n. Compare this confidence interval to the one we calculated just earlier. So here, capital T sub alpha over 2 is the alpha over second quantile over the t distribution with n minus 1 degrees of freedom. Table 2, by tradition, table 2 is the t distribution table. So in the back of the book, there's probably a table 2 that you would use if you had to. This slide compares with the z distribution, the standard normal distribution, the blue distribution, how it compares to the t distribution. Notice the t distribution is much wider than the standard normal. There's more measurements out here in the tails, far away from 0. In other words, the t-distribution is much more variable than the z. Why does that make sense? It's because when we were using the z-distribution, we only had one source of uncertainty. That was in the x-bar. The denominator was a sigma squared, a population variance. With the t, we've got more sources of uncertainty. We've got the x-bar, but we've also got a s squared. That's a random variable also. So we've got 2 sources of randomness. So we would expect the t-distribution to be much wider than the z. Now this confidence interval for mu works if you're trying to estimate mu. If you're able to calculate x bar and n and s squared, which again, those are from the data, so you should be able to calculate them. And if the data are generated from a normal process, or if n is large enough. Again, we're doing this for x bar has to be normally distributed. And that happens in 2 ways. If the x's are normally distributed, or if n is large enough and the central limit theorem works. Let's do question 3. Why do we use a t-distribution when the population variance is unknown? So that should be 2 or 3 sentences, or maybe 1 or 2 sentences. Again, write the question on the left-hand side, answer it below. So we've got our procedure to estimate mu. Okay, with just one mu. As we go through this section, these 2 chapters, 8 and 9, we're going to get more and more procedures to estimate things. We're going to get a procedure to estimate p. We're going to get a procedure to estimate sigma squared. We're going to get a procedure to estimate 2 mu's, or the difference in 2 mu's. The difference in 2 proportions, the ratio of 2 variances. We're going to get procedures that work when the sample is not normal enough. So make sure that you can match what you're trying to estimate, the parameter, with the correct procedure and the requirements for that procedure. If we go back one, these are the requirements for the t-distribution. Or I'm sorry, these are the requirements for the t-test, for the t procedure. If you don't meet these, then you've got to use something else. Here's a list of several others. Go to the allprocedures.pdf handout that's located online. That will give you all the procedures we'll be looking at. We're going to be able to even have a procedure for mu tilde, the population median. So in today's slide deck, we covered the central limit theorem again. We looked at the definition of confidence intervals. We looked for confidence intervals for mu when sigma squared is known, for mu when sigma squared wasn't known. In both of those cases, x bar had to be approximately normal. We looked at confidence intervals for other instances, or I just mentioned them. And most importantly, the idea or the theory behind confidence intervals. This is the key for today. Understand what confidence intervals tell us. Once you understand this, then you can just hop on the computer and have the computer calculate those confidence intervals for you. It's the theory that you need to understand. In the next slide deck, we're going to show how to do these confidence interval calculations in R. Tomorrow we're going to review a little bit of today. We're going to look at some processes to create confidence intervals for 1 and 2 means, medians, proportions, variances. But we're going to do it in R, so instead of having to actually do those calculations by hand, it's going to be 1 line of code and interpret the results. So in the future, we're going to see a lot of these procedures. Make sure you keep a separate sheet. I would have it in the back of your notebook. And for every procedure, you should state how to do it in R, what the procedure is for. Is it for a single mean? Is it for 2 proportions? Is it a ratio of variances, etc.? What the requirements are, otherwise known as the assumptions of it, and then how to interpret. So chapter 8 and 5, and then Wikipedia. All of those will be helpful. Hope this was helpful. I'll see you in the next lecture. Hello and welcome to Section 10.4. Chapter 10 is all about hypothesis testing. Section 10.4 is about handling proportions, one sample and two sample proportions. So by the end of this lecture, you should be able to understand the theory behind and test hypotheses about a single population proportion and the difference between two population proportions. You should also better understand what the p-value means and how to test hypotheses, and clearly specify why confidence intervals and p-values both give important information about the population parameter. So, one parameter procedures. This will be about population proportion, P. The parametric procedure is the binomial procedure. The usual graphic is the binomial plot. That seems to be a lot like what we did back with confidence intervals and one parameter, one population proportion. Requires the data being generated from the binomial distribution. That really sounds familiar. The R function is binom.tests, x comma n. X is the number of successes, n is the number of trials. I guarantee we've seen this somewhere before, haven't we? Note that this is not the procedure that Hawks covers. They use something called the Wald test, wald.test. It also takes x comma n. So that should help you with the Hawks assignments. Here's the tests theory. We've actually covered this back when we introduced hypothesis testing. It was a whole bunch of binomial stuff. Well, this is what led to the binomial test. We're trying to draw conclusions about a single population proportion. We should use a test statistic based on the sample proportion or on what we observe, the number of successes. If we do it based on the sample proportion, we'll use the Wald test. If we do it on the number of successes, we'll use the binomial test. Again, the binomial test is the exact test, and the Wald test is the approximate test. We're given x follows a binomial distribution. Recall that the binomial has two parameters, n and p. The number of observations serves as a particularly fine test statistic because we know its distribution exactly. It's binomial. We only know the distribution of the proportions approximately. X divided by n is only approximately normal, and that only comes about because of the central limit theorem. If we go all the way back to section 6.5, approximating the binomial with the normal, we see, oh, there's a lot of error that can pop in there because it is an approximation. And the smaller the sample size, the more the error. The following are three examples showing how to perform these calculations. I have a coin that I think is fair. To test this, I flip it 10 times and count the number of heads in those 10 flips. A total of 3 heads actually came up. Is this sufficient evidence that the coin is not fair? So the claim is p is equal to 1/2. That's the research hypothesis. Since it contains the equal sign, this is also the null hypothesis. Since the equals is the null, the alternative will be not equal. We're trying to make a conclusion about p where the data are generated from a binomial. Thus, under the null hypothesis, x follows a binomial, n of 10, p of 0.5. We observed x equals 3. P-value is defined as the probability of observing data this extreme or more so, given that the null hypothesis is true. In other words, the p-value is the probability of x being less than or equal to 3, plus x greater than or probability of x greater than or equal to 7. Data at this extreme would be x equal 3. The or more so is less than 3. Where'd the 7 come from? Well, expected value of x, which is n times p, is 5. 3 is 2 less than 5. Just as extreme would be 2 more than 5. And more extreme than that would be greater than 2 plus 5. There's the distribution of x. distribution of the number of heads. We observed 3. That's the red thing. 7 is equally extreme. Less than or equal to 3 is or more so on the left, and greater than or equal to 7 is or more so on the right. So the red heights added up will give us our p-value. So the p-value is 0.34375, simply using calculations that we did back in Chapter 5, Section 2. And in fact, we did these calculations back in Chapter 5, Section 2, and we interpreted it correctly as evidence in favor of or against the claim. We're just giving it some more terminology and some more meaning. From the All Procedures handout and the SCA examples that we've looked at, we know we can also do binom.test, x equals 3, n equals 10, and p equals 0.050. Line tells us that the p-value is 0.3438. Since this is greater than alpha, we fail to reject the null hypothesis. The coin may be fair, the coin may not be fair. We have no evidence that can tell us either way. A 95% confidence interval for the probability of a flip landing head is between 6.7% and 65.2%. That is an extremely wide confidence interval. How possibly could we make it narrower? Right. Collect more data. Instead of flipping the coin 10 times, flip the coin 100 times, 1,000 times, 10,000 times. The larger the sample size, the narrower the confidence interval. Example 2. This goes back to a lab that we did. I contend that more than a quarter of students at Knox are juniors. To test this, I randomly sampled from the student body asking class year. In my sample of 100 students, 30 stated they were juniors. Here the claim is p is greater than 0.25, because I contend that more than a quarter, so it's more than. Since it contains the greater than sign, this will be the alternative. The null will be the opposite of greater than, which is not greater than, otherwise known as less than or equal to. That means the two statistical hypotheses are given below. Here's the distribution of the number of juniors under the null hypothesis. Remember, the null hypothesis contains the equals part of a quarter. I asked 100 people, so this will be the distribution of the number of juniors that I experience. P-value will be the probability. Oh, remember I got 30 of them. So this is what I observed right here. Since the alternative was greater than, the p-value is going to be the probability of x being greater than or equal to 30. The equal to is as extreme, and the greater than is the or more so. We get 0.1495. Because the p-value is greater than alpha, we fail to reject the null hypothesis. We do not have sufficient evidence that the proportion of juniors is greater than a quarter. In fact, we can calculate the confidence interval directly and find that the proportion of juniors is greater than 0.2249 based on this data. Or we can use the binomial test. X is 30, because that's what we observed, the number of successes. N is 100, that's the sample size. P is 0.25, that's my value of interest, that's my theta naught. The alternative is greater because I claim that I claim that P is greater than 0.25. We get a p-value of 0.1495. We get the confidence interval from 0.23 up. So I'm 95% that the proportion of juniors is at least 0.2249232. One thing that we can definitely use this binomial test for is to check if a data set is representative on its face. The data file is some college. This is real data. I had to change the name of the college to protect the innocent. It was sent to me by the registrar of some college to do some statistical analysis. I did a little check, sent it right back and said the data are not representative. She said, yes it is. I said, okay, I'll go ahead and do the analysis and it'll be worthless, but I will tell you it's worthless. She kind of got upset with me. I was supposed to model the success, the high enough GPA given some of the other variables. Let's perform a quick check to see if the data are reasonably representative of the population at that college. So my provided sample consisted of 661 students. She claimed a random sample from the college, of which 22 were freshmen. Given that the proportion of freshmen at SCU, some college university, is 28%, are the data representative in terms of freshmen? So here the claim is p is equal to 0.280. Since it contains equal sign, it's the null. That means that the two hypotheses are equal and then not equal for the alternative. Under the null hypothesis, the number of freshmen in my sample should follow this binomial distribution, n of 661, p of 0.28. Remember, I observed 22. So I observed something down here. Something just as extreme is going to be located way up here. Or we can simply just double the probability of x being less than or equal to 22. Probability of x being less than or equal to 22 is 0. I'll go ahead and double that. 2 times 0 is 0. We could also add 0 to that. We could multiply by 1 if we want to stretch this out, but it comes down, the p-value is 0. Since the p-value is less than our alpha of 0.05, we reject the null hypothesis in favor of the alternative. In terms of freshmen, the sample is not representative of the population of SCU. Since I'm trying to model the GPA, it is very reasonable that freshman GPA will be different from sophomores, juniors, and seniors. Therefore, in order for my analysis to be worth the weight that its weight in gold, I really do need more freshmen in my sample. Or we can just use the power of R, binom.tests, x is 22, number of successes, n is 661, p is 0.28. I got the 0.28 from their website. Got a p-value of being less than 2.2 times 10 to the negative 16th. This data would be representative if the proportion of freshmen at SCU is between 2% and 5%. Now that I talk about this, I realize I never did get paid for this, so yeah, it's okay. I didn't do anything other than say that they didn't give me the data. Next types of tests, the two-parameter procedures. We're going to compare P1 minus P2, or we're going to compare P1 and P2. The parameter of interest will be P1 minus P2. This will be the proportions procedure, or the two proportions procedure. The graphic will be the binomial plot. It requires that the expected number of successes is at least 5 in each group. Some would say at least 10 in each group. If no one's dying from you being wrong, then at least 10 should be fine. If you really do need to make sure that you're right, then at least 50 or at least 100 in each group would be preferred. The proportions test is based on the normality approximation to the binomial distribution. Therefore, a large sample size is required. The R function is pardon me, is prop.test. You give it the number of successes, x, and the number of trials, n. Since it's two proportions we're comparing, you got to give it two sets of x's, or two x's, and two n's wrapped in c's. They use something close to this, but this procedure actually makes adjustments for the fact that the binomial distribution is discrete and the normal is not. As such, you'll need to use the Wald test to perform Hawk's homework estimating P1 minus P2. So again, when you're using proportion stuff with Hawk's, use the Wald test. The Wald test will require both the x and the n, just as laid out here with prop test. Sample sizes are large. The Wald test and the proportions test will give you essentially the same answers. It's only when the sample size is small that they're going to be different. So here's the theory behind the proportions test. Actually, here's the theory behind the Wald test. Since we're trying to draw conclusions about the difference between two population proportions, we're going to use a test statistic based on the difference in two sample proportions. In other words, we're going to use sample proportion 1 minus sample proportion 2. We do know that x and y both follow binomial distributions, each with their own sample sizes, each with their own probabilities, px and py. One of the biggest problems is x minus y is not going to work because we don't know the distribution of x minus y. It's not binomial. But we do know that the sample proportion for x minus the sample proportion for y is a good estimator of px minus py. And the sample proportion is just the number of successes divided by the number of trials. So that's going to be successes over trials for x minus successes over trial for y. All we have to do now is figure out the distribution of this statistic. If we're okay with approximation, we know that x is approximately normal and y is approximately normal, which means that x over nx is approximately normal, and y over ny will be approximately normal, and x over nx minus y over ny will also be approximately normal. Central limit theorem is just so awesome. I mean, we can say all of that simply because of the central limit theorem. And the approximation increases, the approximation gets better as the sample sizes individually get better. Which is what we're saying here. Remember that if x follows a binomial, then it also approximately follows a normal with expected value of np and variance of np 1 minus p. And we'll subscript all the x stuff with x and all the y stuff with y. Standardizing, dividing by x nx and y will get us this as our normal distributions. Subtracting x over nx and y over ny gets us its own normal distribution. Notice that this px minus py is what we're trying to estimate. In other words, our sample proportion for x minus the sample proportion for y is unbiased for our population proportion x minus population proportion y. That's good. Here's the variance though. And we'll do the typical standardization. We're going to subtract off the expected value, divide by the square root of the variance, and that means that it will follow this test statistic here will follow a normal distribution with mean 0, standard deviation 1. And the standardization comes directly out of either Chapter 2 or Chapter 3 when we did the z-scores or the standardized scores. If px equals py is our null hypothesis, then that means that the second half just goes to 0 or is equal to 0, and this is the usual z-procedure version of the test. We can do an equivalent test to this. This is an aside. If we square this thing on the left, and that means we have to square this thing on the right. Squaring this thing on the left leads us to this. Squaring the thing on the right brings up a new distribution. It's the chi-squared distribution. This probability statement and this probability statement are identical. There is no information contained in one that's not contained in the other. There is no difference in power. There is no difference in precision. There is no difference in accuracy. The two tests are mathematically equivalent. So the one you use, if you use this one, you might as well use this one. If you use this one, go ahead and use this one. They're the same. The proof of that is left for a later class, 225 or 321. So let's see how to do this. I'd like to determine the proportion of males who wear hats is the same as the proportion of females who wear hats. Notice now we're dealing with proportions in two separate populations. Proportion of hat wearers of males and proportion of hat wearers of females. To test this, I sample 100 males and 100 females. 10 males and 16 females were wearing hats. So those are the hypotheses. Step 1, we're going to assemble the information we have. P sub x is what we observe. P sub y, sample proportion, I guess. Nx and y, we asked 100 males, 100 females. Alpha is 0.05, which means our z sub alpha over 2 is plus or minus 1.96. This is the test statistic we have to calculate. I'll give you a hint. There's a fast way of doing this in R, and you already know it. But let's go ahead and churn through this. So here's the formula for the test statistic. This is the plug. This is the chug. And we're chugging some more, and more chugging, and chugging, and we're done chugging. So our test statistic is negative 1.26601. This distribution is our standard normal distribution. This is what we observe. Negative 1.26601. It's right here. That value is as extreme, so is positive 1.26601, or more so is the shaded area on both sides. So these two areas add up, give you the p-value. Because the normal is symmetric, twice this area is the p-value. So we can calculate the p-value. It's 0.2053. Because the p-value is greater than alpha, we fail to reject the null hypothesis. We do not have evidence that men wear hats at a rate different than women, which is what this says. There is no evidence to claim that. They may not. We just don't know. We don't have the evidence. What I just described is the Wald test. Doing this in R is just one line, as opposed to doing all this calculation by hand, all this fun calculation. It's just one line. This is the output. 10 successes for males, 16 successes for females out of 100 trials for men and 100 trials for females. Gives us back the data. Here's the p-value. 0.2071, greater than alpha, failed to reject the null hypothesis, no evidence of a difference. And that's it. How much faster is this than all of this? And I'll tell you this, when I was typing this up, you know how many times I had to go through this and make sure I didn't make a mistake in the calculations? I'm not talking about in the typing it up, I'm talking about the calculations. I think I even made a mistake in the numerator here. I think I made this as plus 0.06. So allowing the computer to do all of this in one line is just amazing. So in today's slide deck, we covered procedures for estimating a single population proportion and for estimating the difference in two population proportions. If you're doing this in if you're doing this for Hawks, Wald test works for both of these. And you should use the Wald test if you're doing Hawks. If you're doing this for real, binomial test for the first and prop test for the second. In the future, we're going to see many more procedures, more tests. Again, create that section in your notebook dedicated to tests and the assumptions of the tests. We looked at binom.test and prop.test. Wald.test behaves the exact same as either one of these, except instead of binom.test, you'll do wald.test. And instead of prop.test, you'll do wald.test. But the parameters that you put over here are going to be the same. Here are some available SCAs to help you work through these. SCA 12 and 22. The 2 means it's for proportions. The 1 is the number of samples. So this SCA 12 is for 1 sample proportions. And SCA 22 is for 2 sample proportions. And they're all located in the usual place. So now I'm going to ask the intra-lecture questions. One of these will be very familiar. Question 1, when is the research hypothesis the same as the alternative? I encourage you to go back and look it up again. The rest of the remaining 2 questions will be different, but similar to each other. For what types of hypotheses do we use the binomial test? And what I mean by that is, I'll just give you the answer because it's fun. The types of hypotheses for which we use the binomial test are those where we're trying to test hypotheses about one single population proportion. And question 3 is, what types of hypotheses do we use the proportions test? I can give you that answer too. It's for hypotheses about comparing 2 population proportions. I don't mind giving the answer sometimes. Chapter 8 in R for Starters, sections 10.4 and 11.4 in Hawks. Go ahead and read up on hypothesis tests in Wikipedia. All procedures.pdf, you should have that printed out and available to you when you're working on stats. And that's the end. Handling proportions. Hope this was helpful. I will see you or talk to you later. Hello and welcome to Chapter 10, where we cover a lot of the hypothesis testing, not all of it, but a lot of it. And here we're looking at categorical independence, Section 7. Categorical independence means that you're testing for independence between 2 categorical variables. Contrast this with testing independence between 2 numeric variables, which will be linear regression, which will be in the future. This lecture is about 2 categorical variables. And that's really what we're doing. Still understanding the theory behind and hypotheses about determining if 2 categorical variables are independent, and better understanding the p-value and how to test hypotheses. Parametric procedure is the chi-squared test of independence. It's called a chi-squared test because the test statistic follows a chi-squared distribution. They're called t-tests because things in the past that we've covered are called t-tests because their test statistic follows a t-distribution. Things in the past have been called z-tests because their test statistics follow a z-distribution. We saw an f-test at one point because the test statistic follows an f-distribution. Here, this is one of many chi-squared tests, and they're called chi-squared tests because the test statistic follows a chi-squared distribution. The null hypothesis is that the 2 categorical variables are independent. The graphic's a matrix plot, or a graphic is a matrix plot. Resign yourself to the fact that graphics for chi-squared tests of independence all look ugly and are difficult to interpret. This requires the expected number of successes to be at least 5 in each cell. Or 10 in each cell, and the reason for this is it's a normal approximation of the binomial distribution. And so larger sample sizes means that that normal approximation improves. Central limit theorem, section 6.5. This function is indeed what Hawks covers, so you won't have to change anything to do your Hawks homework with this. However, for R to give you Hawk's results, you'll need to use correct equals false in the function. And I'll show you where to do that. So let's go ahead and look at a framing example. I would like to test if there's a relationship between whether a person has blue eyes and whether that person is a math natural science major. Yeah. To do this, I asked 100 people at Knox College, so I'm dealing with one large sample of 100 people, and I'm measuring two things on each person. One, if that person has blue eyes or not blue eyes, and two, if their major is in MNS or not in MNS. So here's the contingency table. Notice that each of these is a count. So in my sample, 7 people had blue eyes and were MNS majors. 20 people, 7 plus 13, 20 people in my sample had blue eyes. The 52 people did not have blue eyes and were not math natural science majors. 80 people, 28 plus 52, did not have blue eyes. 35 people were math natural science majors, and whatever 13 plus 52 is, I think that's 65, were not math natural science majors. And adding them all together gives you 100, the number of people that I asked. So a contingency table is a table of counts. So let's ask ourselves this question. What does it mean for two categorical variables to be independent? Recall back to chapter 4, that really fun chapter where it covered independence at one point. That is exactly what we're going to be using to create our expected counts. So we'll have observed counts, expected counts, and when you've got those two, it's just a hop, skip, and a jump to your chi-squared test. So what does it mean? It means that the value of one does not affect the value of the other. Particularly for this, it means that the probability of a math natural science major does not depend on whether you are blue-eyed. We can also frame this as the distribution of MNS majors is the same for blue-eyed people as it is for non-blue-eyed people. We could also frame this as the distribution of blue-eyedness is the same for math natural science majors as it is for non-MNS majors. Let's check with the data for this interpretation. Here's the counts. So what's the proportion of blue-eyed people in this sample? 7 plus 13 over 100, so 20%. What's the proportion of blue-eyed people who are math natural science majors? It's 7 divided by 35. This is the number of blue-eyed people who are math natural science majors, and this is the number of math natural science majors. 20%. It's a match. So if I tell you I'm blue-eyed, that does not affect my knowledge about you being a math natural science major. Notice we could do the same thing. Proportion of blue eyes in the sample versus proportion of blue-eyed people who are not math natural science majors. Again, it's 20%. So if I tell you I'm blue-eyed, that should give you no information, or that does give you no information about whether I am a math natural science major, because the probabilities are the same, or whether I'm not a math natural science major. Probabilities are the same. We can do this with non-blue-eyed people. Proportion of non-blue-eyed people in the sample is 28 plus 52, which is 80, divided by our sample size of 100, 80%. Proportion of non-blue-eyed people who are M&S majors is also 80%, 28 divided by 35. So if I tell you I'm not blue-eyed, I'm not giving you any information about whether I'm a math natural science major, next page, or not, because the proportions or the percents are the same. So me giving you information about my eye color doesn't give you any information about my major. In other words, my eye color is independent of major. Now that we've seen a small example, let's go ahead and generalize this. Here's our data. Variable 1 is A. Variable 2 is B. Variable 1 has two levels, A1 and A2. The B variable has two levels, B1 and B2. X11 is the number of people, the actual counts, who were A1 and B1. X12 is the actual counts of people who were B1 and A2. X21 were the actual counts of people who were B2 and A1, and X22 is B2 and A2 count. I'm going to scroll back to our data. I only have to go back to here. This would be X11, X12, X13, X1. No, I got that wrong. X11, X12, X21, X22. There we go. The variable A is eye color. The level A1 is blue. Level A2 is not blue. The variable B is major. Level B1 is math and natural science major. Level B2 is not math and natural science major. Now we're going to create column and row sums. We'll number the row sums R1 and R2. R1 will be the number of people who are B1. R2 will be the number of people who are B2. Column sums will be the number of people who are A1, and C2 is the number of people who are A2. Going back a slide, so R1 will be 7 plus 28. There are 35 B1s. R2 will be 13 plus 52. There's 65 B2s. C1 is 7 plus 13, so there's 20 A1s and there's 80 A2s. The total sample size will be the sum of everything here, or it'll be the sum of the row sums, or it'll be the sum of the column sums. N's 100. So here's the data that we were working with. Here's abstraction of it. In other words, we've got our counts. This is observed. Now we got to figure out how to get expected. If the two variables are perfectly independent, and again refer back to section 4.3, the expected values would be, well, their expected values would be n times p. So we got the n's common for all of these. P is the probability of being in this cell. If the two variables are independent, that would be the probability of being in row 1 times the probability of being in column 1. If they're independent. Here, this would be the probability of being in row 2 times the probability of being in column 1. Row 2, column 2. Row 1, column 2. Those would be the probabilities multiplied by n to get np, which is the expected counts. So this will be the table of expected counts. You've got the table of observed counts, table of expected counts, and we know what to do with that for a chi-squared distribution. Observed minus expected squared over expected. We're going to call this x2 instead of ts. Chi-squared distribution has one parameter called the degrees of freedom. For the goodness of fit test, it was groups minus 1. For the test of independence, it's going to be rows minus 1 times columns minus 1. Rows minus 1 times columns minus 1. In this example we've been working with, there are 2 rows, 2 columns, so the degrees of freedom will be 1. 2 minus 1 times 2 minus 1. Example, one of the actual examples. We'd like to determine the proportion of males who wear hats is the same as the proportion of females who wear hats. To test this, I sample 100 males, 100 females. You know, this is sounding familiar. 10 males, 16 females were wearing hats. Oh yeah, we have seen this, comparing two proportions. Let's also look at this in terms of a test of independence. Independence between gender and hat wearingness. So, doing it the long way, here's the table of observed values. 16 females had a hat, 84 did not. 10 males had a hat, 90 did not. Row sums are 100 and 100. Column sums are 26 and 174. If the two are independent, then we would expect the proportions of females with hats and the proportion of males with hats to be close to each other and close to 26 over 200. Here's the table of expected values, again in all the painful glory. N times R1 over N times C1 over N. N times R1 over N times C2 over N. R times, etc. So these are observed counts, and these would be expected counts. Doing the math, it actually comes out kind of nice. It took a lot of effort to get it to come out so nice. So here's the test statistic value. Observed minus expected squared over expected. We observed 16, we expected 13. We observed 84, we expected 87. Observed 10, observed 90. We get a chi-squared test statistic of 1.5915. We need to compare this test statistic to the chi-squared distribution with 1 degree of freedom. R is 2, C is 2. Here's how we'd actually calculate that. So the p-value is 1 minus, because it's greater than or equal to 1.5915. Degrees of freedom is 1. Gives us a p-value of 0.2071. After all this fun calculation, because remember we also had to determine the expected values here. Or we can use R. If we add correct equals false, then we'll get the Hawkes result. If we leave the correct equals false out, we'll get a better result. The first step is to create the matrix of observed values. The matrix of observed values. Here's how we do that. We use the function matrix. The first thing we give the matrix function is the counts, and then we specify how many columns. Here, notice that the counts are going in by row. Let me go back. 16, 10, 84, 90. 16, 10, 84, 90. So this line will actually give you the observed matrix. Going back, this thing right here as a matrix. And then all we have to do is a chi.tests of that observed matrix. If we're doing it for Hawkes, we do comma correct equals false. It's this first line that is the most difficult, but it's just the matrix function, the values by row, and then you specify the number of columns. If we do the R, we leave off the correct equals false. Here's the output for R. Got a p-value of 0.2931, degrees of freedom of 1, the observed value of 1.1052. Because the p-value is greater than alpha, we fail to reject the null hypothesis. We do not have evidence that the hat wearing rate for males differs from the hat wearing rate for females. Similarly, we could say we have no evidence that the gender ratio for hat wearers differs from that for non-hat wearers. Both are actually equivalent interpretations. Equivalent interpretations. If one is true, the other is true. Notice the difference between the two tests is minor when the sample size is large. What do we have? 100 or so. Sample size pretty large. So this is with the continuity correction. If we did it with correct equals false, we'd have it without. Example 3. I'd like to determine if females have a different grade distribution in my Stat 200 courses than males. This is data from, I forget what, I think my first 3 years here. So gender, this is A's, B's, C's, D's, and F in the class. Yes, it is fake data. Don't worry. So of all my past students, 57 were females who got A's, 68 were males who got B's, 40 were females who got D's, and 22 were females who got F's. So I would like to determine if the grade distribution for females is different than that for males. In other words, what I want to determine is the grade distribution dependent on gender? Is the grades, a categorical variable, independent of gender? Categorical variable. There are a lot of ways of interpreting this, and they're all logically equivalent. So to do this, we just got to get these numbers into a matrix, 57, 49, 78, 68, etc., and do a chi-test on it. It will automatically tell us that there are 4 degrees of freedom. How did I get 4 degrees of freedom? 2 rows, 5 columns, r minus 1 times c minus 1 gives us 4. Putting the matrix in, specify the number of columns as 5. We did it by column. This is the Hawkes result because I specified correct equals false. P-value is 0.9851. Because the p-value is greater than our usual alpha of 0.05, we cannot reject the null hypothesis. There is no evidence that the grade distribution differs between females and males. Similarly, I could say, hey, I have this student got a C. Well, guess what? I didn't give you any information about the student's gender. Because information about the grade is independent of information about the gender. So let's go to the intra-lecture questions. This looks familiar. When is the research hypothesis the same as the alternative hypothesis? Should have this by now. Question 2. I want you to give an example where you would need to test independence of 2 categorical variables in your area of interest. 2 categorical variables. And this is for our lecture today. You would be able to use the chi-squared test of independence for this example. Question 3 is, give an example of where would you need to use test for independence of 2 numeric variables in your area of interest. You do not know how to do this test yet. This is not from today. Today was just 2 categorical independence. In the future, we'll learn how to do 2 numeric independence. But I want you to start thinking about, okay, where would I need to test for independence of 2 numeric variables? So we learned how to test if 2 categorical variables are independent today. Future, we got ANOVA and linear regression. Chi-sq test performs a chi-squared test of independence. M is a matrix. The SCA is number 41. There are no readings in R for starters. Hawkes has section 10.7. And the usual, don't forget the all procedures. Make sure you have a page for each of these. And that's it. Hello and welcome to the analysis of variance. This is the most important part of chapter 11. Analysis of variance is used to test for independence of a categorical and a numeric variable. That's one use of ANOVA. The usual use of ANOVA is testing for equality of population means amongst more than two groups. So by the end of this lecture, you should be able to understand the theory behind testing the means of more than two populations and the independence between a numeric and a categorical variable. And again, better understand p-values and how to test hypotheses. So let's do a framing example here. I like to test if the average GPA of a student is the same for the four types of majors at Knox. MNS is Math and Natural Science, HSS is Humanities and Social Sciences, HUM is Humanities, I guess it's History and Social Sciences, and Art is all the art stuff. So to do this, I asked 200 students at Knox College, 50 of each major type, and asked two questions. One, what is your major type? Two, what is your GPA? So note that we have one population, students at Knox College, and on every member of that population I asked two questions. One, what is your major type? And two, what is your GPA? If we're looking at a relationship between the two, we're actually testing for independence between those two variables. The major type is categorical, and the GPA is numeric. So here's a box plot, side-by-side box plot of the data I collected. Each dot represents a student that I talked to. Green dots are MNS majors. Horizontally corresponds to the reported GPA. The dots are included as are the box plots for each of the four major types. So there's actually a few equivalent ways of looking at this question. And as you've learned from your math courses throughout the years, the ability to look at a single question from multiple standpoints is always a strength. And that strength leads us to be able to, in this case, determine what the actual test should be. So one way is, do the means in each group significantly differ? In other words, is the mean for math and natural science, which is probably located somewhere around here, is that significantly different than the mean for history and social sciences, which is probably down here somewhere, and for humanities, which looks like it's here somewhere, and art, which looks like it's here somewhere. So the first way of looking at this is comparing the means of the individual groups. Second way of looking at this is, are the group and the GPA independent? These two questions are logically identical. Are the group and GPA independent? And the third way is, does including the group identifier improve our ability to estimate a person's GPA? And since we're looking at the mean, the expected value, what we're looking at is actually testing, okay, does the information of group improve our understanding of GPA? Thinking back to Chapter 4, that's equivalent to saying, are group and GPA dependent or independent? Think back to the conditional probability definition of independence. And it's this last one that gives us some insight into the test statistic. What improving predictions implies is that we reduce the uncertainty in those predictions. And reducing uncertainty means we reduce the variance in those predictions. And this is the idea behind the analysis of variance procedure. First thing you do is measure the variance of the original data. Two, measure the variance that is left over after you include the model. And by model, I mean the group identifier. And then you look at the ratio between the two, from the explained to the unexplained. And it's this last ratio that's actually the test statistic. Now let's think about that for a second. If the explained variance, the variance that's explained by the model or contained in the model or taken care of by the model, is large compared to what's left over, the unexplained variance, then the model is good because the remaining variance is small compared to what you started with. The model is explaining a lot of the uncertainty in the dependent variable. If, on the other hand, the explained variance is small, in other words, if the model doesn't explain much of that dependent variable, then the model is virtually worthless. And it's that ratio, which is an F ratio. It's called an F ratio because the test statistic follows an F distribution. It's this F ratio that leads us to a p-value, which leads us to an interpretation of those results. So that was the theory. Let's go through the calculations by hand. Probably the only time. I think we got one more time when we do it by hand. But so with that background, let's calculate the test statistic and the p-value using the ANOVA table. And here's the blank ANOVA table. This is what an ANOVA table looks like. There's three sources: the model, what's remaining after you apply the model, and then what's originally there. So model is the model that you apply, which is the independent variable, the grouping variable. Error is what remains after applying the model, and then total is what you start with. SS is sum of squares. So this box will contain the sum of squares for the model. This box will be the sum of squares that remains, and this box will be the total sum of squares, or the original sum of squares. Note that this box plus this box will give you this box. This will be the degrees of freedom for the model, degrees of freedom for the error, and then the total degrees of freedom. And the total degrees of freedom will be just the usual, the total sample size minus 1. And again, note that this box and this box will add to this box. MS stands for mean squared. So this will be the mean squared error for the model. Sorry, this will be the mean squared for the model. This will be mean squared for the error. The mean squared is just the ratio of the sum of squares to the degrees of freedom. We saw that back in Chapter 2 or Chapter 3 when we were looking at the variance calculations. It was the sum of the squares divided by the degrees of freedom. We just didn't use term degrees of freedom back then. It was n minus 1. This F ratio is going to be this box divided by this box, and this p-value will be a function of this F ratio according to the F distribution. So let's fill it in, and you get to see all the calculations. The column marked SS contains the sum of squares for those three sources. The sum of squares is just the sum of the deviation between the observation and the mean. Notice the structure of all of these is the same. You're adding up over all the data values. That's what the double summation is. You're adding up within the group to the grand mean. So this is what's explained by the model. The mean within the group differenced with the grand mean, or the mean of all the data values. What's remaining is the variation within the group, the data value to the group mean. And this is the original. This is the data values to the group mean. Back in the day, this was x minus x bar squared, added up. Here we're just renaming x and x bar. So again, this is what's explained by the model. This is the group mean minus the grand mean. This is what's left unexplained, the variance within each of the groups, the data value to that group mean. And this is what you started with. Because each of these calculations require 50 sums, differences, and squares, calculating by hand is not realistic. So I'm just going to give you the answers for this data. Notice I didn't actually give you the data itself. Here's the sum of squares, here's the error that's remaining, here's the total. Notice the sum of squares for the model plus the sum of squares error is going to add up to the total. The important reason for that is that means that the SS model, or the sum of squares for the model and the sum of squares for the error, are independent of each other. Doesn't mean much for us in Stat 200, but it will be important in later stat courses. The column marked DF contains the degrees of freedom for the three sources. They're the parameters that reflect the amount of information contributed by each source. probably believe the best definition of degrees of freedom. The degrees of freedom total is just the total sample size minus 1. So it'd be 200 minus 1 because I asked 200 people. DF model is the number of groups minus 1. There's 4 groups, 4 different major types, so DF model will be 3. And then the way I calculate it is just DF total minus DF model. That'll give you DF error. 3 and 199, and the DF error will be 196. The mean squared will be the sum of squares divided by the degrees of freedom. Now this should look very similar to what we got back in chapter 2 with the variance, sample variance. It was 1 over n minus 1 times the sum of x minus x bar squared. Calculating the same thing here. This is an estimator of a variance, just like s squared was an estimator of a variance. So mean squared model is 2.6104, mean squared error is 0.4718. This F statistic is going to be the mean squared model divided by the mean squared error. As you should guess by now, the distribution of the F statistic is F. That's the name of a distribution. Do you know what that distribution is named after? Fisher. John Fisher, one of the luminaries of early statistics in the 20th century. There's F, it's 5.533. Last box, we'll calculate the p-value. P-value is calculated in exactly the same way. It's the probability of the test statistic being this extreme or more so, given the null hypothesis is true. If the null hypothesis is true, F will be 0. I mean, if the null hypothesis is perfectly true, this F ratio will be 0, because there will be no, this number will be 0. This number will be 0. Remember, the null hypothesis is there is no difference in the means, or the null hypothesis is that the two variables are independent, or the null hypothesis is the model explains none of the variation. If the model explains none of the variation, this is going to be 0, which means the mean squared is going to be 0, which means the F ratio will be 0 over something, which is 0. So this is the probability of the distribution being greater than or equal to 5.53. Which looks like this. Here's the F distribution for this particular problem. P-value is way out here. It's this area that's hard to see. It's 0.00115. How do we interpret the p-value? Absolutely correct, same as always, compare it to alpha. If the p-value is less than alpha, as in this case, we reject the null hypothesis. That means all of the following three things. The two variables are not independent. And that is GPA and major type. Those are not independent because P is too small. It means the average GPA in the 4 groups is not the same. And it means if you want to model the GPA, if you want to explain the GPA, then including the major type will help with that. Okay, let's look at the rice yields. I'll give you the data so we can see how all the calculations are done. Does rice variety influence the average yield amongst these 4 varieties? Here's the yield in each of the 4 plots for each of the 4 varieties. So we got 16 plots. In each plot we planted one of the 4 varieties of rice. So there's the raw data. Here's a graph. Sure seems like variety D is much higher than the rest. I don't know about variety A, but it certainly seems as though at least one of the 4 varieties has a different average. Here's the blank ANOVA table. Let's calculate this all together, just so we can see, oh wow, we really don't want to do this by hand. So here are the formulas for SS model, SS error, and SS total from here. So here's SS model. We're adding up over all the data values, the average in the group minus the grand mean squared. What this actually translates to is this, because there's 12 data points, so we've got 12 terms. From the data, this is what we get. The grand mean is 991.9375, and the individual group means or variety means are those. Now we just plug and chug. This term becomes 984.50 minus 991.9375 squared plus etc. Substitution. Do a lot of calculations and we get 89,931. So the sum of squared for the model is 89,931. We can do the same thing with the error and total. We could just calculate the total, which is the variance of the data, and subtract off the model to get the error. Degrees of freedom. We've got 16 data points, so DF total will be 16 minus 1. We've got 4 groups, so DF model will be 4 minus 1. And then DF error will be 15 minus 3. Mean squared is just the sum of squares divided by the degrees of freedom. That 2 should not be there. The F ratio is just the ratio of the mean squared of the model to the mean squared of the error. So this would be about 30 divided by 4 should be about 7.5. This is the F ratio, and it follows the F distribution. That's why it's called an F statistic. It follows the F distribution. And now this p-value is the probability of this distribution being greater than or equal to 7.212. There's 7.212. This shaded area is the p-value. 0.00503. Interpret the p-value in the usual way. Compare it to alpha. If the p-value is less than alpha, reject the null hypothesis. In this case, the null hypothesis is that the 4 means are equal, or that the yield variable and the variety variable are independent, or if we're trying to model the yield of wheat, was it wheat or corn? If we're trying to model the yield of whatever grain this is, including the variety will help. Those 3 are equivalent. The one you use depends on what you're trying to understand about rice. I guess it's rice instead of corn or wheat. Now we'll do it in R. 3 lines to get the data in. It's the rice data set. Summary just to make sure that you loaded it in correctly and attach it. That's what the box plot looks like after prettying it up a little. Here's the code for the fancy box plot. The box plot line is actually way down here. This will just get you a nice plain box plot. Here's the 2 lines of code to do all of the ANOVA calculations that you need to do. We'll call it rice mod. It's the model about rice. The function is AOV. analysis of variance. In parentheses, this is the dependent variable. That's the tilde to the left of the 1. And this is the independent variable. The dependent variable here is the numeric variable, and the independent variable is the grouping variable, or the categorical variable. This Rice mod line doesn't do much of anything except everything inside. It's the summary that takes it from what's inside R to actually put it in a form that is meaningful for you. Notice it doesn't give the total stuff, but we can figure out degrees of freedom total is 15. The sum of squares total is just the sum of those two. There are 4 varieties, so the degrees of freedom for variety is 4. There's the sum of squares. The mean squared is the sum of squares over the degrees of freedom. The F value is the ratio of the mean squared variety to the mean squared residuals, which is often called error instead of residuals. Here's our p-value. Notice we got 2 stars on it. 2 stars is down here, so that p-value is between 0.001 and 0.01, which we knew because we got the p-value there. And that's it, just those 2 lines. Once you get the data in, just those 2 lines, interpret. Same conclusion. Ronald Fisher introduced the ANOVA procedure in his 1925 book. And to illustrate ANOVA, he came up with this experiment. Collect a sample of pond water. Okay, so you take your 5-gallon bucket and dip it in the pond, and you've got a sample of pond water. Now divide that water in that same bucket amongst 4 different beakers. Now separate the beakers to ensure that there's no cross-contamination, and from each beaker take 4 samples and count and record the number of amoeba present. So you got this sample of pond water. Dip 4 beakers in that same sample. So you would expect the amoeba concentration to be the same in those 4 beakers. And now from each beaker take 4 small samples and count and record the number of amoeba. So you'd expect the averages in each of those 4 samples from each of the 4 beakers to be about the same. So we would expect the p-value of this experiment to be rather large. The data is available in the Fisher 38 data file. This loads it, attaches it. This does the analysis of variance, and the summary gives us these results. And we got a p-value that's rather large. Notice that when the f value is small, the p-value is large. And when the f value is large, the p-value is small. It's because the larger the f value, the more extreme your observations are if the null hypothesis is true. And the null hypothesis is either all the means are equal, or the 2 variables, the numeric variable and the grouping variable, are independent, or that grouping variable gives us no information about the numeric variable. There's that F distribution, there's the p-value in darker blue. It's not small. We didn't expect it to be small. There's the conclusion. And at this point we should be asking, do these results make sense for every single analysis? The results either make sense, or we are learning something new, or we did something wrong. So here's the summary slides, but I'm going to throw in the intra-lecture questions here. So the first intra-lecture question: does a large value of f correspond to a large p-value or to a small p-value? Does a large value of f correspond to a large p-value or a small p-value? And again, I would write the question in your notes on the left, answer below. Question 2, what is the null hypothesis in ANOVA? Notice I've given you 3 options for this. Give me any of those 3. In 3, here's a given example where you would need to test for the independence of one numeric variable and one categorical variable. Any example will work. Any good example will work. So here's what we did in today's slide deck. We covered ANOVA. This procedure helps us determine 3 things. If the mean of several groups are the same, if a numeric and a categorical variable are independent, and if knowing a group membership helps with estimation of the dependent variable. All 3 of those are logically and statistically equivalent. The way that you frame your results will depend on what the original research hypothesis and/or research question are. If the researcher is asking about the means of several groups, then that's the one you're going to use to interpret your ANOVA. In the future, we're going to do linear regression. Same reminders as always. Create that section in the notebook dedicated to the test and the assumptions of that test. Take advantage of the SCAs and use the all procedures handout. There's some functions that we are hinting at. The AOV function we did and the summary function we did. You've already seen the Shapiro test function. The Fligner test function is what we're going to use in the next set of slides. Notice that all we were able to conclude was the means are all the same, or at least one mean is different. We weren't able to determine which mean was different. The next set of slides will cover that. We looked at. We could also conclude that the 2 variables are independent or they are dependent. We weren't able to classify what type of dependence. The next set of slides will help with that. However, the Fligner test will need to be used to test one of the assumptions of ANOVA. But that will be for next time. And there are the readings, and that's the end. And I hope this was fun, or at least helpful. Hello and welcome to Beyond ANOVA. In the last lecture slides, we ended up with only being able to determine if at least one of the means was different, or if the 2 variables are dependent or independent. We weren't able to tell which of the means was independent. And fundamentally, that's the purpose of this set of lecture slides. The other purpose is to figure out what do we do when we can't use ANOVA. That is, ANOVA's got its own set of assumptions. We have to test those assumptions. What do we use if those assumptions are not met? So yesterday, or the last lectures, we saw the theory behind ANOVA. We performed the calculations behind ANOVA by hand and saw how cumbersome that was, and then we used R to perform these calculations for us with 2 little lines. Today we're going to understand the assumptions behind ANOVA a little bit more. We're going to test those assumptions. We're going to get to know the non-parametric test for ANOVA, because remember, we've got a parametric test. It was a 1-sample t-test, a 2-sample t-test, and ANOVA. And we've always had a non-parametric version if the assumptions of that parametric test were not met. For the 1-sample t-test, it was the Wilcoxon test. For the 2-sample t-test, it was the Mann-Whitney test. And for ANOVA, it's going to be the test. I guess. So here we are, the z-test, the t-test, and the variance test all assumed normality in the population. We tested that normality using the Shapiro-Wilk test. If the p-value on the Shapiro-Wilk test was large enough, then we could use those parametric tests. If not, then we couldn't. For the t-test, 1 sample, we could use the Wilcoxon test if symmetry was met. In the 2-sample, it was Mann-Whitney test, and there really were no testable assumptions. For the Wilcoxon test, if symmetry was not met, then we'd have to use the non-parametric bootstrap. For the binomial test, there were those 5 requirements, none that were able to be tested using R. Those were all based on how the data were collected. proportions test required normality, as did the chi-squared goodness of fit test and the chi-squared test of independence, so it's also required normality. However, those normality tests were not based on the Shapiro-Wilk test. They were based on, do we have enough data so that the binomial is appropriately estimated by the normal distribution? So the double stars refer to needing the sample size to be large enough for the central limit theorem to help us with the normality. The single stars binomial test, you've got the requirement of the 5 requirements for a binomial distribution, and the Whitney test, there is an assumption to it, but that and the binomial test are beyond the scope of this course. For the ANOVA procedure, there are 2 assumptions we need to make. Assumption 1, as you might be able to guess, is normality in each group. All of the parametric tests we've worked with so far, normality has been the assumption. So same thing with ANOVA. Normality must be, the data in each group must be normally distributed. The second assumption is equal variances across the groups. That is, the variances in group 1 has to equal the variance in group 2, has to equal the variance in group 3, has to equal variance in group 4. Remember, these are population statements. So the population variances have to equal. The population distribution has to be normal. We know how to test normality, Shapiro-Wilk test. The test for equal variances is called the Fligner-Killeen test. The null hypothesis for the Shapiro-Wilk test, as you know, is that the data are from a normal distribution. The null hypothesis for the Fligner-Killeen test is that the variances, the population variances, are equal. The small p-values indicate that the requirements are not met by the data. In order to use ANOVA, all assumptions must be met. So all groups must pass the Shapiro-Wilk test, and the entire thing has to pass the Fligner-Killeen test. If any of those get too small of a p-value, then we cannot use analysis of variance. So let's look at the Rice example again. First, we got to test, since we're testing for independence between a numeric and a categorical, we would like to use analysis of variance. Here are the hypotheses. The null hypothesis is that all 4 means are equal. Remember, this is in the population. The alternative is that at least one of those 4 means differs from the others. The alternative hypothesis is not that all 4 means differ. The opposite of all are equal is at least one is not. We'd like to use ANOVA because it's the most powerful test for this type of hypothesis. However, this test has 2 assumptions: normality in each group and equal variances across the groups. So here's how we test normality and equal variances. Bring in all those extra functions, read in the data, attach the data, do the Shapiro-Wilk test, do the Fligner-Killeen test. It's Fligner.test. And the thing in parentheses is the exact same thing as you put in the parentheses for the Shapiro-Wilk test. The yield, which is a numeric variable, there's the tilde to the left of the 1, and the grouping variable, which is variety. Here's the output for the Shapiro-Wilk test. Here are all the p-values. Notice all the p-values are greater than alpha. Therefore, there is no violation of normality that we can detect. Here's the result of the Fligner-Killeen test. Notice it tells us that the null hypothesis is homogeneity of variances. Homogeneity is the $10 word for equal variances. There's the p-value. What do we do with p-values? As always, compare it to alpha. Is this p-value greater than alpha or less than alpha? It's greater than alpha. Since the p-value is greater than alpha, what do we do with the null hypothesis? Fail to reject it. Therefore, we fail to reject homogeneity of variances. We have no evidence that the variances are different. So in other words, passes the normality test, passes the equal variances test. So we can use ANOVA. We've already done that last time. Notice we've got a paragraph dedicated to the assumptions test that ends with a sentence that tells us which test we're going to use, and then an interpretation of the results of that ANOVA procedure. Conclusions are getting long because we are adding more to them, because we're conveying more information to our readers. Notice that the conclusion was at least one mean differed from the others. That's all we can do with ANOVA. At least one mean differs from the others. That's it. We don't know which mean is different. We want to know which mean is different, but ANOVA doesn't tell us that. ANOVA can't tell us that. However, there is an easy test that can tell us which of the groups is different. It's called Tukey's HSD test, or Honestly Significant Difference test. The assumptions for Tukey's HSD test are the same for ANOVA, so if you use ANOVA, use Tukey's HSD test. If you use ANOVA and the p-value is too small, use Tukey's HSD test to determine which mean is different. I'll repeat that. If you use ANOVA and the p-value is too small, use Tukey's test to determine which mean is different. Here's how you run the Tukey HSD test. This is the Rice model variable. So we're applying Tukey HSD to Rice mod. Here's the output. Not the most user-friendly of outputs. Again, it tells us the name of the test, specifies the confidence level. Again, it repeats what our original ANOVA was, and then here's the results interest us. Which column do you think is the most important column to look at first? If you said the p-value, good for you. It's this last column. These are all the p-values for something. We will talk about what they are for pretty soon. What do we compare the p-values to? Correct, we always compare p-values to our stated alpha. By default, alpha is 0.05. This being greater than alpha tells me the null hypothesis for whatever hypothesis this is for is not rejected. 0.747 is greater than alpha. Failed to reject this null hypothesis. 0.0567296 is greater than alpha. It's pretty close. We'll talk about that pretty soon. 0.995769 greater than alpha. 0.0066, so that's less than alpha. And the bottom one is less than alpha. Now, so we're going to focus on these two because those p-values are less than alpha, and we're going to go all the way over here. What's less than alpha? The p-value, which means that d minus b is not 0. D minus C is not 0 in the population. So we have shown, since in the sample D minus B is positive, that the yield for D is greater than the yield for B. D is greater than B, because this is positive. In other words, rice variety D tends to give a higher yield than rice variety B as in Bob. Similarly, rice variety D gives a higher yield than rice variety C as in comma. This is the differences in the samples. This is a 95% confidence interval for that difference. So we're 95% confident that variety D gives between 42 and 313 bushels per acre more rice than variety C. So we were able to detect a difference between varieties D and B and D and C. From our selected alpha, none of the other differences are significantly different, or none of the other differences are significant, or we did not detect a difference in any other comparisons. This one's 0.0567296. If we are hung up on alpha is 0.05, then we'd say, nope, no difference between D and A. D and A was discovered. However, that's pretty darn close to 0.05. So what should we tell our client? And that's what this is saying. P-values, interpret them for the null hypothesis that the difference in averages between these two levels, B and A, C and A, D and A, C and B, D and B, and D and C, is 0. Usual level of significance, only detect between B and D and C and D, the bottom two, because these are the only two that have p-values less than alpha. We know that variety D has a higher average yield than variety B by between 53 and 324. And D is higher than C by between 43 and 313. And we do not detect a difference between the average yield between any other comparisons, because all the p-values for the other comparisons were greater than alpha. That's not too surprising. Here's variety D. It clearly is greater than B and C. B and C look very close. Average of A and C look close. So these three, I would imagine it's hard to determine which is greater than the others, which is less than the others. I would say mainly because we only got 4 data points in each of the four groups. So, what if any requirement / assumption is violated? If any of them is violated, we shouldn't use ANOVA. We should use what's called the Kruskal-Wallis test. It's got the same requirements as the Mann-Whitney test. It is part of the Agricole package. Its output is much simpler than that of ANOVA. It has its own multiple comparisons test called the Kruskal test, or the Kruskal multiple comparisons test. And the Kruskal test output is also much simpler than that of Tukey. So let's see an example of that. Citizens' initiative allows people of the state to force a vote on a given issue, a vote of other people in the state. Do the political cultures use the initiative at the same rates? Political cultures will be our categorical variable. Initiative will be our numeric variable. Null hypothesis is that the 3 means are the same. Alternative is at least one of those 3 is different from the other 2. Could be that they're all different. We have to test the assumptions of ANOVA. One assumption is that the data come from a normal distribution in each group. The other is the data have the same variance across the groups. Shapiro test tests the first. Fligner-Kleene test tests the second. Notice the stuff in parentheses is identical. Here's the output. Normality. None of those is greater than alpha, so we could actually just stop and say, no, we can't use ANOVA. However, going on, we see the Fligner-Kleene test also has a p-value less than alpha, so even more so we can't use ANOVA. So can't use ANOVA. What do we use? We use the Kruskal-Wallis test. It's used a Kruskal.test. This is important. Very important. Numeric variable, comma, categorical variable. For the Kruskal-Wallis test, that should be a comma. For ANOVA, this would be a tilde. So be aware of that. And notice we're not saving this as anything. We're just saying Kruskal.test. We're just running the test. We're not saving it as a model. Here's the output. There's the p-value. What do we compare the p-value to? Alpha. Is the p-value greater than alpha, less than alpha? Less than alpha. What does that mean about our null hypothesis? We reject our null hypothesis. What does that actually mean? Since we reject our null hypothesis, we conclude that at least one mean differs from the others. We don't know which one. We just know that at least one is different. Kruskal-Wallis rank sum test tells us the same stuff as ANOVA, whether or not the means are all the same. Since at least one of the means is different, we move on to the Kruskal multiple comparisons test. And I also need you to pay attention. The Kruskal multiple comparisons test and the Kruskal-Wallis test are in the Agricole package. That's why they're behaving a little bit differently than what we would expect. Cruscal is the function. Again, we got the comma. So cruscal parenthesis dependent variable, the measurement variable, the numeric variable, comma, independent variable, the categorical variable, the grouping variable. And then that cruscal function is wrapped in a print function. If you don't use the print function, you're not going to get any output. So don't forget this. And between the two of us, I agree this is very poor programming on the part of the people who created the Agricole package. But it is what it is. There's a lot of output. This is the important ones. Notice that this output looks a lot different from the Tukey HSD test output. I prefer this output because it actually tells us something about the grouping. It's a lot easier to read. If we did a Tukey HSD, we would have 6 rows to pay attention to. Here we have 3, one for each of the groups. Those groups that share a common letter are not significantly different. So moralistic and individualistic, because they both share an A, we did not detect a difference in the means between those two. Individualistic and traditionalistic, because they share the letter B, we did not detect a difference in the means between those two groups. Moralistic and traditionalistic, because they don't share a letter, we were able to detect a difference between the average for the moralistic states and the average for the traditionalistic states. Moralistic states use the initiative at a greater rate than did traditionalistic. So for the Cruscal multiple comparison test, you look for the groups. Those group levels that share a common letter, we did not detect a difference between. So again, first paragraph we spend talking about the assumption tests. We end up with what tests we actually used. Then we interpret the results of that that test. Don't hide anything from your reader. Share it with your readers. The results really aren't that surprising, or maybe they are, I don't know. We were able to detect a difference between the traditional, I actually don't remember what we were able to, moralistic and traditionalistic. Okay. Between the top two, we were able to detect a difference. However, there's enough variation that we couldn't detect a difference between traditionalistic and individualistic, or between moralistic and individualistic. Okay, we're going to go through about 4 examples now. Before we do, let's look at some of the intra-lecture questions, though. Intra-lecture question 1, what are the assumptions of ANOVA? And there are 2. Question 2, what tests are used to test each assumption? So what's the test you use for the first assumption, and what's the test you use for the second assumption? Not the code, the name of the test. And 3, what test is used if ANOVA is not appropriate? So ANOVA's got those 2 assumptions. If either of those assumptions is not met, we have to use this other test. And what's this other test called? The name of the test, not the code. So let's go through some examples. 4 examples. Does the 2000 violent crime rate significantly vary across the 4 census regions? 2000 violent crime rate is your numeric variable. 4 census regions is going to be your categorical variable. Here's hypothesis. The null hypothesis. The mean in the northeast is equal to the mean in the south is equal to the mean in the midwest is equal to the mean in the west. And the opposite of all are equal is at least one is not equal. I would like to use ANOVA. ANOVA's got 2 assumptions, normality and equal variances. Here's how I test the normality. Here's how I test the equal variances. Here are the results. We look at the p-values. All of these p-values are greater than alpha, so we're good to go so far. Got to check the homogeneity of variances. P-value is greater than alpha here, so we are good to go. We can use ANOVA for this problem. To use ANOVA, figure out some name for the model that's going to equal to our AOV function. Dependent variable, the numeric variable, that's the tilde. Independent variable or grouping variable. To get the results, summary of C mod 1. Here's your ANOVA table. Here's the p-value. Because the p-value is less than alpha, we reject the null hypothesis. The average violent crime rate in one of the four senses is not equal to the other. At least one. Don't know which one from ANOVA, we just know that at least one is different. To determine which one is different, we use Tukey's HSD test. Why do we use Tukey's HSD test? It's because we were able to use ANOVA. Here's the partial output of Tukey's HSD test. We look here for the p-values less than alpha. This one's less than alpha. This one's less than alpha. So south is significantly higher than the northeast. Why higher? Is because south minus northeast is positive. South is significantly higher than west. Why higher? Because west minus south is negative. So we detected that south is significantly higher than the west and the northeast. No other combinations were detected to be different. There's the conclusion. The first one is about testing the assumptions, ending up with what test we're going to use. And then the second is an interpretation of those outputs. Here's the box plot. I would imagine the big reason that the south is so much higher on average is because of this outlier. If we eliminate this outlier, it would be nice to know if the conclusions would be the same. And what does this outlier correspond to? I'll let you guess. Example 2. Does the 2000 weighted average educational attainment significantly vary across the three political cultures? This WAEA is your numeric variable. Political cultures will be your categorical variable. Mu for the individualistic is equal to mu for the moralistic is equal to mu for the traditionalistic is our null hypothesis. The alternative is that the null is wrong, that not all are equal, that at least one is different. I'd like to use ANOVA, but ANOVA's got two assumptions. Here's how we check those assumptions. Here are the results. P-values here look good. P-value here looks good. We can use ANOVA. P-value on ANOVA. Notice AOV is a function. We save it into a variable because there's a lot of information that's used or created from this function. P-value is less than alpha. We know that the WAEA is weighted average educational attainment, is different in at least one of the three. Don't know which one. To figure out which one, we do Tukey's HSD. So we do ANOVA if we can. If we're able to do ANOVA and the p-value is small enough, we do Tukey. If the p-value on the ANOVA is not small enough, then the conclusion is we didn't detect a difference. So it doesn't make sense to then go on and say, okay, which is different? Because we didn't detect a difference. Here's Tukey's output. P-values, these two are very less than alpha. First one's not. So it looks like traditionalistic is significantly less than individualistic, and traditionalistic is significantly less than moralistic. So the traditionalistic states tend to have a lower weighted average educational attainment than the other states. We weren't able to detect a difference between the moralistic and the individualistic states. Here's the conclusion. Notice that the first paragraph again takes us to which procedure we're going to use. Second paragraph interprets the results of that procedure. There's the box plot. Looking at the box plot, our conclusions are not surprising. Clearly, the average of the traditionalistic is less than the average of the other two. Example 3. GSP per capita, that'll be our numeric variable. Vary across the 3 political cultures, that'll be our dependent variable. I got that backwards. The GSP per capita is our numeric variable. This is our categorical variable. Sorry, I spaced out there for a second. 2 hypotheses, the means are all equal, the means are not all equal. Test normality, test equal variances, Shapiro, Fligner, Colleen. Interpret the results. Okay, we can stop right there. Shapiro-Wilk test, at least one of these is less than alpha. I don't care if all 3 are less than alpha or only one. At least one is less than alpha. Therefore, we cannot use analysis of variance, and we have to use the Kruskal-Wallis test. Here's how we do the Kruskal-Wallis test. There's the p-value. Since the p-value is less than alpha, we did detect a difference. The GSP per capita in 2000 for the 3 dominant political cultures is not the same. Don't know which of the averages is different. We just know they're not all equal. Now here is the Kruskal multiple comparisons test. Remember, Kruskal is a function to do the Kruskal multiple comparisons test, and then you got to wrap it in a print function. Again, remember it's comma instead of tilde. There's a partial output. So individualistic is higher than all the others. Moralistic and traditionalistic, we could not detect a difference between those two. So the individualistic states, on average, have a higher GSP per capita than the moralistic and the traditionalistic. There's the conclusion. Again, first part leads us, or first paragraph leads us to what test we're doing, and the second interprets the results of that test. Box plot. Example 4. Does the professional level of the state's legislature, numeric variable, significantly vary across the 3 political cultures, categorical variable? The means are equal for the null hypothesis. The means are not all equal for the alternative. Not all equal means that at least one means differs, not that they're all different. Normality, equal variances. We got at least one of these is less than alpha, so we can't use analysis of variance. We have to use the Kruskal-Wallis test. Kruskal.test, p-value is less than alpha. Since the p-value is less than alpha, we were able to determine that at least one of the means is different. We don't know which one. We'll do the Kruskal multiple comparison test. A, B, and B. So the individualistic is significantly higher than the other two, and we were not able to detect a difference between the other two. There's the conclusion. There's the box plot. I labeled some of the parts. Massachusetts and New York, California and Michigan. Definitely outliers. So I wonder if we got rid of these outliers, what the results would be. So here's what we did today. We covered ANOVA and related procedures, the Kruskal-Wallis test. They tested 3 things. If mean of the groups are the same, if the numeric and the categorical variable are independent, if knowing the group membership helps with estimating the dependent variable. Again, those are the three ways of framing the null hypotheses. They are equivalent logically. And not only were we able to determine if they're the same or independent or doesn't help, we were able to figure out how to determine which mean is different. Provide a statistical ranking of the levels. So the first three come from ANOVA or the Kruskal-Wallis test. The last one comes from Tukey's HSD or from the Kruskal multiple comparisons test. SCA for this is 42A and 42B. We just have linear regression left, but that also includes correlation. Same reminders as always. Create a section in your notebook dedicated to the tests and to the assumptions of that test. Download and use the All Procedures handout. Take advantage of the SCAs available for practice. And email your professor. Here are the functions we've used. And I believe there actually is a typo here. I believe for the Kruskal multiple comparisons test that does need to be a comma instead of a tilde. I think I just got copy paste happy. So change this to a tilde. Or leave it as is, and if you don't get anything that you like or if you get an error, then change it to a comma. Same thing here. Use a tilde. If that doesn't give you what you want, then use a comma. The rest are fine. There are the SCAs. And by the way, we are covering the slide deck this term. Boom. And that's the end. This was a lot. These two sections, 11.6 and 11.6 plus, ANOVA and beyond ANOVA, are a lot. The book itself only does the ANOVA part. However, as you know, you can't use ANOVA without understanding its assumptions. If you just apply ANOVA whenever you want, and the assumptions aren't met, your conclusions are going to be wrong. And you don't want wrong conclusions if you can help it. So I actually would go through these two sections again. Double check that your notes got everything. Use R to go through as many of these activities or examples that we can. And practice, practice, practice. Ta-ta. Hello and welcome to Chapter 12. This will be the last chapter of the term. Chapter 12 covers looking at relationships between one numeric and another numeric variable. The first section of Chapter 12 just looks at correlation, looks at trying to determine if two numeric variables are related and how strong that relation is. Once we move on beyond section 12.1, we're going to see ways of modeling dependent variables that are numeric using other numeric variables, which allows us to estimate and predict future values. By the end of this lecture, you should be able to understand the theory behind testing correlation between two numeric variables. And a lot of what we're doing in this lecture is going to be history, seeing how we got to where we are. So what we've done recently is looking at how to test for deep independence between two categorical variables. That'll be the chi-squared test of independence, and between one categorical and one numeric variable, and that'll be ANOVA, or the Kruskal-Wallis test if the ANOVA assumptions aren't met. In this test, we're going to look to see, in this deck, we're going to look to see how to test independence between two numeric variables. We're going to use correlation. So we'll start a framing example. Is there a significant relationship between the violent crime rate in 1990 and in 2000? Notice the question is there a significant linear relationship? So how could we possibly do this? And the question is awesome, and give you a little hint. Statisticians, when they're lost for how do we do a test, the first thing we're going to do is graph the variables. And that's what this is. Now, looking at this graph, is there a correlation between these two variables? Do you think, by looking at this graph, there is a correlation? I agree with you. I think there is a strong correlation between these two variables. Now, what is it about this graphic that makes you think that there's a strong correlation? So you go from, yes, I think it is, to breaking it down as what aspects of this graphic make me actually think that. And once you get down to the nitty-gritty and understand why or what aspects of this graphic make you think that there's a strong correlation, you're going to better understand what correlation actually means, and, by extension, how to test for it. So, that question that I just asked, the exercise I just put you through, is what the early statisticians were doing. This was the actual question that led us, eventually, to our modern measure of correlation. We didn't start out with this measure of correlation, the Pearson measure, but we eventually got there. So the next several slides walk us through the history of the answers to this question. So, first step was to compare the number of concordant points to that of discordant points. By the way, these are going to be more for you to understand how we got here. I will not ask any questions on what is a concordant point and what is a discordant point. So relish the history here and the way that statisticians got from the very simplest definition of correlation for them to the one we actually use today. So a concordant point is one that supports a positive relationship between the two variables, and discordant supports a negative relationship. In other words, concordant points are the green ones, because these are the ones that line up along a positive slope, and the red ones are along the negative. What's the difference between red and green? Well, the vertical dotted line is the average of the horizontal values, and the horizontal dotted line is the average of the vertical. So this actually splits it up into 4 quadrants. Quadrant 1, 2, 3, 4. When you got points in quadrant 1 and 3, they lie along the positive slope line, so those would be concordant points. And those in 2 and 4 lie along a negative slope line, so those would be discordant points. So the first attempt at measuring correlation was to calculate something called a concordance ratio. Concordance ratio is just the number of concordant points, the number of green dots, minus the number of red dots, discordant points, divided by the total number of dots. So really all we're doing is measuring some sort of nominal level variable of which of the 4 quadrants is the dot in. And as we know, nominal variables contain very little information, and if we want to move forward, we need to get more information in those variables. So here the concordance ratio is 84%. So we would conclude that is very high. So it is a high positive correlation, because 0.84 is a positive number. If the number of red points was much larger than the number of green points, like if there were 47 red points and 4 green points, then this would be a negative 0.84, and we'd say a strong negative correlation, or a negative concordance ratio. There are some strengths to this. It's easily calculated. It's just counting. The numbers range between -1 and +1. I mean the concordance ratios range between -1 and +1. You'll get a -1 if this numerator is negative the denominator. In other words, if all of the points are red points. It'll be a +1 if all the points are green points. That is, if all 51 of these points were in quadrants 1 or 3. There is weakness. It ignores information about the points. And statisticians hate ignoring or throwing away information. The information that's ignored is how far from that center the point is. All of the points have the same weight. Even if they're close or if they're far from the center, they all count as one. To fix this weakness, the covariance was created. Covariance is an important measure in its own right, but it was originally created to discuss correlation between two variables. Covariance is a measure of how much the two variables vary together. Notice that this takes into consideration both the concordance and the distance to the center. So this is a measure of the distance to the center, and this is measured to the distance to the center. The first one is along the x-axis, the second is along the y-axis. So those dots that are farther from the center, farther in the first quadrant, this will be a very large positive number. This will be a very large positive number. So the covariance will increase a lot positively. If they're in the third quadrant and far away, this will be a very large negative number, a very large negative number, but negative times negative is positive, so this will be a very large positive number. That'll also lead to a positive covariance. That's 1 over n minus 1. This sure looks like the variance formula. In fact, what's the difference between the covariance formula and the variance formula? So DC, which is way out here, will add a lot of positive value to the covariance, whereas this red dot here will add a little negative value to the covariance, and this green dot way back here will add a lot of positive value to the covariance. So from looking at this, we would know that the covariance was probably pretty large. In fact, the covariance for this is 88,047.41. Function for covariance is COV. Now, what's a strength of the covariance? It takes into consideration which quadrant you're in, positive, positive, or negative, negative, plus it also takes into consideration how far away from the center you are. Farther away from the center, the more weight you're given to the correlation. Drawback, covariance of 88,047.41. I don't know if that's humongous. I don't know if that's small. It depends on the measurement of the data values themselves. If the violent crime rate was actually measured from 0 to 25,000, then the covariance would be 880,000. It actually would be less than that, but pretend. So that's its drawback. It does not range between -1 and +1. So it's got its strengths, but it also has its weakness. To fix this weakness leads us to the actual definition of correlation that we use nowadays. And this is where you should start taking notes again. Not just accept the history of it, but okay, this is where it is. Correlation is a standardized measure of how much two variables vary together. Covariance was just a measure of how much the two variables vary together. Correlation is a standardized measure. Notice the numerator here is just the covariance. We're standardizing by the standard deviation of x and the standard deviation of y. Why do we standardize by the standard deviation of x and the standard deviation of y? Because that forces this measure to range between -1 and +1. Values of +1 mean perfect positive correlation. Values of -1 would be a perfect negative correlation. Values of 0 would be absolutely no correlation. And this is going to be the correlation measure we use, symbolized by little r for the sample correlation. For the population correlation, it's the Greek letter rho. And this contains all of the advantages of the covariance, plus it avoids the disadvantage of the covariance because now it ranges from -1 to +1. The correlation here is 0.9364691. Very strong positive correlation. Because the highest you can get for correlation is a positive 1. This is really close to positive 1. So here's some graphics. This is a strong positive correlation. This one on the right is a strong negative correlation. And this actually is a no correlation. Why no correlation? Is because this correlation is a linear measure. It looks at lines only. Doesn't look at parabolas. It looks just at a line. So this should lead you to realize that a strong correlation does indicate a strong dependence between the two variables, but a zero correlation does not necessarily mean the two variables are independent. Because here we've got a zero correlation, but we see clearly that the x and the y are dependent. That if you tell me a value of x, I can give you a good estimate for the value of y. It can be shown, that's code word for beyond the scope of this course, it can be shown that the sample correlation is approximately normal with expected value of rho. Rho is the population correlation. And variance of this, 1 minus rho squared over n minus 2. Now it can be shown that this is true, but only for correlations near 0. Since we know the distribution of our sample statistic, even approximate distribution of our sample statistic, we can create confidence intervals, p-values. Here's our test statistic t. It's our sample correlation divided by the square root of that standard error. Follows a t-distribution with n minus 2 degrees of freedom. N minus 2. N minus 2. Check out your t-statistics from back in chapter 10, and you'll say, oh, that's kind of interesting how that happens. For R, the command to perform this is core.test. Makes sense because this is correlation test. You give it the x variable and the y variable. Now let's go through a few examples and see how this actually works. Are the property crime rate in 1990 and 2000 significantly correlated? Okay. Don't have to source in the functions, but let's get into the habit of it, or let's continue the habit of it. Read in the data, attach the data. This is all you got to do to find the answer to the question. Core.test, first variable, comma, second variable. Here's the output. P-value is very much less than 0.05. Therefore, we know that the we know that the correlation is not 0, that there is indeed a correlation between the property crime rate in 1990 and the property crime rate in 2000. We're 95% confident that that correlation is between 0.67 and 0.88. Our sample correlation is 0.80. Our conclusion is because the p-value is much less than our alpha of 0.05, we reject the null hypothesis that there is no correlation between the two property crime rates. We are 95% confident that the true correlation is between 0.67 and 0.88. And this graphic illustrates that. Strong correlation between the two. Example 2, wealth and professionalism is the average wealth in the state, the GSP per capita, and the level of professionalism in its legislature, ProfLeg, correlated. This is a part of the crime data set, so we don't have to load anything new. Core.test, variable 1, variable 2. Again, these both have to be numeric. Here's the output. P-value is less than alpha. We have detected a correlation between the two, a non-zero correlation between the two. We're 95% confident that the correlation is between 0.05 and 0.55. So not a strong correlation. It's kind of a weak to moderate correlation, as illustrated here. The size of the bubble actually is the population of the state. It kind of helps us, so that tells us that this is large state. It's going to be California, and it's going to be Texas. And I don't know, one of those two is going to be New York, and the other is going to be Michigan. Are the average wealth in the state and the school enrollment correlated? Core.test, numeric, comma numeric. P-value is greater than alpha. We were not able to detect a correlation between average wealth and school enrollment. There could be a correlation between the two, but we were not able to detect it. Again, doing this by population. The color is done by violent crime rate, just because we can. There's a big clump right here. We got two outliers way out here and here. So, by the way, this is DC. So I'm thinking now there doesn't look to be any relationship, and going back a slide, p-value is greater than alpha, we didn't detect one. Is the average wealth in a state correlated with the violent crime rate in the state? Average wealth, violent crime rate, core.test. There's the p-value. We're 95% confident that the correlation between the two is between 0.20 and 0.65. This is what a correlation of about 0.5 looks like. Again, the question that you should have is this outlier and this outlier. This is DC, I think, and this is California. If we take these two out, do we get the same level of correlation, or does that correlation go away? I believe if we take these two out, correlation goes away. Which makes you wonder, should DC be a part of these analyses? If we're doing it for all the states, then I'm not sure DC should be a part of it. Something to think about. California, yeah, I'm pretty sure you got to keep California in there. It's a state. Oh wait, no, that's not California. This would be California. Connecticut, maybe? So before we get into this, let's go ahead and do the intra-lecture questions. Question 1, what does it mean for two numeric variables to be correlated? This is getting at your understanding of the word correlation between two variables. What are the possible values for the correlation between two numeric variables? And this will be the measure of correlation that we currently use. So it's from -1 to +1. And 3, what is the R code to run the correlation test? So the conclusion. Today we covered correlation, and that's all we covered. All we were looking at if two numeric variables are numerically related. We're not trying to predict or estimate a value of one numeric variable. We're just looking at the relationship between the two. Note that we can only test if a linear relationship exists. Linear. Nonlinear relationships such as parabolas are beyond this test, and we cannot predict values of the dependent variable given the correlation. That's not the purpose of correlation. Correlation is just looking at the strength of the relationship and whether it's positive or negative. Linear regression can help with both of those weaknesses to an extent. We will only look to solve the second in this course. The first one is for Stat 225, which is kind of the extension of this course. But in the next lecture, we'll look to see how we can estimate and predict values of the dependent variable. We got one more lecture, linear regression. Our function we saw today was core.test. The SCA is 42A. The readings, and we're done. One more to go. Hello and welcome to Chapter 12, and the rest of Chapter 12. This is linear regression. It's really how to do linear regression, what it means, and how to use R to get the most out of your time. So by the end of this lecture, you should be able to understand the theory behind testing the relationship between two numeric variables. So this goes above and beyond what we can do with correlation. In fact, we can actually recover the correlation from linear regression. We estimate a value of a dependent variable, predict a value of the dependent variable. Estimate is looking at an expected value, predict is looking at a future observation. Remember, confidence intervals and prediction intervals, those will be brought up again today. Better understand the p-value and how to test hypotheses. Recently we've learned how to test independence between two categorical variables. That would be the chi-squared test of independence. A categorical and a numeric variable, that would be ANOVA or the Kruskal-Wallis test. And two numeric variables, which was correlation. In this deck we're going to learn how to model, which is the next step beyond just looking at correlation. The dependent variable using independent variable or variables. If we only have one independent variable, it's called simple linear regression. If we have more than one independent variable, it's called multiple regression. We'll just call it all linear regression. So let's start with a framing example which will lead to the theory, and then seeing how to do it in R rather quickly. What's the relationship between the violent crime rate in 1990 and in 2000? Two numeric variables. Note that we now want to know more than just if there is a significant relationship. The core.test from last lecture told us there was. We want to be able to specify how much one influences the other. We want to be able to predict violent crime rates in 2000 given the value in 1990. How do we determine these things? Great question as always. Let's look at a graph to see if it can give us any clues. There's the graph. We've seen this before. So the question is, what's the relationship? And subtext is, what is the linear relationship? To summarize this relationship, we're going to use a line of best fit. A line of best fit. Which means we have to specify what we mean by line and what we mean by best. Well, we all know what a line is. It's a geometric shape, one dimension. It's got a slope and an intercept. It's a straight curve. So our line's going to have this form. Y equals intercept plus slope times the x value. Our intercept is going to be called beta dot, and our slope or effect is going to be called beta 1. Because these are Greek letters, this is referring to the population intercept and the population slope or population effect of x on y. Now we got to determine what we mean by best. That is a very, very important question. There are multiple definitions of what we could mean by best. Each of the different definitions will lead to different fitting methods. MathStat 225 will cover the different methods. It's very interesting to see the difference between ordinary least squares and weighted least squares and generalized least squares and generalized linear models, multiple and maximum likelihood. But that is for a different class. We're going to look at the easiest method called ordinary least squares. Ordinary least squares defines best as a line that minimizes the sum of the squared residual values. That is what we mean by best. Minimizes the sum of the squared residual values. In other words, if that is the line of best fit, then the sum of the squared residuals is the smallest of all possible lines. The sum of the squared residuals is the smallest of all possible lines. The vertical distance between the dot and the line we're going to call the residuals, and it is the vertical distance. So those are the residuals. We want to square those, add them up, and the line that minimizes that sum will be our best fit line. This process just requires differential calculus, which you would have gotten in 145 or 151. If you had me in 145, we'd actually did this process. As an example, none of you have had me in 151. Calc is not a prerequisite for this course, so if you have not had calculus, space out until I call you back. If you have had calculus, 151 or 145, then pay attention, because you'll see an application of what you learned in a statistical context. So we want to minimize the sum of the squared errors. We want to minimize Q. Q is defined as the sum of the squared errors. This Q is also referred to as the objective function or the target function. It's what needs to be minimized. It needs to be minimized with respect to the beta naught and beta 1, the y-intercept and the slope. Notice there's no beta naught or beta 1 here with the e, so we have to expand e, which is just the error, the difference between what you observe and what you predict according to the line. What you observe, what you predict according to the line. Still don't see any betas. But this, what we predict according to the line, this is your line. This is what you're going to be predicting according to the line. Y-intercept, slope. So this is going to be our objective function. To minimize it, the usual calculus technique, take its derivative, set the derivative, set the derivative equal to 0, solve for the parameter. Here we've got two parameters. We've got a beta naught and a beta 1. So we'll first take its derivative with respect to beta naught, solve it for beta naught, and then go back again, take the derivative with respect to beta 1, solve it for beta 1. Again, remember, if you haven't had calculus, space out. If you have had calculus, this is kind of an interesting application of it. So here we are taking its derivative with respect to beta naught. Derivative with respect to beta naught of q. Well, this is q. I just distribute the negative sign. The derivative of this is bring the 2 out front. With respect to beta naught, got a negative 1. And we keep the base. This is just the power rule. Set it equal to 0. And we're going to solve for b naught. Notice we went from betas to b's. It's because now we're restricting our b's, or this variable, to indicate something beyond the population. This is going to be our estimate of that population. So we change from beta to b. Divide both sides by -2, interpret the summation. The sum of the yi is just n times y bar. The sum b naught is just n of these b naughts. And we got a b1 times x and x bar. We're solving for b naught. Pretty easy. Remember, this is equal to 0. So we have our estimator for b naught, estimator for our population y-intercept is just y bar minus b1 x bar. What is b1? We don't know that yet. We're going to figure that out next. Hopefully b1 is not going to be a function of b naught, otherwise we'll have a circular reference. So now to determine B1, take the derivative of q with respect to beta 1. This again is q. There's beta 1, so the 2 comes out front, and we also multiply by a negative xi. Set it equal to 0, change the betas to b's. We know what b naught is. That was from our last, it's y bar minus b1 x bar. Do some algebra. So here we're just realizing that the sum of the xi is nx bar. Here we're distributing. Remember, this is equal to 0, so we're going to move all the b1 stuff on the left. Now we got b1, all the b1 stuff on the left. We're going to divide out by what's not b1. Boom. So this is our estimator for beta 1. Those are the results. This second formula can be written in a couple different ways that might be helpful. They are algebraically equivalent. I think this is the most helpful. This is the correlation. Standard deviation of the y's, standard deviation of the x's. Remember, standard deviation is a measure of spread, so this is kind of like the rise over the run times the correlation. Okay. Now everybody wake up, even if you haven't had calculus. Calculus is done for the term now. Wake up. These are the results. From all the calculus we just did, we now have an estimator for beta naught and an estimator for beta 1. And this estimator for beta 1 can also be written as the correlation times standard deviation of the y over standard deviation of the x. Can you imagine doing this by hand? Or this? For a real data set of 50, 100, 50, 100, 2 million? Here are some important quantities when you're doing this by hand. This will be the total sum of squares. This will be the sum of squares according to the model. This will be the sum of squared error. That sounds a lot like ANOVA stuff. This is mean squared error. Ooh, that also sounds like ANOVA. That's because this is ANOVA. Remember when we talked about ANOVA, one of the interpretations was, does knowledge of the independent variable give us information about the dependent variable? Well, that's what we're doing here. With ANOVA, that independent variable was a categorical variable. With regression, it's a numeric variable. And these ANOVA measurements and the table that you can create, from the ANOVA table that you can create, gets interpreted the same way, about the model as a whole. So the ANOVA stuff talks about the model as a whole. This R squared is a measure of how well the model fits the data. It's not surprising that this is R squared, because if you take your correlation, your little r, and square it, you'll get the same value. Here's the ANOVA table that you would get for regression. Again, the ANOVA table talks about the model as a whole, which might be important. So here's how to do it in R. There's our usual preamble, bring in the extra functionality, load the data. We're going to use the crime data as usual. First step, create the model. Back when we were doing analysis of variance, it would be AOV here. Now we're doing LM. That is an LM for linear modeling. Dependent variable, there's the tilde, independent variable. And then we do the summary of it. We can either do the summary in terms of the analysis of variance, which would be summary.AOV, or we can do a summary of the regression results, which would just be summary, or it could be summary.LM. Here's the analysis of variance results. P-value is less than alpha. That means this model does give us a lot of information about the dependent variable. Specifically, this violent crime rate in 1990 does tell us a lot about the violent crime rate in 2000. Because the p-value is less than our usual alpha of 0.05, we reject the null hypothesis that the model does not offer significant understanding of the relationship between the violent crime rates in 1990 and 2000. Notice in many ways this tells us nothing beyond the correlation, what correlation told us. 3 stars, that means the p-value is between 0 and 0.001. So the ANOVA output's not useful for us at this moment. You'll see later how it's useful. What's useful is going to be just the summary.lm, or summary if you're fitting it using the lm function. Here's the output of the summary. 4 parts to it. First part reminds us of what our model was. Second part gives us a 5-number summary about the residuals. Third part is the regression table. Fourth part tells us about the model as a whole. The regression table tells us about the variables and the levels within those variables and how they affect the dependent variable. The model as a whole tells us about the model itself. So this would be a lot of the ANOVA and the R-squared stuff. P-value for vcrime 90 indicates that the effect of the violent crime rate in 1990 on our violent crime rate in 2000 is not 0. We estimate it to be 0.58065. In other words, for every 1 increase in the violent crime rate in 1990, the violent crime rate in 2000 goes up by an average of 0.58065. This is the slope. It's the effect. It's interpreted the same way as slope is. For every 1 increase in x, this y will go up by the slope. Here, since we're talking about variables that have meaning, this is also referred to as the effect of x on y. The r-squared value is 0.877. R calls it the multiple r-squared to be generic. This is the r-squared. It's 0.877. This means that the correlation between vcrime 90 and vcrime 00 is just the square root of that. We'll note that that's a moderately strong correlation. Right now, that's the only thing you should take from it. If you actually do the analysis of variance table, you'll see the F value of 349.3. Degrees of freedom for the model is 1. Degrees of freedom for the error is 49. If I go back, I believe we see that. Degrees of freedom for the model is 1. Degrees of freedom for the error is 49. There is the F statistic of 349.3. This p-value here, going forward, is the same as this p-value here. So this is one of the cases where R simplifies your analysis, simplifies the calculation so much, but now you have to interpret what R is telling you. So the burden is now only on interpreting, not on the calculations. So here are some things we know. The effect of 1990 violent crime rate on 2000 is 0.58065. 0.58065. For every 1 increase in the violent crime rate in 1990, the estimated violent crime rate in 2000 increases by 0.58065. In other words, this 0.58065 is the slope of the line of best fit. Going back, the intercept, the y-intercept for that line of best fit is 109.52716. That means if your violent crime rate in 1990 is 0, then your estimated violent crime rate in 2000 is 109.52716. The effect of the 1990 violent crime rate on 2000 is not 0 because the p-value is less than alpha. We don't have confidence intervals for it yet. We'll get those pretty soon. The model explains 87.7% of the variation. The model, this is the r-squared. The model explains 87.7% of the variation in the violent crime rate in 2000. So the r-squared is interpreted as the percent of variation explained by the model on the dependent variable. The mean squared error is the square of 85.55. 85.55 is the standard error, so to get the mean squared error, just square it. So again, R takes very little to get this. Run the model and do a summary of the model, and you get all of this. Hard part is interpreting it. I would suggest just focusing on the parts that we have discussed a lot: the estimate, the p-value, multiple r squared, and what those mean. So there's our line of best fit. This is the estimate for the intercept. This is the estimate for v crime 90. To get the confidence interval for the slope and the intercept, we run confint. So this will give you the confidence interval for the slope and the intercept. Here's the output. So we're 95% confident that the true effect of violent crime rate in 1990 on the violent crime rate in 2000 is between 0.52 and 0.64. So this is a confidence interval for the slope. Similarly, this top number is a confidence interval for the y-intercept. But in none of my analyses have I ever cared about the y-intercept. It's always been the slope that I care about, the effect of x on y. I'm 95% confident that the effect of x on y is between 0.52 and 0.64. We can also estimate the violent crime rate in 2000 for a state with a 90 violent crime rate of 1500. And we can get a confidence interval for that estimate. So going back a slide, the confident function gives you a confidence interval for the slope and the y-intercept. Going forward, the predict with interval equals confidence gives you a confidence interval for that estimate. To use predict, we give the model, we give the new data, and we specify we want the interval to be a confidence interval. Notice new data equals data.frame. That needs to be typed over and over and over again. Inside the parentheses of the data.frame, give it the independent variable and a value for the independent variable. Independent variable for this model is vcrime 90, and we want to estimate the 2000 violent crime rate for a state with a 1990 violent crime rate of 1500. So this 1500 is this 1500. So we are 95% confident that the expected violent crime rate in 2000 for a state with a rate of 1500 in 1990 is between 918 and 1043, with a point estimate of 981. So LWR is the lower confidence bound, UPR is the upper confidence bound, and fit is our point estimate. That's our line, that's our point on the line. And we can do one more thing. We can do a prediction interval. Going back a slide, confidence interval, remember, is an interval on the expected value. Forward, a prediction interval is an interval on a future observation. The only difference between getting a prediction interval and a confidence interval is specifying interval equals prediction for a prediction interval and interval equals confidence for a confidence interval. Here's the output. So we are 95% confident that the violent crime rate in 2000 for a state with a rate of 1500 in 1990 is between 797 and 1164. Notice we're talking about the violent crime rate, not the expected violent crime rate. The expected violent crime rate would be the confidence interval. The actual violent crime rate would be a prediction interval. Notice also that the prediction interval is much wider than the confidence interval. That doesn't surprise us from previous labs because the prediction interval takes into consideration the uncertainty in the expected value, aka the confidence interval, plus the uncertainty in the data itself. So the prediction interval is always going to be wider than the confidence interval. Notice also that the fit, or the point estimate, for the prediction interval and the confidence interval are the same. So the difference between the two is the wording. Are you looking at an expected value in the future or an observation in the future? The former, you should use confidence intervals. The latter, you should use prediction intervals. And this illustrates it. The dots are the states. The blue line is our line of best fit. The thick black, that's our confidence interval. The red is going to be our prediction interval. So we're 95% confident that the observation will be inside this red line. We're 95% confident that the expected finite crime rate in 2000 is in the black line. So let's see 4 examples of putting all this to work. We want to look at the relationship between violent crime rate in 2000 and school enrollment in 1990. Violent crime rate in 2000 is going to be our dependent variable, and the school enrollment in 1990 is our independent variable, because dependent variable is going to depend on the other variable, and 2000 is later than 1990, so this has to depend on something earlier. Since it's from the crime data set, we don't need to load anything extra. First line is for defining the model. Again, that's LM. Second line does a summary of that model. 2 lines to do all these calculations. There's the output. 4 parts. Reminds us of what we typed in. 5-number summary for the residuals. Regression table tells us about the variables and the levels of the variables and how they affect the dependent variable. And then the model talks about the model as a whole. Notice the R² for the model is 0.01329. So this model describes 1.3% of the variation in the violent crime rate. In other words, this is a lousy model. The F statistic is 0.66. That leads to a p-value of 0.4204. Thinking back to the ANOVA stuff, this is greater than alpha, failed to reject the null hypothesis. Therefore, this model gives no additional information about the violent crime rate in 2000. We can also see this in the 0.420 p-value for enrollment. This is greater than alpha, so the enrollment could be 0. The effect of enrollment could be 0, could be positive, could be negative. Because the p-value is so large, we don't know. So in other words, this model was a waste of time. Example 2, relationship between the 2000 violent crime rate and the average wealth in 1990. 2000 violent crime rate is going to be the dependent variable because it will depend on an earlier event. We also want to predict the 2000 violent crime rate for a state with an average wealth of 50,000. Create the model, dependent variable, tilde, independent variable, summary of the model, confidence intervals, and then the predict. We're doing a prediction interval because we're asked what's predicted. Model, new data equals data.frame of, this is the independent variable, and we're specifying 50,000 for the independent variable. And we're saying we want a prediction interval. Interval equals prediction. There's regression output. The effect of GSP per capita in 1990 on the violent crime rate is not 0. P-value is too small. The estimate is 0.01598. For every additional dollar in GSP per capita in 1990, the violent crime rate on average goes up by 0.01598. Multiple R² is rather small. While this model does help with some description, there's a lot of variation that's not described by the model. This model only describes 28% of the variation. That leaves 72% unexplained. We're 95% confident that the effect of GSP per capita in 1990 on, what are we doing? Violent crime rate in 2000 is between 0.00862 and 0.02333. This is for every $1 increase. The effect on violent crime rate in 2000 is between this number and this number. If I want to do it for a $1,000 increase, which it's much more realistic, then we just multiply these by 1,000. So for every $1,000 increase, the GSP in GSP per capita in 1990, the violent crime rate in 2000 goes up by between 8.6 and 23.3. I'm also 95% confident that the violent crime rate in 2000 will be between 409 and 1338, with a point estimate of 873. Not the expected GSP per capita, I'm sorry, not the expected violent crime rate, but the crime rate. The state will have a violent crime rate between 409 and 1338. If I want to talk about the expected violent crime rate in 2000, then I look at a confidence interval. But here I've got a prediction interval, so I'm looking at an actual crime rate. Relationship between the 2000 violent crime rate and the unemployment rate in 1990, dependent variable, independent variable. And if there is a relationship, estimate the violent crime rate given the 1990 unemployment rate is 10%. So this is talking about an estimated value, so this will be for a confidence interval. Dependent variable tilde independent variable summary. This will give us the regression table that we want. P-value on the unemployment rate in 1990 is 0.373. This value is greater than alpha, therefore the unemployment rate in 1990's effect on the dependent variable is positive, negative, 0. We don't know. P-value is greater than alpha, therefore we did not detect an effect of the unemployment rate in 1990 on the violent crime rate in 2000. It may exist, we just didn't detect it. The R-squared is 0.01624, so this model describes 1.6% of the variation, leaving 98.4% unexplained. P-value for the model is 0.3728. Therefore, this model does not give us any important information about the violent crime rate in 2000. So in other words, because the p-value is so small, we didn't get anything out of this model. Example 4, the violent crime rate from urban percent and region. So now we have two independent variables. Not only do we have two independent variables, but one of those independent variables is categorical. So dependent variable is still the 2000 violent crime rate numeric. Independent variables are percent of population in urban numeric. And for census regions, categorical. We can do this with linear modeling. And we need to estimate, so this will be a confidence interval. Here's how we do LM, dependent variable, tilde. Here are the two independent variables. That is a star. It's located on top of your 8, probably. We could also use a plus. The difference between the two is if we use a star, then the relationship, then the effect of urban percent can vary across the 4 census regions, and the y-intercept can differ across the 4 regions. If we use a plus, then only the y-intercept will differ across the 4 regions. We're going to do a summary.aov for reasons you'll see pretty soon. Then we're going to do a predict. Remember, it's a confidence interval. We've got two independent variables, so we have to specify values for both independent variables. First independent variable, urban P, that's a 90% urban population. The second is for census 4, it's in the south. Urban P is numeric, so we just have to give a number. Census 4 is categorical, so we have to put it in quotation marks. Here are the results. Here's the ANOVA output. Each row refers to a different part of the model. First one refers to the effect of just the urban percent. Second row looks only at the effect of the census region. Third is for the interaction. This is because of the star. You use the star or an asterisk. This is statistically significant. P-value is greater than alpha. Therefore, we should keep this interaction term. If this number were greater than alpha, then we would refit this using a plus instead of a times. But this is less than alpha, so we fit it using just a times, which is what this says. We need to predict the 2000 violent crime rate for a southern state. Estimate. This word here should be estimate. With a population of 90%. So we use the predict function on the model. New data equals data.frame. Values for each of the two independent variables. Urban percent is 90. Census 4 is south. Quote, south, quote. Interval equals confidence, because we need to estimate. Wow, there's another error here. This is the output. Point estimate, lower confidence bound, upper confidence bound. And there should be a confidence interval. I believe. Although I've made that mistake so often here, this might be what's wrong. Try it with confidence, see if you get this. Try it with predict, see if you get this. Here's the graphic. Notice that the lines of best fits have different slopes and different intercepts. That's a result of us using the star. If we had used plus instead of star, those four lines would be parallel, because the effect would be the same. The y-intercept would be different. The orange refers to the Midwest, green to the Northeast, red to the South, blue to the West. So urban percentage on violent crime rate for the South is strongest. It's the steepest line. Urban percentage effect on violent crime rate for the Northeast is actually negative. So the higher the urban percentage in a Northeast state, the lower the violent crime rate, which I find interesting. Midwest and West, the orange and the blue, they're about the same. Nothing overly exciting about those. But the South is interesting, and the Northeast are interesting. So let's go to the intra-lecture questions. There's 3 of them as usual. These 3 deal with R functions. Question 1, what does the LM function do in R? Again, that's LM, lowercase l, lowercase m. Question 2, what does the confint function do in R? Be careful, don't just say it calculates the confidence intervals. What does it calculate the confidence intervals of? And 3, what does the predict function do? And now, sadly, conclusion for our last slide deck. Today's slide deck, we introduced linear regression. This procedure helps us determine how 2 numeric variables are related. So at this point, we can tell a test if a linear relationship exists. We could use core.test for that. And how they are related, the effect of the independent variable on the dependent variable, and how to predict and estimate values of the dependent variable. We can do all that now. And we can do that with the LM function, linear modeling. And this just scratches the surface of what you can do with linear modeling. Stat 225 gets you even further. In the future, we've got nothing new in this course. The very last lecture is just going to review everything that we've done. Regression and ANOVA are continued in Stat 225, linear models. We will practice all procedures, or you should practice all procedures. You should review all procedures. And then the usual 3 reminders. Here are the R functions we did today. LM does the actual linear modeling. Dependent variable, tilde, independent variable, stores results in whatever variable you put here. I tend to use mod 1, mod 2, mod 3. Summary provides a regression table. Summary.AOV provides the ANOVA table. Summary.AOV, the ANOVA table, helps you determine if a variable is statistically significant and should be kept in the model. More about that in Stat 225. We can also do the predict. We can predict and get a confidence interval. So we're looking at expected values. We can do a predict and get a prediction interval where we look at future observed values. The regressions are found in SCA 42A and 42B, stored in the usual place. There are the readings. That's the end. The last lecture will just be an overview of what we've done. Thank you very much. 1000 is between 83.9 and 183.5. So we have a lot of evidence here that it did go down. Because remember, this is 1990 minus 2000. So positive numbers mean 1990s crime rates were higher. Difference in 2 proportions. We can use the binomial plot. The requirement here is that the expected number of successes is at least 5 in each group. Sometimes it's at least 10. I recommend at least 30. When you take later stat courses, you'll figure out why at least 30 is a good rule of thumb. The R function is prop.test. The one used in the Hawks book is wald.test. There we go. So I looked through the class, and through all of my stat classes, I'm comparing them. There's 34 in one of my stat classes. There's 41 in another one of my stat classes. And the first of my stat classes, the number of people with wearing hats is 14. And the other one, the number of people wearing hats is 22. I would like to see if there is a reason for this difference. I've got to change that to a 2. And it could be because my first stat class is first period and my second stat class is 6th period. So I would like to look at this data first. You got to give it both x values and both n values. Notice the 2 x values are held together with a C function, and both n values are held together with a C function. So this is vertical axis, it's proportion. We've got the observed proportion being the horizontal line, and then this illustrates the 95% confidence interval. So it looks like there's a lot of overlap, so I would expect there not to be, or I would expect the difference between the two to include the value of 0. So this will be the prop test for Hawks. It'll be the Wald test. Prop test says that the 95% confidence interval for first period versus sixth period is from negative 0.38 to 0.13, meaning since 0 is in there, it tells me that it's reasonable to conclude that there is no real difference in the hat wearing propensity of the two classes. The Wald test, which will be the Hawks version, is going to give us something similar, but not quite correctish, dare I say. It's going to be from negative 0.35 to 0.10. So negative 35% to 10%. What are the assumptions of this? You just have to get enough successes and failures in order to ensure that the distribution of P is approximately normal. Two-parameter procedure for the ratio of two variances. Notice it's the ratio of two variances, not the difference. For the mean and for the proportion, it was always differences. For the variance, it's going to be the ratio. The graphic is going to be the side-by-side box and whiskers plot. Requires that the data are normally distributed in each of the populations, so use the Shapiro-Wilk test. The R function is var.test. Is var.test. And if you've got two samples that are separate, then you'd use this version of it. If you've got one variable that you want to split off into different groups, you'd use this. I guess we could do compare the variances for, what do we do? The enrollments. Let's do the enrollments. Oh, we already know enrollments are not normally distributed. That's okay. So we'll do the Shapiro-Wilk test for the enrollment in 1990 and in 2000. 90, it's sufficiently normal. In 2000, it's not. But notice there are procedures for when this assumption is not met, but we're not covering them in this class. So test the normality, and regardless of the outcome, use the var test. We're 95% confident that the ratio of the two variances is between 0.43 and 1.31. Since 1 is in this interval, why 1? Because we're looking at the ratio. If 1 is in this interval, then the ratio of the two variances is 1, or the two variances are equal. So for the ratio of two variances, we're looking to see if 1 is in the interval, to see if the variances are different. For everything else, we've looked to see if 0 is in the interval. Since 1 is in this ratio, there is no evidence that the variances are different. Or you could also think it's reasonable to claim that the variances are the same. When we get to the hypothesis testing part, we'll be able to interpret more of these values, but we're just paying attention to the confidence intervals for now. And that's it. Not too much today, he said laughingly. We looked at these things today. We looked at single population mean, proportion, and variance. We looked at comparing two means, two proportions, and two variances. For the means and the proportions, it was minusing were the difference. For the variance, it was the ratio. Beyond the scope of this course to explain why. We also looked at the testing normality assumption. This is a new test, Shapiro-Wilk test. You already know how to test for symmetry using the Hildebrand rule, but this is the normality assumption test. So not too much today. Let me give you a little suggestion. Go through this lecture one more time, hit pause, run the code yourself, just to get a feel for it. Future work, Lab D will be something that you can look at in the future. More importantly, we're going to be looking at the flip side of the confidence intervals. We're going to call this the p-value. The p-value is just a measure of how well the data support the null hypothesis. But that means we have to learn how to create a null hypothesis, a good null hypothesis. Usually the scientist will give you that null hypothesis, and once the scientist gives you the null hypothesis and the data, you can go into the analysis. But since you're scientists already, you're going to be the one generating those null hypotheses. Here's some SEAs that are available to you, 6A and 6B. And then note we start the SEAs in double digits. These are just scripts. These double-digit SEAs are just scripts. The numbering is the first digit is a 1 if you're dealing with one population. First digit a 2 means you're dealing with two populations. 1 is for means, 2 is for proportions, 3 is for variances. So SEA 11 is looking at estimating one population mean. SEA 22 is 2 population proportions. SEA 13 is 1 population